Hi everyone and welcome back to another lecture of computer organization and architecture. So today we'll start with the lecture 4A of this particular subject. So today we'll learn about data part. Basically how exactly an instruction is being fetched and what happens throughout the whole bus, how data gets transferred, those things I learned. So I gave you a high level picture previously. Now we'll exactly go into the CPU, inside the CPU, and see exactly how it decodes the instruction as well. We'll learn about decoding, we'll learn about control unit. So control unit is the main manager basically, which manages everything. Okay, so it is there to decode the instruction, what does each instruction means, and it instructs everything, right? So inside CPU we have control unit and arithmetic logic unit. Arithmetic logic unit performs the arithmetic and logical operations that will be given by the control unit. So that we'll learn. So I previously told you, right, later on we'll study about control unit. So today is the day we'll study about control unit. Then I will understand CPU cycle. So inside a CPU cycle, how much time happens. So we already know about instruction cycle. We'll know about what is CPU cycle, what is the difference between instruction cycle and CPU cycle. Then we'll learn about hardwired control unit. So there are many types of way in which you can implement your control unit. So one method is hardwired control unit. So and in the next lecture we'll learn different methods of control unit. So that we'll study in the next lecture. So yeah, what is basically I told you previously, CPU. What is a CPU? CPU is the brain of the computer responsible for processing input, managing data, producing output. It performs all essential operations required for the computer to function. This we already know. This I have already told you. It is basically the heart and brain of the CPU. Heart and brain. So without your heart and brain, your body will not work. Okay. Obviously, all the parts are responsible, but the most important parts are heart and brain. Okay, now you can think the brain to be the control unit and your heart to be the like also without heart also you cannot work, is the ALU. Why brain to be the control unit? Because control unit actually instructs everything what to perform. Heart does, heart just pumps the blood, right? Because brain is sending signal, pump the blood faster, so to pump the blood faster. So that is what control unit is. Control unit is the brain of the computer and heart is the ALU of the computer. Just giving you an analogy. It is nothing theoretical, nothing like that. I'm just giving you an analogy. So in this, what does data path mean? What do we mean by data path? Data path is a collection of hardware components within the CPU that perform operations on data. It includes functional units like ALU, multiplexer, and registers. Once I will show you the picture, there you will understand this. So data path, okay, the picture is not here. The picture is here, right? This is the data path. So what does data path means? Exactly what the name says, data and path. So it talks about how data flows. Now you need to focus more. How exactly, I will write in different color, exactly how the data flows through the whole CPU, right? Within the CPU, how is data flowing? So that is what it is saying. It is the interconnection of hardware components, right? Because you will obviously require hardware, right? Digital component is there which understands whether it is 0 and 1, but at the end it is a hardware component, right? So hardware, how is everything connected? So actually, I will tell you one thing, that everything is interconnected with respect to the control unit. So all the internal components, first thing is all the internal components of CPU are interconnected. Okay, if I can through what? Through control unit. Through control unit. Now, why is it so? Let's take an example of like your job or something. You are in the job, right? And your manager is there. So your manager is not just your manager. Your manager is manager of a lot of employees, right? Why is it so? Why is it so? Your manager needs to be in connect. So your manager is here. It needs to be in connect with lot of people. Why is it so? Because it needs to give assign task to everyone, because control unit is the main thing that assigns the task, and then control unit assigns the task, as I explained at the starting of this lecture. So obviously it has to be connected with all the components so that it can assign some task, right? Whether to perform a read or write. How it will assign that I will talk about later on, but for now control unit at least needs to be connected. This is hardware, I'm talking about hardware. It needs to be connected to every component of the CPU to assign any task to any of the component. Let's say ALU, it needs to be connected to ALU, it needs to be connected to the PC, it needs to be connected to the instruction register, it needs to be connected to everything. So if you see in the block diagram, this bus, right, there is a common interconnection between everything, not just control unit, through everything. Why is that the case? Because where is my control unit? So this is my control unit, the instruction decoder and control signal. So it through the bus it will send some control signal to PC. So generally PC can have two inputs through the control signal. It can either give data on the bus or it can take data from the bus. Because sometimes what I want to perform is I want to perform write operation on PC. So it will be in, then the in control signal will be 1. If I want to read from the PC, then the out control signal will be 1. Okay. So exactly, I hope you understood that how does my instructional logic decoder send control signals. How does it decode? We'll come to that later on. First of all, let's just understand that control unit has decoded the instruction, and it knows that I have to read from the PC. If it has to read from the PC, it will send some signal through this common bus. To the PC that, hey man, I have made my signal 1 out of the signal 1. So please give my value, give my PC value. So that is what my control unit does. Okay. So there are many components of a control unit. That is ALU. Obviously ALU, it's not control unit, sorry, data path. ALU will be there. Performs arithmetic and logical units, multipliers and dividers. Handles complex arithmetic computation. Okay. So this is just the extension of ALU. Registers, temporary storage for data. So there are many registers here, right? Like memory data register, instruction register, and these general purpose register. So in the data path, all these components will be present. That is what is written. What components are present in the data path? Obviously, buses will be there to transfer the data. And control signals directs the flow of the data and determine operation to perform. So what type of operation do I need to perform? Do I need to perform read operation, write operation? Your manager tells you, right, what you need to do. Okay, like exactly what task you need to accomplish. That your manager tells you. So then let's come to the function of a data path. Instruction fetch. So I will tell you the whole cycle. Instruction cycle I have already explained. Again I will explain with the help of data path now. So things will be more and more clear now. So there are two cycles, right? One is execute cycle and instruction fetch. So what happens in instruction fetch? There are a lot of things that happen on instruction fetch only. In instruction fetch, retrieves instructions from memory. It retrieves the instructions from the memory. Okay. So from the memory somewhere there will be some instruction present, right? In the memory somewhere there will be some instruction present. I will retrieve it and store it where? I will store it in instruction register. So instruction register gets the instruction from the memory at the program's counter's value. So PC will point to memory and I will store it in my instruction register that I already have told. I will show with the data path example. Then what happens? Data movement transfers data between registers and memory execution. Like then some data movement happens like operand fetch. After instruction fetch, what we do? Operand fetch was also inside the cycle, right? Inside the execution cycle. So we can do operand fetch, or we can fetch the address of the operands. Then again, I will go to the effective address. Then what happens? Execution. It processes data using the ALU. So the data has been fetched to its own registers. Then we process the data using ALU, and the control signal directs it, and other functional units. There are other functional units nowadays. Obviously, ALU is not there, right? A lot of things are there that does the computations. So how does it happen actually in the data path? How does it happen? I've already told you, CU is your manager. Okay. So first what will happen is point 1. If let's understand, if I am loading something, okay, I am doing some instruction. I have an instruction I1 that is present at this location 2000. Okay, so hence my PC value will be what? PC value will be simply 2000. PC value is 2000, right? PC value initially is 2000. So when I will start to like execute this instruction, what will happen? First I will fetch this instruction. So first the instruction will be first the address of the first the contents of the PC will be copied to memory address register. So it's not like I will directly copy the instruction register. It's not like that. It's not that simple. So first I will copy the contents present in PC to memory address register. So what will happen? Exactly what will happen? In step 1, CU will make the out of PC to be 1 and in of memory address register to be 1. All the other bits will be 0. Okay, so what will happen? Data will go out from the PC on the common system bus and it will go to where? It will go to memory address bus, as in is on for memory address register and out is on for PC. So data will go from here to memory address register. This is the data path. Okay, next what will happen? Now the address has been stored in memory address register. Then I will go to that location that is pointed by memory address register and I will copy that on my instruction register. So now what will happen is that then I will go to the memory address register that is stored in MAR and store the contents in IR. So somewhere in memory it will be stored, right? Like 2000. MAR has 2000 now. So what will happen is now the control signal will actually make the MAR out. Okay, MAR out, and then it will go to the MAR signal. Here what will happen? CU will make the CU makes the out of MAR 1 and in of IR as 1. Whenever there is some out signal, right, we already know that it is coming from an address register. So we will only go to the address. We will not directly store it somewhere. We will directly go to that address. Whatever the output of MAR, it is already known to me that it is an address. It is address of what? It can be address of anything like operand, or it can be address of a a instruction. Okay, so it will be address and I will go to that address somewhere in the memory location. Somewhere in the memory there will be some instruction, and that instruction will be like this instruction will be fetched, copied to IR, as IR has its in signal on. Okay, so it will be copied to IR. So now it is done. So after this what will happen? Then the control unit will take some input from the IR. So after this the control unit, so instruction has been fetched. So as soon as the instruction has been fetched, what will the control unit say? Control unit will then tell, please PC update your value PC +1. Then what will happen? Then I will go, then the third step will happen. Then here, this is the decoding step, right? Decoding step. Here control unit takes input from the IR and it decodes. We have a decoding circuit. Don't worry about that. We have a decoding circuit. I will talk about that later on. It will decode, right? It will simply decode the instruction. So if there is some like data storage, something like that, right? What we do is we store it. Like if there is some data in or data out, like we want to fetch the operands. So here after decoding, what the control unit will do is it will do operand fetch. If there is some operand fetch or if there is some addressing mode, whatever there is, it depends. All of it depends on the instruction. So what will happen is now somehow control unit has got to know that there are two operands and the addresses of this operand has been provided. So operand 1 has address location as 2000, not 2100, and operand 2 has address location of 200. Okay, so these are the address locations of the operand 1 and operand 2. So now we know this. Now what we can do? Now what we can do is we will go to this address and fetch this where. Now I will store these addresses where these addresses will again be stored in memory address register, and then after storing it in memory address register, control unit will send some signals. Then again I will go to this location and then the operands will be stored in memory data register. Okay, why? Because CPU obviously, again I told you previously, it doesn't trust everyone. So there will be some memory data register where it will be stored. Then from the memory data register, the ALU will take inputs. Okay, ALU doesn't take inputs directly from the memory data register. ALU will take some inputs. Okay, so this is just an example. Don't go too much into this. Just I'm giving you an example. So after that, the ALU will store back the results. ALU will write the results in accumulator. Result is stored. Okay, and after that result is stored, we then put it in the memory data register. From accumulator it goes to memory data register, and from there it goes to the memory. Okay, it doesn't directly go to the memory. We don't directly do it. We store it in memory data register, and then control unit gives some MDR, memory data register signal out to be 1, and then the data goes out and it goes into the memory. Okay, so this is what happens. Like I have just given you a high level example. A lot of things internally happen also, but I have just tried to give you a high level example exactly how data flows and what happens in a data path. So this is a data path basically. I hope you understood the significance of data path. Okay, so the main question comes is, why is a common bus used in a computer system? Why is there a common bus? What is the requirement for common bus? If a system has 32 registers, memory, an ALU and a program status word. So like I've just given you an example and other components. There would be minimum of 36 components. So just giving you an example. So here if I consider if a CPU has 32 registers, memory, an ALU, a program status word, it will have 36 components. Connecting this would require more than 1260 connections. How am I getting this 1260? Basically, I have total 36 components. 36 components I have, and I have to choose either two, because all those two should always be interconnected. I have to choose any two, and any two should be interconnected. How many ways can I choose two? Okay, it should be 36 C2, that is 1 2, that is 36 into 35, that is 1260. Let's take a smaller example. If I have two components and if I want to connect those two, how many ways can I connect it? In only single way, just a single way, right? It is 2C2 only, this 2. If I have three components, how many ways can I connect it? I have three components, how many ways can I connect it? So this is C1, this is C1, this is C2, and this is C3. Okay, so this will be here, this will be here, and this will be here, and all three are connected. So it is 3C2, correct? It will be 3C2. Why it will be 3C2? I have three components, and always I have to choose any two, because this wire can be connected between any two. Then if I have four components, okay, I will take in the next page. I'll go in the next page. This is C1, this is C2, this is C3, this is C4. Now it is connected here, here it should be connected, here it should be connected, here. Okay, and this also should be connected, right? Any two components I have to choose. So how many ways? 1, 2. How many wires are there? 1, 2, 3, 4, 5, 6. Now if I apply my formula, 4 components, I have to choose any two. 4C2. It is 4 times 3 divided by 2. So it is simply 2 times 3, that is 6. Why this divide by 2 comes? Because this is the twice, like few connections will be repeated if I am choosing the repeated ones. So I hope you get the understanding of this. So yeah, this right, this should be actually divided by 2 as well. There will be division by 2. So there will be 1260 wires. Can you imagine how many wires is that? That is huge number of wires. To reduce the complexity, a common bus is introduced to connect all the components. So I cannot do like each component will be interconnected by them. Then like each when I will send some data from C1 to C3, only this wire will be used. If I send some data from C2 to C4, only this wire will be used. That will be very complex and hectic because I will have so many wires. I don't want that. So obviously, to simplify, we have a common bus, a common where data flows at once. Only two components can talk. In new architecture, things can be different, so don't come in the comment section and blame me, sir, you got it wrong. I am just giving you an example. Obviously, when we implement, things will change. I am giving you a simplistic view that at once only two components can talk. One will send the data, another one will receive the data on the common bus. Only two components communicate at a time. Control signal determines which components can access the bus. So I told you, right? Here I have told you that it makes CU makes MDR out 1, CU makes this out MAR 1, in IR 1, all these things it makes, right? So it should be MDR out MDR actually, not MDR. So CU actually decides which bus needs to be turned on. So just like your manager decides who needs to do what task, same like that. This approach simplifies and minimizes the required connections. Okay, so I'm just giving you an example. Then currently the architecture can be different. I'm just giving you how we started. Now, how ALU MBR registers common bus process the data. I've already explained this actually. You can go through this. You can read this, okay? You can go through this. I have told you, right? We have elementary operations known as hardware operations. So each time a elementary operation has been performed, it is known as a micro operation. Okay, a register to register transfer operation is a micro operation. So I have already explained this, like how data transfer works. So you can go through and read this. I will not read this again. Okay, so let's do a question. So try to pause the video and whatever concept you have learned till now, try to solve it by yourself. So let's read this question. Consider the following data path. Just hold on a second. Consider the following data path. The ALU, the bus and the registers in the data path are of identical size. So everything is of identical size, like all the registers are identical size. All operations including incrementation of PC and the GRPs are carried out by the ALU. So even if I increment my PC, right, PC incrementation, okay, after every instruction page, that will be correct done by ALU. That there is no separate ALU for that. 2 clock cycles are needed for memory read. Okay, the first one for loading the address in the MAR and the next one for loading data from MDR. So as I told you previously, right, we don't exactly load from the memory directly. First we load the address of the data on the MAR, then we load it to the MDR. So one cycle, 1 clock for MAR, loading the address to the MAR, then another clock for loading the data to the MDR. Okay, next what we have, next we have the instruction add R0 R0 has the register transfer interpretation that R0 will be equals to R0 plus R1. The minimum number of clock cycles needed for the execution of this instruction. So what will be the minimum number of clock cycles for this instruction? So they are only telling me execution cycle, right? Please read, don't mess up here. Execution cycle of the instruction. So I don't need to fetch the instruction. Again, they have mentioned here execution cycle, so we can ignore fetch cycle. Assumption is the instruction has already been fetched. The instruction has already been fetched in the IR. Okay, I don't need to do that. So how many clock cycles will I require? So first, one clock cycle will be required because R0, right? It is already inside the CPU. I don't need a memory access here. I directly go to R0 and get the data. So first one cycle for storing the value of R0 to some memory data register of CPU, MDR of CPU 1. Then another cycle, this is just for the data transfer. Address I don't need because this is inside the CPU, this is the CPU register. Another cycle for storing the data MDR2 from R1. Then I perform my addition, right? So it adds the value. To perform addition, do I need any extra cycle? They have just mentioned me that for reading and writing the data, I need one cycle. They have not told me that I will need any extra cycle for adding the data. I can instantly add the data and then store the result. So like I will get the data to S. Here they have given me the two inputs as S and T, right? So I will from this registers, one data will come to S, another data will come to T. So this is MDR1 and MDR2. I can write this as directly S and T. Okay. Next, I will add them and directly put it in the bus. It is there in the bus, right? So then it is in the bus. So it will go to where it will be stored in register. So again, I will require one more cycle to store the value, to transfer the value from ALU to the register. Correct. So one cycle will be taken to transfer the data from accumulator to register R0. So total how many cycles I required? 3 cycles. If fetch cycle was included, then how many cycles will be required? How many cycles will be required if fetch cycle was included? If fetch cycle was included, I have to first load the address on MAR from the PC. That will be one cycle. Then I have to load the instruction that is pointed by the MAR to IR. So 2 cycles. Okay. 2 cycles. So total how many cycles I will be requiring? For the whole instruction, 5 cycles. Total I will be requiring 5 cycles. Now there is an important word here. Important mention that all the data path have identical size. Why is it so important? Why is it so important to read this statement? All this path, right, has identical size. Let me take an example. Let's say your signal path or data path can only transfer 8 bits in one cycle, but your general purpose registers are 16 bits. So how many cycles will it require for me to transfer the data from a general purpose register to T? Will it be 1 or 2 cycles? Please let me know in the comments or just reply me somewhere. How many cycles will I be requiring to transfer the data from a general purpose register to T register? How many cycles? 2 cycles. There I'll be requiring 2 cycles. Okay. So why? In the cycle C1, first 8 bits will go. Then in the second cycle, next 8 bits will go, total 16 bits. I cannot transfer all 8 bits at a time. So it will be twice as much. Now if I had been requiring 3 cycles, there I would have been requiring 6 cycles. And for the whole instruction, it will be 10 cycles. If everything is 16 bit data, if let's for example take that the PC value is 8 bits only. It is 8 bits only. So it will take now 6 cycles for this particular execution phase, and for the PC value, it will take 3 cycles, because here, right, I will not be requiring 2 cycles, only 3 cycles. So total I will have 9 cycles. Total instruction cycle will be 9. So it depends, right? So you have to read all this statement, small information. Small informations are also very, very important. They can trick you in the examination. Let's read this next question. So consider the following data path. We have this common bus, MAR, MDR, all these things are there. These will go to the memory, and these are PCIR. All these things we know. Consider an instruction, same thing only. R0 is equals to R1 plus R2. The following steps are used to execute it over the given data path. Assume that the PC is incremented appropriately. So PC is incremented appropriately. We don't have to worry about the PC. So it is telling us we don't have to worry about the PC. We don't have to worry about increment of PC. The subscripts R and W are for read and write operation. So these are few operations that are happening, right? Which one of the following is the correct order of execution of the above steps? Which of the following is the correct order of execution of the above steps? So in a data path, what happens? I've already explained at the starting of the lecture exactly what is the sequence of steps that happens, right? In a data path, it is asking exactly that. So it is telling me R2, I'm reading R2 and I'm reading the temp1, right? I'm reading the temp1 register and I'm performing addition operation. I already don't have started the addition operation. First operation should be what? First operation is basically fetching the address from the PC. Okay, reading the contents of the PC. That should be the first operation. So I see PC only here. I'm reading the contents of PC from here. So obviously I will start my instruction fetch cycle from here. So this will be the first operation. Reading PC, writing MAR, which is correct, right? I will read from the PC and I will write that value to MAR address because it is an address. Then after that I will read from the memory. I'll go to that memory location, let's say 2000. I'll go to that 2000 location and then I will read that value, and that value will be stored where? That value will be stored in instruction register. So after this I should have instruction register. Yes, instruction register is here. So I read from the memory and then I store it in the memory data register, or like not memory data register. I read from the memory, and then what happens is that value, right? That value from the memory, it is stored in the memory data register. That instruction is stored in the memory data register, and from the memory data register we connect it to the instruction register. Okay, that goes into the instruction register. So obviously second portion will be instruction register. Then what happens is, now I know the instruction. Now it will go to the control unit and it will decode the instruction. So what is the instruction actually? It is R1 plus R2. So what I will do? Then I will store the values of R1 and R2 in some temp1 and in this temp1, right? I store value of in this temp1, and one operand is can directly go into the ALU. So I will do temp. I will write something in temp1. Here I am writing something in temp1. Here I am writing something in temp1. Okay. So temp2. Which one shall I choose? I should choose temp1, right? Because after this what will happen? I will load the values on my temp1 and on the other ALU input that is directly connected. So yeah, R2 read. I will read the R2 and store it in temp1. So it is correct. Okay, just hold on. R2 read. Okay, no, this is not correct. Here, right? I am reading R1 and storing it in temp1, writing in temp1. So this will be the third phase where I will read from the R1 register and then store it in temp1. And the other input I can directly take. I don't need to store in a register. So then what I am doing is I am reading R2 and I am reading temp1. So R2 is directly being read. If R2 is directly being read, it is on the bus, right? So I will read here from the ALU, and temp1 is also directly being read. So R2 and temp1 both are being read, and then I am performing addition operation, which is correct. This R2 and temp1 both are being read, and I am performing addition operation. Then I am storing it in some temp2 register, known as accumulator, right? Writing back the result in temp2 register. This will be the fourth one, and this temp2 R0 write will be the final one, because finally I am storing it in R0. So this will be the fifth one. So which option will be correct here? So I can see first is this one. So 3 is first. First I am starting with 3. Then I am going to 5. Then I am going to 2. then I'm going to 1, and then I'm going to 4. So 3 5, okay, just hold on. Yeah, 3 5 2 1 4. Yeah, option C. So this was supposed to be option C. Option C will be correct. So it's not that difficult. You just have to identify, understand the data path, because I've explained you what exactly happens in data path, right? I've explained. So previously I was I think I have made a mistake here. Here, right? I have told that it directly goes to the instruction register, which is a bit incorrect. If I've told here it directly goes to the instruction register, this is incorrect. Here what happens is it goes to the, that is wrong on my behalf. It depends on architecture, but here generally it goes into the memory data register. Okay, so after it goes to the memory data register, from memory data register, then we store it in the IR. So it was my mistake on behalf. It first goes to memory data register, and from memory data register it goes to the IR. Okay, so let's like this is the solution, right? So there I just made a bit of mistake. So now let's start with the control unit. So what is a control unit? I explained it. Control unit is the brain. It's a component responsible for directing operation by generating control signals. It ensures coordination among all hardware components and enables execution of instruction. So it gives some control signals. It will say that whether I need to give out the data, whether a particular component needs to give out the data or take in the data. Okay, that is what control unit is. It is connected to everything. Okay, it is connected to everything. So what is the function of a control unit? It first of all generates control signals, sends specific signals to components like ALU, memory register to execute operation like data in, data out, perform addition, perform division. It will send the control signals. Synchronize operations, ensures all components work in univision by following the sequence dictated by the instruction cycle. So all like it has to synchronize everything, right? That I get the result at a correct timing. Okay, it's not like I have loaded some value in temp 1 10 cycles back, and now I am performing, after 10 cycles I am performing addition, so temp 1 can store some other value, so I have to synchronize everything. Then obviously it has the task of instruction decoding. What is that instruction? What does it mean? Is it telling me to perform addition operation? Is it telling me to perform division? Or is it telling me to store some data, load some data? That control unit will do. It understands that. So how do we do? Basically, how do we decode? So there is one name known as control variable. Control variable represents the name of the control signal. PC in, ALU out. PC in meaning it is the wire that is going to the in of the PC. So if this signal is 1, if PC in is 1, then PC will understand that it has to take input from the common bus. It will take input from the common bus. If PC in is 1, it means it will take input from the common bus. Okay, and if ALU out is 1, then that means I will ALU will load the data on the bus. If PC in is 1, then PC will load the data from the bus, and this is load the data to the bus. Okay, now what is a control word? A collection of control signals generated simultaneously by CU to perform a specific operation. So a control word is basically collection of control signals. So each bit will represent a particular control variable. Let's say the 0th bit here, right? 0th bit here represents PC in. Okay, I will just reduce the size. 0th bit here represents PC in. First bit here represents PC out. Second bit represents ALU in. Okay, and like that. Each one represents a control variable. And at once I simultaneously send this control signal to the whole bus, so that every component knows what it needs to do, whether it needs to perform write or read operation. So we send it, right? We directly send it on the bus. So this is a control word. And in each CPU cycle, a control word is generated. In every CPU cycle, what is CPU cycle? I will explain that. In every CPU cycle, new control word is generated. Okay, we can think of this like micro operations. micro operations. Previously I haven't explained to you exactly what a micro operation is. This is exactly what a micro operation is. So every time a new micro operation is being generated, that means a new control word is being generated. So control signal gives control word, like a control unit gives control signals that you have to perform a new task. So some data in, some data out will be turned on, right? So this is the actual meaning of micro operations. Okay. So I hope now the concept of micro operations has been cleared. So we will understand the control word more with an help of example. So here I have a control word, okay, and I have 14 components here, just the hypothetical system, and I'm performing the addition R2 plus R3 and storing it in R1. Okay, so I have this many bits here. Okay, so each bit has a designator. So this is a control variable, ALU in. If this particular bit is 1, that means ALU will take input, and if this particular this position is 1, that means ALU will give output. Okay, all of it depends on the control word. This is a control word. Okay, so to perform this, first I have a micro operation, that is fetch the instruction into IR. So it is a micro operation, right? So what we do, we take PC out and take memory in. So we make PC out signal 1 and we make the memory in is not this, right? AR, this AR in to be 1, correct? PC out third bit to be 1 and fourth bit to be 1. Third and fourth. Obviously there will be more micro operations. I'm just saying you the high level stuff. Okay, so this is the first one where I will just mark the points for my better understanding. This is ALU, this is PC, this is address register, this is instruction register or data register. Yeah, this instruction register. Okay, I forgot to write the data register. I hope you understand that data register is also there. Actually, first it goes to the data register, then it goes to the instruction register. Then I have the registers, right? R1, R2 and R3. Just a hypothetical system. Okay, somewhere I may have messed up. Yes, here I have messed up. Here R1 will be here, and this will be R2, and this will be R3. Okay, so currently what I am doing PC out to be 1. So this third position will be 1 and my AR will be 1. Everything else will be 0. Okay, everything else will be simply 0. Just giving you a hypothetical system, don't go into the theoretical here, just I'm trying to explain something. So this is a control word that is generated, that the control unit will send. This will be sent. This is a control word that will be sent on the common bus, and in the next step it has been loaded into the instruction register, right? In the next state it will be loaded into the instruction register. So now what will happen is this MAR PC will be 0 now. MAR out will be 1 and IR will be 1. IR in will be 1, right? It will take the input. And in the next, I'm just giving you a high level example. In the next cycle, what will happen? Now we will decode. Control unit has understood what is the instruction, so it has decoded. So it will take input from R1. This R1 will be R1 out will be 1. Okay, R1 out will be 1 and your ALU in will be 1, right? ALU in will be 1 and R2 will also be it will not be on one simultaneously. We will store it in some memory data register, then it will be loaded in the ALU. Okay, this will be 1, this will be 0 only, and your R2 also will be 1 in the next cycle. Okay, it will be stored in some temp register value. I'm not showing that. Okay, I hope you understand. I'm not showing the temp value register. It will be stored somewhere. So first I store the value of R1. Then what I can do, I can directly add, right? I can directly add. So ALU in will be 1. So opcode, all those things are there also. I'm just ignoring that. Okay, ALU has only one operation, that is add. Okay, ALU has only one operation, that is add. So next I will take R2 out will be 1 R1 will be 0. So now what it will do, it will perform the addition operation. It performs the addition operation. ALU has performed the addition operation, and next the result, this is 4, this will go, this time my R2 will be off and my R3 in will be on, right? So it will take the input and ALU out will be on. It will store the result on the R3. Okay, so this is how a control word generates and all the things. So of course there will be a opcode, ALU opcode, there will be opcode. So control word also will consist a opcode here. Okay, this will be the ALU opcode. There will be a provision for ALU opcode. Okay, just I am not showing it here, just to reduce complexity. I am not showing it. There will be opcode and there will be many other things. Many other things will be there. I am not showing it. I am not showing that. I am just trying to explain it. Okay, I'm just trying to explain one particular concept, that how does my control word gets generated. That is my only target to explain. How is my control word getting generated? So I hope you can ignore this ALU opcode for now. There will be a ALU opcode that I am ignoring for now. Okay. That you can ignore. Okay. So this is how a control word gets generated. Let's now understand a new term, that is CPU cycle. So what is a CPU cycle? It is the, like I've told right already, that control unit sends control word and control word represents micro instructions. So the time required to perform each micro instruction is known as the CPU cycle. So that is one cycle, right? One cycle. Now it may so happen, I'm rephrasing it. I'm rephrasing my definition. The time required for the CPU cycle is exactly the time required to perform the each micro instruction, each micro operation. Now CPU has a clock. If you have heard, like your CPU, right? Intel is CPU has 1 gigahertz clock, 2 gigahertz clock. I think you have heard, whenever you have gone to the market to buy processors, you have heard about this. What is this? This is unit of frequency. This is unit of frequency, and this is what actually? This is the clock frequency of that particular CPU. Clock frequency. Okay, this is the clock frequency of that particular CPU. Now, is this same as the CPU cycle time or CPU cycle rate? No, this is not the same, because to perform different micro operations, the CPU will take different time, but it will always be a multiple of that this CPU cycle. What do I mean by this? What does it mean? It means clock frequency. What is the unit of frequency? What is the definition of frequency? Frequency definition is cycles per second. And to perform each micro operation, right, it may be required that I have to take 2 cycles of a clock, 2 cycles of a clock, or 1 cycle of a clock. Let me give you an example. In a micro operation, I'm doing some read operation, right? So it will require me 2 cycles. In a micro operation, I will do write operation. It requires me 1 cycle. It is hard coded. It is the architecture. I will be recording 2 cycles to complete a read operation and only 1 cycle to complete the write operation. It is hard coded. Just assume. So if I assume this, now if in an instruction I have both read and write operation, what will be the average number of cycles that I needed to go through? Average, how will I compute average? 2 plus 1 divided by 2, that is 1.5 cycles. So each micro operation, I will write here, each micro operation can take different different number of cycles. Different number of cycles. Okay, each micro operation can take different number of cycles. So what I will do, I will take the average of those and I will compute the average cycles. This is the average cycles. Okay, so now if I have computed the average cycle, there is a term known as cycles per instruction. So this tells me how many cycles on average each micro operation will take. Okay, or like not micro operation exactly, how many cycles each micro instructions will take. This is cycles per instruction, micro instruction. Okay, cycles per instruction. So this is basically, if I combine a lot of micro operations, that gives me micro instructions. Okay, so this will be micro instructions. So this is micro instruction. Okay, so now if I want to compute what is the time taken by the CPU to perform n of these micro instructions, how will I compute that? So I know this, right? I know clock frequency. I know clock frequency. So can I compute how much time does each cycle take? Time taken by each cycle. So CPU cycle time will be what? Time taken by each cycle is basically 1 by clock frequency, right? 1 by clock rate. And if I know the average cycles per instruction, then if I multiply this, I know that this is 1 cycle time. Okay, and if I multiply this with the CPI, what I will get? I will get the instruction time, right? Instruction time. I will get the instruction time. So that will be CPI divided by clock rate. Now let's take, this is just a single instruction. So a single instruction can have many micro operations. So it is a micro instruction. Now if I have a program, so what time it will take me to calculate the whole, like to compile the whole program, right? Or to execute the whole program. It will be, if I have n instructions in that particular program, then it will be n times CPI. Okay, now the CPI, right? If a program, like I am just giving you a lot of thoughts. So first I will just give you an overview. First I have a program, right? Your normal C code. Okay, C code. In C code you have many instructions. Each line is instructions. Okay, instructions. Each line is an instruction. And in instructions, it is a micro operation, because C also, if I write here I equals to 5, it doesn't happen instantaneously. It may take more cycles, right? It may take more micro operations. So in atomic level, I have micro operations. Micro operations. Okay. So this is called, like sometimes this is also called micro instruction. Okay, sometimes this is also called micro instruction. So I am telling you, I like to perform each micro instruction, right? Each micro instruction can take different number of cycles. So there can be I1, I2, I3. So this, to perform this micro instruction, I may need CPI1, I may need CPI2 and CPI3. CPI2 and CPI3. So what will be the, I have to compute the average CPI actually. Because each instruction will take different number of cycles, because it will have many micro instructions. So I was wrong here. I don't directly calculate the average of cycles. Sorry, I was wrong here. That your micro operations will be same only. Micro operations is 1 cycle only. Okay, each micro operation is 1 cycle. So here it is 1 cycle only. I was wrong here. 1 cycle. But micro operations are made from instructions, and instructions can have 3 micro operations, 2 micro operations, or 5 micro operations. So micro operation is related with the clock frequency. Okay, and each instruction will have many micro operations, 5, 4, 6. So what I will do, instruction I1 has 5 macro operations, so its CPI will be 5 cycles. Instruction 2 has 3, instruction 3 has 2. So what will be the CPI average of this whole program? It will be 5 plus 3 plus 2 divided by 3, whatever this value comes out to be, 10 by 3. So average cycles per instruction is 3.33. Now what will be the total time? Total time, although it will not be exactly accurate, but it will be simply the program will contain n of this type of instruction, I equals to 5, then I plus plus n of this number of whatever the number of instructions I have. So I'll multiply n, I'll multiply with CPI average, and I will divide by the clock rate, correct? Because this is the total number of cycles. Although this is not exactly accurate, but that is how we calculate, and this is the time taken in each cycle. So this is what, like I have written the formula only. This top thing is the total number of cycles, and this bottom thing is what? This is the, not this bottom thing actually, this reciprocal, right? This 1 over something. If I have written 1 over here, 1 over this whole thing, okay, this is equals to what? This is the time taken to perform one micro operation. Okay, so if I have n instructions in the program, the execution time of n instructions will be n multiplied by this. Okay, total number of cycles in n instructions. Or what can I say about these cycles? This cycle I can talk also about micro operations, relate with micro operations. Okay, so what does execution time actually depend on? This is not exact formula, this is the average formula. So average is good enough approximation for us. So it is the total, like it depends on the total instructions, how many instructions I have, then average CPI, then also clock time and clock rate. So obviously the higher the clock rate, the execution time will be lower. So that's why we search for which processor has the highest clock rate. 2 gigahertz, we search for 5 gigahertz, 6 gigahertz. Why do we do that? Why do we look for bigger numbers? So this clock, as the clock rate is higher, the execution time of each instruction, T execution, will be lower. So that is why we look for it. So obviously there are few trade-offs as well that we will see. Okay, that we will not understand here. That those are physical trade-offs. Those we will not discuss here. Okay, so here I've given you one example of average CPI. Already have computed it. So how do we calculate the average CPI? Actually, we do not do that simple arithmetic average. We do weighted average. There I have just shown you an example. So how do we do weighted average? So it is the instruction count of type into CPI of type. So if I have ALU and ALU has 400, like ALU has to perform 400 types of instruction, its CPI will be 1. Memory will have 300 instruction, its CPI is 4. Branch, if I have to perform branch, there are 200 branch type instructions in a particular program, and its CPI is 2. So I will multiply individually. So like once we'll solve a question, I will understand. So how to perform the average here? What we do, like there is a program. Okay, there is a program. And that program has 400 ALU instructions. Compiler has calculated it has 400 ALU instructions, and it has been given that each ALU instruction takes CPI, cycles per instruction, as 1. This many cycles. We require only 1 cycle. And for 300 memory instructions I have, like either read or write the data from the memory, my CPI for that particular thing is 4, right? You can observe it is a very costly task. It takes very high number of times, the cycle time for the memory read and write. And I have 300 branch type instruction, and what is it? Its CPI is cycles per instruction is 2. Branching takes 2. So what will be the average? Basically? So CPI average, okay, CPI average will be the sum of the weighted average, right, of each CPI. It will be like, this is the formula. I don't want to tell you the formula. I want to write directly. So I have 400 ALU instructions times its own CPI average. That is 1. So total 400 ALU instructions will take how many cycles? 400. If I have 300 memory instruction, and if each memory instruction takes 4 cycles, to total 300 memory instructions will take how many cycles? 300 into 4. And if I have 300 branch type instructions, and if I have and each branch type instruction takes 2, this is not 300, so this is 200. And if I have 200 branch type instructions and each branch type instruction takes 2 cycles, so it will be 200. Total number of cycles will be 202 divided by the total number of instructions. How many total number of instructions I have? 400 plus 300 plus 200. So this will be 800 plus 1200, that is 2000. 2400 divided by 900. Okay, so if I just calculate it, I don't have the phone, just hold on, I will just quickly calculate it. Two 400 divided by 900, so it is 2.66. okay, I've written this correctly, so it is, yeah, each takes 4, yeah, it will be 2.67. So I hope you understood how to compute the CPI average. Now as I have got the CPI average, what will be the total time taken to execute this particular program? Total time taken to execute the program will simply be equals to CPI average by total number of instructions, whatever number of instructions I have, divided by the clock rate. Because this is how we compute the CPI average. Once we do a few examples, we'll understand this. Okay, now there is another term known as MIPS. What does MIPS means? Means millions of instruction per second. How many million of instruction that can the CPU perform per second? Because obviously the CPU can perform a lot of instructions in a single second, right? So it's a better a better stat or a better metric. This is a better metric, right, than normal just instruction per second, because it will be a lot. Every time we have to write 10 into 10 raised to power 10 or something, it will be huge. So this is a better metric. Just this is a better metric, nothing else. Better metric. Now, if it is how many millions of instructions per second, that means the number of instructions executed in millions divided by total time. That will give me millions of instructions executed per second. So this numerator should be in millions. So it should be number of instruction executed. This is not in millions. I will divide this by 10 raised to power 6. That will give me million, right? Because a million is 10 raised to power 6. So I will divide it by I will divide my number of instructions executed by 10 raised to power 6. That will give me million. The unit will be in million, right? This unit will be million. Okay. So how many number of instructions? I have n. Let's assume n number of instructions. And what is the total time? Total time is, I have already derived, right? Total time is equal to CPI average into n divided by clock rate. CPI average, okay, this is a bit wrong. Yeah, into cycle time. Yeah, so, n into CPI average, 1 by clock rate, right? 1 by clock rate also is known as, or sometimes what do we call 1 by clock rate? 1 by clock rate is also called as the cycle time. Correct? I think I have mentioned this in the previous few slides. 1 by clock rate means how many cycle, what is the period of each cycle. That is 1 by clock rate. Basically 1 by f equals to time period. 1 by frequency is time period. That's it, right? So I can write it like this, I can write it like this, anyhow. Just you can manipulate the formula. So if some data has been given, if you have to find out MIPS, can you do it? Yes, you can, right? You just know the basic thing. Just remember this basic thing, then you can derive the other things. Okay, that is the most important point. So these are few key points that CPI and clock time directly impact execution time. Basically, the lower the period, right, clock period, the higher the CPU will perform. That's why we see Intel has 3 GHz processor. Your new phone, right? New phone has Snapdragon Elite processor. It has higher clock speed. Obviously, it has its drawback. Higher the clock speed, the more heat it will generate, and the more heat it generates, the performance can go down. Okay, it can degrade the performance. So there is a like drawback to it. So that is for other discussion. Okay, so higher MIPS implies better CPU performance, but may not always accurately reflect the CPU efficiency for certain workloads. Efficiency may go down. Average CPI will change depending on the type of the processor, because each processor can have different clock rate, because CPI is dependent on many things. So average CPI also will change upon processor to processor. So this is basically clock. Okay, I hope you know about clock. If you don't know, this is a clock cycle. It just toggles from 1 to 0, and this one whole cycle, for a period when it is 1 and for a half a period it is 0, that is known as a clock cycle, whole time period. Okay, so let's now do few questions from there, like this concept will be cleared better. Consider two processes P1 and P2 executing the same instruction set. So I am executing the same instruction. Okay, so yeah, that is one thing. Assume that under identical conditions for same input, a program running on P2 processor takes 25% less time but incurs 20% more CPI. So if the same program is running on processor P2, it is taking 25% less time. So TP2 is 25% lower than TP1. This is first equation. And what is the other equation? Other equation is but incurs 20% more CPI clock cycle per instruction as compared to program running on P2. So it depends on processor to processor. It is telling me the CPI of P2 is 20% more. So it will be 1.2 of CPI of P1. Now what are they asking me? If the clock frequency of P1 is 1 GHz, so frequency of P1 is 1 GHz. What are they asking? They are asking me the clock frequency, then the clock frequency of P2. What will be the clock frequency of P2? So basic things we know. Even if you tend to forget the results, right? One thing you know, how much time will processor P1 take? What will be the time? How much time does a processor take to completely execute instruction? Total number of instructions. How many total number of instructions? That is n. Let's say I have n instructions and I will multiply this by CPI average. Okay, CPI of that particular processor. Let me name this as TP, divided by the frequency or the clock rate. Okay, or multiplied by the clock period, whichever one you are suitable to remember. So I will write this FP. Okay, so this gives me the total time taken by a processor. So if I just simply take the ratio, right, TP1, TP2, I will get my result, because all these values, like n is same, right? N is same because it is telling me it is executing the same instruction. So number of instructions will be same, but each of them take different times for executing different instructions. So TP1 divided by TP2 will be equals to n will get cancelled simply. So it will be CPI P1 divided by CPI P2 into FP1 divided by FP2. So I know, right? I know the ratio between TP1 and TP2. What is the ratio? It is 0.175. So I need FP1 actually. I have been given FP1. I need FP2. So FP2 is here. So what I will do is I'll move this FP2 on the left hand side. FP2, let me release. FP2 will be equals to TP2 by TP1. TP2 by TP1 is simply 0.75. TP2 by TP1 is 0.75 into CP1 by CP2. CP1 by CP2. CP1 by CP2 is 1.2. Sorry, not 1.2. CP1 by CP2 is uh, 1 by 1 by 1.2, right? So this is what my CPU1 by CPU2 is, correct? Okay, I think I have made a mistake. Yeah, I have made a mistake. Yeah, because FP1 will be here, right? This will be FP2 by FP1. That is my minor mistake. So actually this will be just swapped. Okay, so it will be 1 by 0.75 into 1.2, and what is FP1? FP1 is 1 gigahertz, correct? So this will become, I can quickly calculate this will become simply this is actually 3 by 4 into 1.2, so this is 0.4, so this will be 1.6 gigahertz. So they have asked, just check the units, what have they asked? They have asked in gigahertz only, so your answer will be 1.6 gigahertz will be the clock frequency of the second processor. So let's do the next question. So next question is again the part 2 of a question that I solved previously. So like all these instructions are there and clock cycles are provided for various operations, and they have asked total number of clock cycles required to execute the whole program. Okay, register to and from memory transfer is 3 clock cycles, add with both operands is 1 clock cycle, and instruction fetch and decode takes 2 clock cycles. Now they like here they missed a point. They should have also mentioned that to instruction fetch and decode 2 clock cycles, this is per word. Okay, they missed this. They should have been given, it should be per word. Instruction fetch and decode per word is 2 clock cycles. If the instruction size is 2 words, then it will be 4 clock cycles. Okay, as the instruction size is higher, it will take more time for me to decode and obviously fetch, right? Because fetch will take more time, because I have to load 2 things in the memory from the system bus, right? Twice I will wait. I have given an analogy as well. If my bus is 8 bits and the register is 16 bits, I will have to do 2 times the data transfer. So they are asking me the total number of clock cycles required to execute the program. So simply for this first instruction, how many clock cycles I will require? To fetch and decode the instruction, I will require, like each word requires 2 clock cycles, and I have 2 words, so it will require 2 times 2, 4 clock cycles. So 2 times 2, 4 clock cycles, plus this instruction itself takes some time, right? That is, it is a move instruction, so it is a register to and from memory transfer, so it will take 3 clock cycles plus 3. Okay, then for this particular instruction, it is also a move instruction, but it is a register instruction, right? Move, register, move, so it only takes 1 clock cycle. Okay, 1 clock cycle, so not 1, so 1 into 2, because each instruction takes 2 clock cycles to fetch and decode, plus its own clock cycle, that is, it is a register transfer, right? It is 3 clock cycle plus 3. Okay, so it will be plus 3. Then I have this add R2 R3. Add R2 R3 means R2 plus R3, R2 plus R3. So I'm adding, okay, I'm doing just this add operation. So to do this add operation, it will take me 1 clock cycle. Okay, they have told me, right, add with both operands in register, so it will not take me any extra clock cycle to load it somewhere. Okay, so 1 plus to fetch the instruction is 1 times 2, right? Because it is a 1 word instruction, so 1 times 2 plus 1. Then next is this move 6000 R2. Move 6000 R2, so I am moving the contents of R2 to 6000. So obviously again the instruction size is 2 words, so it will be 2 times 2 for the fetch and decode, plus this register transfer takes 3 clock cycle, 3, and hold, right? Hold, remember this, that for hold we only will need to get the fetch, right? We only will take some time to fetch the result. They have not mentioned how many clock cycles I will require for hold to complete, so I will assume 0. So assume for this, right? For this, assume 0. Okay, obviously I have to fetch the instruction, that I have to do, but after fetching, how many clock cycles will be required for this operation, they have not mentioned, so I will assume 0. So this is 0. So to fetch it, it is a 1 word instruction, so it will be 2 times 1 plus 0. So overall what result I will get? This is 4 7, this is 5, this is 3, this is 4 7, this is 2. So 7 7 14, 14 5 19, 22 24. So your answer will be total of 24 clock cycles. Option B will be correct here. Okay, so like I know there are few ambiguity points, so don't stress about this. Currently I hope gate will provide more information regarding what each instruction takes, how much clock cycle. But if they haven't, few things you should know. This is the thing that you should know. Okay, don't take too much stress. Few things you should know. Just by solving questions you will get to know what things you should know and write in your short notes. Okay, so we have learned all this. We have learned about CPI and all those things. Now we will learn a few types of control unit. So first one, we have already learned about it. Okay, indirectly it is called as hardwired control unit. Hardware control unit is what? It is a control logic is implemented using gates, flip-flops, decoders and other digital circuits. Working based on the instruction opcode. CPU generates specific control signals using combination logic. So what happens is, the designer, before the CPU has been designed, right, he decides exactly in the hardware what does each instruction means. Okay, so how to execute a particular program, the designer will decide it, like a specific task like addition, division and all those things. So here what happens is, we have a clock generator. Clock generator is there for like obvious reasons. At each clock some control signal will be sent. Okay, and what will happen, that the designer will decide before manufacture what type of control signals need to be sent for particular instructions. Okay, particular instructions. Okay, so one important portion is this, it is hardwired. So it is a hardware thing, we cannot change it. Anyways, we cannot change control unit, but there are few modality which we will learn in the next lecture about a different type of control unit. Here everything is present in hardware, so we actually implement hardware logic. We don't implement software logic. In the next lecture we learn we will actually implement software logic. What do we mean by hardware logic? Just we make using combination logic, boolean gates and all those things, right? Logic gates. Okay, so what happens is, here we generate a control word. According to each components. We'll see an example there, will understand. Now this is very good. Okay, so this has very good advantage as it is faster due to direct hardware implementation. We directly implement hardware. Okay, it is implemented in the hardware, so it is very faster, can be optimized for specific task. But this has some disadvantages, that's why we don't use it. What is the disadvantage? Difficult to modify once or update once designed. So as we implement it in hardware, it is implemented in the hardware, right? So we cannot modify it. Later on, if you want to modify that, the add operation, the control signal should be something else, I cannot modify it. It is required actually, sometimes modification is required, so I cannot do it. Okay, as it is a hardware thing. Complex wiring makes debugging and reconfiguration challenging. So if we have lower number of instructions, then we will require less number of hardware components, right? I told you previously, there was one example, if I have 36 components, how many wires I will require, I told you previously, right? But control unit will require all the wires. If it is a hardware, control unit will require so many wires and so many logic decoding circuits. So if you have so many elements, then if it is hardware implemented, right, it will be very, very difficult to make that logic decoding circuit, because decoding circuit is hardwired. Once we'll see the next control unit in the next lecture, there we'll understand why am I telling that it is challenging. But this one I hope you understand why it is difficult to modify. It is hard coded, right? It is hardware. So changing hardware is very difficult. How will you go inside the CPU? CPU is so tiny, right? How will you go inside the CPU and change the control unit? No, you cannot. Okay, so that's why. So basically what happens is, generally we have a lookup table. In hardware configuration we have a lookup table, and what happens is, our control unit, right, will send a control signal. how it will send? It will send a control word, right? It will send a control word. Okay, it will send a control word. And let's say, like, I'm just giving you example that this is control signal 0 or like or something, control signal 0, control signal 1, okay, control signal 2, and so on, correct? And for each time cycle, right, each clock cycle, for particular instructions, it is written in the hardware itself that for I1 instruction, let's say this I1 instruction is add. This instruction is add. For I1, it is defined. We defined it that if I am doing some addition operation, the control signal of this particular bit will go high for in the first clock cycle. Then in the next clock cycle, control signal CS5 will go high, CS6 will go high. Okay, we define it for I1 instruction. For I2, let's say subtraction, or let's say some move instruction, right? Load instruction. Fourth bit of the clock signal will go high. That means it will, like, fourth wire of the clock signal CU will go high. Okay, so it is, all of this is defined, and we design a lookup table. So obviously we know, right, we have this table, and from this we can like design a logic, Boolean algebra logic, and from there we can design, implement it in GATS and AND gates, NOT gates, all those things. We can design any logic, right? So with the help of this, first we have a lookup table. First I define, okay, for add operation, control signal 1 bit will go high, and control signal 7th bit will go high. Okay, so I will make that bit high, 1 1. And for subtract operation, 0 signal will go high and 5th signal will go high. So I make a lookup table, then I implement it using Boolean algebra. So if you have studied digital electronics, you will know we have a table, and from there we can implement any expression, Boolean expression, right? And from there we can implement it with the help of gates. So exactly that is how we implement a hardware control unit lookup table. Okay, so this helps. So first the programmer or a designer first makes this lookup table, then he makes a logic. Okay, Boolean expression helps to make the Boolean expression and then that Boolean expression is used to implement using logic gates. I don't have space. That is the most unfortunate thing. Using logic gates. Using logic gates. Okay, so I hope you know how we implement logic gates, all those things. I am not going into that. So let's do a few questions on this. So this hardwired logic thing, right, hardwired control unit, will get more clearer. So here we have a hardwired CPU. I will just zoom in a bit. Hardwired CPU uses 10 control signals, S1 to S10. So I have 10 control signals. So it is not mandatory that I will have 10 control signals only. I can have many more, right? Now, in various time steps from T1 to T5 to implement 4 instructions, I1 to I4 as shown. So I will implement 4 instructions. I have 4 instructions only. Okay. And in first clock period, it has been defined by the designer that signal S1, S3 and S5 will be high. It has been designed for a particular instruction. You can take this as addition, this as move, this as load, anything you want. Okay. So these signals will be high in the first clock period for I1. For I1 in T2 second clock period, these signals will be high. In the third period, these signals will be high, and so on. And for I2, similar, right? But other signals will be high. So it has been designed. Now, what are they telling me? They are telling me which of the following pairs of expressions represent the circuit for generating control signals S5 and S10. Okay. So this is telling me this is just the Boolean expression. That's it. So what are they asking? They are asking for me to design write down the logic, Boolean logic for signal S5 and S10. It is just a digital electronics question. It is not even a computer organization architecture. Okay. So this is just a digital question. Okay. Digital Boolean algebra. Basically, I have to write the Boolean expression. Okay. I have got a table and I have to write the Boolean expression. Can you do it? I will do this first one. And next next one we don't have any question, but I will do this. But mostly questions for hardware logic, right, will come like this. So what you have to do here, I have to see where does my S5 come. So it's very simple. It's a very simple thing. Okay. So I will write S5 will be equals to what? Here, if I observe that I have S5 in instruction I1 for the T1 clock period. For I2, I have S5. For I3, I have S5. For I4, I have S5. So how will I write it? So we write it like this, that it is present in I1, as well as like here how they have written T1 times something, then T3 times I2. Like I1, I3 are in OR, and it is multiplied with T4. So what I will do, I will see each clock period. I will see like this vertical, okay, as they have provided me the expression. If they would have provided me like it is I1 multiplied by T1 or T2, so I would have gone horizontal. Okay, so I will explain that as well. So I will explain, just hold on a second now. So here in the first clock period I am observing S5 is on for everything. So it is basically for the first clock period I1 or I2 or I3 or I4, it is always on. It doesn't matter. In the first clock period it will be always on. If I am at the, so what does this statement say? That I am ORing everything. I am ORing everything means I am ORing all the instructions. That means it is 1. So it becomes simply 1. It becomes simply 1. So if I am at the first clock period, then I am 100% sure that S5 signal will be on, because that's how the designer has made it. Okay, S5 signal is always on for the clock period 1. Okay, so basically it will be T1. Now then I will do OR. Now if I am at the second clock period, clock period, where is my S5 on? Is it on in the first instruction? No. Is it on in the second instruction? No. Is it on in the third instruction? No. Is it on in the fourth? No. So it is 0 simply, because it is never on. Or in the third clock period, I will go and see it's on in the second and the fourth. So I will only choose either I2 or 4. That's why a plus sign, because it is OR. Or if I am at the fourth clock period, then when is my S5 on? S5 is never on. So it will be 0. So from this particular thing we get our S5 logic. Okay, just hold on. We get our S5 logic as what? S5 logic is T1 or T3 or I2 or I4. And what about S? What are they asking? What else are they asking? They are asking S10. S10 logic. Now again I will apply the same thing, right? Same thing. If I apply the same thing, S10, if I see S10 is present for T1 period. S10 is never present, so it will be 0 times T1. Or for other periods here, right, S10 is present in the second and third instruction for T2, so it will be second or third for T2. Or in the third clock period, S10 is present in the last, right, only in the instruction I4, so it will be I4 times T3 plus in the in the fourth clock period, S10 is present in instruction 1 and 3, I1 or I3, T4. Okay, then in the time period 5, S10 is present in instruction 2 and instruction 4, so it is present in 2 or 4, I2 or I4. Okay, so this is my T5. So what I can write is S10 will be equals to what? S10 will be equals to I2 or I3 T2 or I4 T3. Okay, I can directly write it, right? This is the result only because it is 0. So I2, so I'll check with option like S5 first, T1, T3. So T1 is here, T3 is with I2 and I4. No, this is cancelled, right? This is wrong. This is wrong. Here S5 is T1 and I2, I4, T3. Yeah, T1, I2, I4, T3. So this can be correct. I will mark this here. This can be correct. And here as well, this is also same, right? This also can be correct. Okay, so first I will check the smaller one, then I will go to the larger one. This also can be correct. Okay, so I have to check all three. Obviously, S10 is I1, I3 with T4. I1, I3 with T4 is correct, but it is missing T2, right? T2 is there, T3 is there. So it is missing T2 and T3. So this is gone. Okay, here what have they given me? They have given me I1, I2, I3 with T2. Sorry, not I1, I2, I3, I4 with T2. I2, I3, I4 is not there, right? With T2. I4 is not there. So again, this also has been eliminated. So only option D will be correct. Here if I see I2, I3 with T2, yes, correct. I4 with T3, yes, here I4 with T3, correct. Then I1, I3 with T4, I1, I3 with T4, again correct. I2, I4, I2, I4 with T5, I2, I4 with T5, again correct. So this is correct. Now, they could have like written this expression in different manner as well. Generally, they write this expression like this only. What they could have done, they could have written it in terms of I. This time they have written it in terms of T. In terms of I, can you write it? So in terms of I, how I will write? So I can copy this particular thing. Okay, copy this particular thing. And if I want to write in terms of I, right? So what you could have done is simply, I'll zoom this a bit. That will be easier for us. So here, if I want to write in terms of I, right, in terms of instruction was, so I will go horizontally now. So horizontally, why is S1 present? S1, no, not S1, sorry, S5. S5 is present here and only here. So it will be I1 will be here and it is only T1. Okay, nothing else. This is my S5. Or in I2, where is S5 present? S5 is present in T1 and in T3. So it will be T1 or T3. This will be I2. Now in I3 is S5 present? Yes, I3 S5 is present, correct. So it will be T1 and S5 is not present anywhere else. So it will be T1 into I3 or then if I go to fourth instruction, it is present in T1. Is it present somewhere else? Yes, it is present in T3 as well. So it will be T1 or T3. So this is how you write instruction wise. You can repeat it for the second like instruction as well. Second signal as well. That is S10. Now if we check I1, like T1 is here as well, T1 is here as well, T1 is here as well, T1 is here as well. So T1 is common everywhere. So T1 will become only T1 and all the other expression will be same. You can cross verify. Okay. So yeah, that's it basically for this lecture. I hope you enjoyed the control unit chapter. I tried to give a lot of analogies. There is still one lecture left for control unit. So in the next lecture, we'll learn about microprogrammed control unit. So it will be a better version of this hardwired control unit. Thank you for watching and I will see you in the next lecture. Until then, happy learning. Hey everyone and welcome back to my channel. So today we'll start the second part of this lecture 4, that is on control units. So up until now we have learned what does a control unit do, what is a control signal, what is a control word, and we have learned about one type of control unit, that is hardwired control unit. So today we learn about microprogram control unit. We'll do for a few questions on that. Also we'll understand the difference between horizontal and vertical microprogramming, which is also a type of microprogrammed control unit, the differences, and we learn about RISC and CISC CPU design, just a few theoretical points. Okay, so what is microprogrammed control unit? So microprogram, as the name suggests, it is programmed within the CU, within the CPU. Okay, here what happens in our control unit itself, we have a memory known as control memory. We have a memory known as control memory. Control memory. Okay. and in that memory we have few things stored. What is it? Is it stored? It is stored we stored a lookup table. Lookup table. Now what does lookup table means? Sometimes in short form we call it LUT. LUT. What does it mean is that what does that instruction means that will be mapped to produce a control signal. Okay, what do I mean by it? Let's take example. I have an instruction 10. This is the opcode. Okay, this is the instruction opcode. Now if this is 10, right, what it will do is there is a lookup table. There will be a lookup table. I haven't drawn it. There will be some lookup table in the control memory. Okay, and somewhere the somewhere the decoding, like the control signals, like what signals that does the control unit needs to send to all the elements will be present of this 10, right? Somewhere here some control signal 10, somewhere it will be present in LUT. Okay, so what we'll do, we'll just directly go here and then send this instruction in the control unit. So control unit understands, okay, I need to, for this 10 instruction, for let's say add instruction, the control word is 00100100, something like that. Okay, it will be present in the LUT. So it will directly take this from the lookup table. Previously we didn't have any lookup table. What we had hardware. In hardware control unit we had hardware logic. For each instruction we had a hardware logic, if you remember. So previously in hardware control unit we implemented the same. We implemented the same using hardware. Okay, I am running out of space actually. Okay, what we can do is we can maybe take this more on the down. Same. Using hardware, but now it is present on memory. So obviously there is a drawback. We are using memory, we are using storage, so it will have some drawback. Also we need memory access here. We're accessing the memory, right? Hardware, it was instant. As soon as the instruction got, there was decoding logic ready, and in hardware it instantly decoded everything, right? It was all hardware present. Okay, all the signals were hardware present, but we have to do memory access, so that will take time. That will slow this microprogram control unit. Also we have to store it somewhere, right? So that will also cost us storage. So obviously hardware also we have to make the hardware, so that is a disadvantage. Also we can change this. We can always change this memory if we want. Okay, like not everyone can change this. It is restricted to the designer or some people. Not everyone can change it, but yes, it is changeable. It's not like it is done in the hardware and I cannot change it ever. Okay, so that is what is written here. A microprogram control unit uses micro instructions stored in control memory to generate control signals. So what does each micro instruction or each micro operation means? Okay, it will what is micro instruction? Actually, micro instruction is a collection of micro operations. That's it. So what does each micro instructions mean? So add, right? If I write add R1 plus R2, it is a micro instruction. Just hold on a second. It is a micro instruction. Okay, where there will be many micro operations. First I will load the instruction from the instruction register, then I will load the values, then I will add the values. So there are many micro operations involved. So I have already explained this previously as well, that micro instruction is what? It is a collection of micro operation. Okay, so there are multiple micro operations. Now obviously the CPU only performs micro operations, right? So control signal will break it down from micro instruction to micro operation, that will be defined here in the LUT. We'll see that as well, how it does that. Okay, sorry, just hold on. So yeah, stored in my control memory to generate control signals required for executing instructions. It functions like a lookup table where each instruction has associated microprogram consisting of control words. So each micro instruction will have a control word, okay, in the LUT, and we'll take the control word from the LUT itself. So here I have given you a block diagram. So if I see, I have this instruction code that goes into some next address generator sequencer. We'll understand this as well, what is sequencer. Then it goes to control address register. So the control address register actually maps to the where the control signal for this particular instruction is present, where the control word is exactly present. So control address register, it maps the control word. Next we go to the control memory. Using the address, I know where that particular control word is present. I will go to the control memory. So here in control memory, all the control words will be present, which generates the control signal, right? Then from this control word gets copied to control data register, and then we have a decoding circuit to which signal to turn on and off. That decoding circuit we have, and finally our control signal gets generated. Okay, so this is the sequence or flow of a microprogram control word. So now we will understand this block. What is next address generator, also known as control word sequencer? So control word sequencing is a key aspect of microprogrammed control unit, determining the sequence of the micro instruction control words that are fetched and executed to carry out an operation. So I told you, right, it contains micro instructions. Okay, so in micro instructions, like control word is what? Each micro operation. Control word is what? Each micro operation. So a micro instruction will have a collection of micro operations. So this is a instruction, micro instruction I1. Let's say I1 is add R1 R2. Okay, so it will contain many micro operations. So we have many micro operations here, right? But obviously the control unit has to know, is this the start of the micro instruction and is this the end of the micro instruction? So where is the start of the micro instruction and where is the end of the micro instruction? That the control unit must know. Who tells the control unit? Control word sequencing. So here if I see, here I have a next address generator, right? It understands whether my whole micro instruction has finished, because all these individually are micro operations. So it will understand that where is my next micro instruction. Okay, so this I1 instruction, we start from here. Okay, then it is just like PC. Where is my next micro instruction in this sequential here, right? Sometimes what will happen is you will have branching, you will have looping. Okay, if you have branching, that means you will branch to some other micro instruction. So that branching is also taken care by control word sequencing. Okay, I hope you know what is branching, what is looping, all these things you know. Okay, so branching means I'm going to some other micro instruction. I will not complete this micro instruction. I will go to some other micro instruction. Okay, so the sequencing process defines the flow of control through the microprogram and ensures that the control unit correctly generates the signal required to execute the instruction. So the instruction can have branching, it can have looping, anything. Sequencer is a hardware component that generates the address of the next micro instruction based on the current control state. This should be not micro instruction, this should be actually micro operation. The words are very important. If somehow we mess up micro instruction operation, the meanings will change. The sequencer determines, by following a predetermined sequence by branching based on the conditions. So there will be some predefined sequence. All this will be defined in the LUT. All this will be defined, right? That's why we have a separate hardware unit to understand, okay, whether we need to branch or we don't need to branch, all these things. Now, what is, like, let me give you an analogy of control word sequencing. What is control word sequencing? Imagine a recipe book where each recipe control word tells you exactly what to do with the signal. So those are micro operations, right? You have to make chicken kofta. So first you have to buy the chicken, obviously get this much 500 grams of chicken, then some amount of soya sauce or some amount of vinegar. I don't know, okay, what recipe you need, but I'm just giving you an example. Okay, ingredients you will need. So you got all those things, then you have to like boil the chicken for 30-10 minutes. Okay, it all depends. Now the sequence actually is given in the recipe book. All of it is written in the recipe book. So recipe book is our LOT. Recipe book is our LOT from where you take all the information. But the sequencer is like a chef deciding whether to move to the next step or jump to a specific part. Now you have, like, you are very rich and you have a personal chef with you, and the chef tells you whether you need to follow this particular like put soya sauce or not, because chef has so many years of experience. He might have his own recipe, right? So he knows exactly, if I put soya sauce here, will it be best or not? Because obviously recipe book is available to everyone, but can everyone make that good amount, like good food, right? Good tasting food? No, right? Everyone cannot make that. We have special people like our moms and obviously other people. So obviously you need someone. So chef is that person who tells you whether you need to do, like, what sequence you need to follow. Chef will tell you sequence, whether you need to put the soya sauce or you don't need to put the soya sauce. Okay. It tells deciding whether to move to the next step or jump to a specific part of the recipe based on the dish being prepared. He has experience. He can have his own. He has made his own dish, right? So it depends on his own taste. Just like sequencer calls. So it depends whether in the instruction have a branching, or the user wants a branching, or user doesn't want branching. User wants loop. Looping means multiple times repeating is the same instructions. It depends on the user. Okay, this time I hope you understood this point. So there can be like many types of sequencing. One is sequential sequencing. This means the next micro instruction is fetched from the next address in the memory. Okay, not micro instructions, micro operation. This will be micro operation. I think this also, and this also will be micro operation. Yeah, now it is fine. Don't get confused sometimes with micro operation and micro instruction. Okay, the smallest possible thing, that is micro operation, and the collection of those micro operations is just a micro instruction. Sometimes they are used interchangeably. Okay, so don't get scared by that terminology. The next micro operation is fetched from the next address. It is sequential. Okay, simplest form of sequencing. Conditional branching. In some cases the sequencer branches to different micro instructions. So it is true, it will branch to different micro instruction. Why? Because if I am, let's say, in I1, okay, and there is some condition that check if the result is 0 or not. If it is 0, branch to instruction I3. Okay, so it will go and branch to instruction I3. So that is the conditional branching. Then looping. For certain instructions or operations, a loop may be employed where the sequencer repeatedly fetches the same set of micro operation until so this will actually might be micro instruction only. The same set of micro until condition is met. Okay, so what we do is the same set of micro operation. This is correct, same set of micro operation. So we check if I, like, what is this? This is, we are branching, right? If result, right, accumulator value is not equals to 0, then branch to I4 instruction in the control memory. Now here, if I will do like I less than 100, and then I will increment I plus plus, and I will say if this condition is true, right, I have started from location I1, so I will again go to branch, go to I1 again. If this condition is true, if this condition is met, I will again go to I1. Okay, so it will keep on repeating itself 100 times if I is starting from 0. Just simple loop. Okay, so those are few control word sequencing. Okay, and your control memory will contain what? Your control memory will contain two things. One is the control word. Okay, another one is the next address of the instruction. So remember, this is the memory present in the hardware, in the control unit. I have already told you this will be present. Control memory will be present. Memory present in control unit itself. Okay, that's why the access is faster, but still it will take some time for us to access a memory, right? It contains the control word and the next address of the instruction. So these two things are present. Okay, so it's, and remember, everyone cannot access it. I have already mentioned everyone cannot access it. CPU or CPU cannot access it always. So here CPU can't access. Okay, it is not like ROM or RAM. Okay, not ROM or RAM. CPU doesn't have access to it. Control word is the leader of everything. So you don't have access to your manager's details, right? Obviously you don't. So that is the thing. So yeah, I hope you understood each control address in a control word in a control memory contains the control word obviously and the next address instruction. What is control word? You already know that. Okay, so let's do a few questions. From there our concepts will be more and more clear. So this is the first question. Consider a CPU with the following characteristics. We have 100 control signal bits. Okay, so I have 100 control signal bits. Okay, so then each instruction requires 50 micro operation and CPU supports 12 distinct instructions. So each instruction supports 50 micro operation and we have 12 distinct instructions. So how many micro operations I have? So this is mu, right? Don't get confused by m and mu. This is mu. How many micro operations I will have? 12 into 50. This many amount of micro operations I will have. So how many bits will I need to define this many amount of micro operations? This is 600, right? So how many I will require? I will require log upper bound log of 600, that is 10 bits. Then a 4:1 mux is used for instruction decoding. So we have a 4:1 mux, right? And if I have a 4:1 mux, how many bits will I have? I will have 4 bits. Now why do I need a 4:1 mux? Okay, for mux select lines, it will have a 4:1 mux. So 4 bits. Why will I have 4 bits? Why will I require mux here, right? If you see, I have to convert, like here I have a decoding circuit. I have to convert the bits into signals. Okay, bits into signals. If you remember, every PC has its in and out. The instruction register has its in and out. Each of it has its signal, right? So which signal to turn on and turn off, mux will do that. Control word sends that, okay, but mux actually finally converts it. So we will require a mux. Okay, so here decoding circuit, mux and all those things will be present. In hardware, mux is anyways present. In microprogram also mux will be present just to send those signals, right? Mux to connect everything. So how many bits, select line bits I will require, because it is a 4:1 mux, right? And if you have studied digital electronics, you will know I need 2 select lines. So here I was wrong actually. Okay, I messed up here. I hope you have studied digital electronics. If I have a mux, right? If I have a 4:1 mux, this is a 4:1 mux, correct? What does 4:1 mux does? It takes 4 inputs here, okay, and gives 1 output. And to select any of these lines, right, I will require a logic. I will require 2 select lines, S1, S0. Okay, what happens is the control word comes here. Okay, now it distributes the signal, right? So first bit will be for the first signal, the second bit will be for the second signal, and so on. So obviously I need a mux. Okay, so that is the decoding logic basically. So this S0, S1 will be the select lines. These bits will be required in the control word, because this also will be provided by the control signal only. So which lines to select, okay, which signals to turn on basically. Okay, that will be decided by the control logic. So that should be also present in the control word. Okay, so for mux select I will require 2 bits. How am I calculating 2 bits? It is a 4:1 mux, so it will be 2 raised to power 2, right? 2 raised to power 2, that is I will require 2 bits to define this. If it was a 16:1 mux, what was the formula if you remember? It is 2 raised to power 4. So I will require 4 bits to define the select line. If it was 8, I will require 3 bits. So simple as, right? So here I will require 2 bits mux select. So what are they asking? First, the question is the total number of micro operations in the control memory. We have already calculated that. Like while reading the question, the total number of micro operations will be 600, because I have 12 micro instructions, and I have told you micro, I have like those instructions are combination of like are collection of micro operations. So each micro instruction has 50 micro operations. So total 15 to 12, 600 micro operations. So total how many micro operations? I will have 600 micro operations. Okay. Now the number of address lines required to access the control memory. How many address lines I will require to access the control memory? Now the control memory has 600 different instructions. So how many bits I will need to store those instructions? 600 different, right? So I will store my instructions like this, right? If I just bring, this is my control memory, correct? This is my control memory. So I'll store my instructions like this. How many address lines I will be requiring? How many address lines I will be requiring? Basically, there are how many? 600 instructions. So 600 micro operations. So I will have 600 of this, right? Present 600 control words. So 600 micro operations, meaning I will have 600 control words. So I will need to store 600 control words. So 600 different address I will have. So total how many bits I will require? Simply the log of this. I have already done that. Okay, solved that. So it will be log of 600, right? So that will be 10 bits. I will be requiring 10 bits or 10 address lines. 10 bits or 10 address lines. 10 address lines. Okay. So it will be 10 address lines. Just hold on a second. I will check if everything is recording or not. Yes, everything is recording fine. Yes, I will be recording 10 address lines. Now let's move on to the part C. What does the part C tell us? The control memory size in bits. What will be the control memory size? Now, this is very interesting, right? You know how to calculate the control memory size. There are address and what does each address contain? That's how we define the control memory, if you remember, right? If you remember correctly. So how many bits does the control memory contain? So that we have to write down, right? So I have total how many of this control word? I have total I will require 10 bits, and in this 10 bits each control word contains how many? Each control word contains how many bits? So I already know that I have 100 control signal bits. So each control word, what will be each control word containing? So I have here a control word where the first portion of it is gone, 100 bits is gone for control signal. Okay, this is gone for control signal. Now next portion is for what? Next portion is for the mux select lines, right? Mux select lines. And don't forget, I have explained the control word sequencing as well. So this control word will contain the information about the next address as well. Next address, next instruction address. So for mux select lines, how many bits do I need to provide? 2 bits. For next address, how many bits do I need to provide? It is address, and address has how many bits? 10 bits. So each control word, this is a control word. Each control word contains how many bits? Each control word contains total of 100 plus 2 plus 10, that is 112 bits. Each control word contains 112 bits. So total how much memory I will have? I have each control word here is 112 bits, and how many of this I have? 2 raised to power 10, because it's a 10 bit address line. So 2 raised to power 10, it is 2 raised to power 10 into each control word bits, right? So this is in bits. So this is what? This is almost equals to k. In computer, this is defined as k. So this will be equals to 112k small b, 112k small b. Now if I want to write it in terms of bytes, how will I write it in terms of byte? Small b, this means what? This means kilobytes, not bytes, sorry, kilobits. And what about if I want to write it in bytes? I have to divide by 8. It will be 14 kb. Okay, this is capital B, so this is kilobytes. Okay, so just be careful. And one more thing I want you to warn is, don't make this silly mistake that I have only 600 micro operations, so I will have only 600 of these control words, and what I will do is I'll simply multiply the memory. Memory will be CU memory. You will do 600 times each, like what does each control word, how many bits does each control word contains? Total 112 bits. 112 bits. This will be totally wrong. Why this will be wrong is, you have told that you are providing 10 address bits, right? 10 address lines. And I know that there is a wastage of space, that few control words will be wasted. Why few control words will be wasted? Because I'm not using all of them, right? I out of 1024, I'm only using out of 1024, I will be using only 600, right, for my operation. And it's okay. I cannot use 9 bits. If I use 9 address lines, it will be 512. So you will be left with 88 control words, like you will not be able to decode, right? So obviously you will require more, you will take extra, and your I'll be only using 600, so the 424, right, 424 words here, 424 words, 424 bytes or like words, they will be just left empty, and it's okay. But you have already assigned 10 bits for address lines. You cannot do like half 600 you will store for control unit memory and you store some other things in there. You cannot do that. Once you assign 10 bits, so all the 10 bits, all whatever memory is there, all of it will be used for control unit. It's okay if you are not using all the instructions, that's fine. You're not using all the memory, that's fine, that's your decision. But you cannot do it like this, that you're only using 600 and you are keeping empty 424 for something else. No, it doesn't work like that. Okay, it is a separate quantity. It is within this control unit, you cannot use it for some other things. Okay, so don't multiply 600 by 112, you will make a mistake here. So that's what I wanted to mention. Now there are two things for your for your control memory. Okay, there are two types of control memory. One is, just hold on, I will check if everything is here is correct. Yeah, everything here is correct only. I'll just quickly check the calculation. Actually 600 into this, yeah, everything is correct. So what I was talking is that there are two types of control memory. One is horizontal microprogramming, another one is vertical microprogramming. So what does this horizontal and vertical means? We'll understand this with questions also. In horizontal microprogramming, 1 bit is assigned to each control signal. So just what we learned, right? This is horizontal. Everything is in horizontal, right? So each control signal will be assigned to one control bit. Okay, just like PC in, PC out, they will be assigned one control bit only. All control signals are explicitly specified in the control words. Okay, all control signals will be specified in the control words. Here, faster as no decoder is required. Mux will be required. Okay, mux will be required. Which signal to pass through, which signal to make high, that will be required. But no decoder. Mainly decoder will not be required. Large control memory size due to longer words. So the words are very long, right? It's like 112 bits long. It is a very, very long word. Okay, so it will take up more space. So if I want to reduce the space in the control memory, we can use a concept known as vertical microprogramming. Okay, so this happens when control signals are grouped and encoded using fewer bits. A decoder generates the actual signal. Okay, how do we do it? I will explain. Just understand this. We will use horizontal microprogramming when we prioritize speed. And we'll use vertical microprogramming when we prioritize I think this will be what do you say, memory. We don't have much storage. Advantage is we will use smaller control memory due to compact control words, because control words will be like smaller, because we will decode all the control signals with a decoding logic. So obviously it will be slower because there is a decoder, so obviously we will need a decoding logic. But do remember one important point: to use the decoding logic, right? To use the decoding logic, all signals in same group must be mutually exclusive. All the signals in the same group must be mutually exclusive. Okay, what do I mean by it? So in horizontal, we already know, like we provide control signal for each of the bits, right? Each of the control signals. So we provide bits for each of the control signals. In vertical microprogramming, what I will do is I will have, let's say, this CS1, CS2, just hold on, CS1, CS2, then I will have here CS3, CS4. So if I would have used horizontal microprogramming, how many control signal bits I will require? I will require a total of 4 control signal bits. 1, 2, 3 and 4. Control signal 1, CS1, CS2, CS3 and CS4. Okay, so total 4 bits. With what? With horizontal microprogramming. Horizontal microprogramming. Okay, now if I want to use vertical microprogramming, how will I store the bits? So what I will do, I know one thing, that if control signal 1 is on, right, control signal 2 will never be on. They are mutually exclusive. If control signal 3 is on, control signal 4 will never be on. So what I can do, I can put them in groups. I will write here that my CS1 and CS2 and CS3 and CS4, they are mutually exclusive. They are mutually exclusive. Like if that, what does this mean? This means if one turns on, other will never be on. Example: PC in and PC out. Can they simultaneously be on? Okay, there can be few cases where they can be simultaneously be on, but I am taking an example. Generally, PC in, like when it is taking the input and when it is giving the output, they won't simultaneously be turned on, right? That is a general convention. So I can give you like many examples like this. So if they are not simultaneously on, what I can do, I can put them in groups. What I will do, I'll put them in groups. So this will be my control word now, and the control word will have group G1, G2. Okay, we'll have group G1, G2. So what I can do is simple put a 1:2 decoder, correct? 1:2 decoder. So this group contains like control signal 1 and 2, but has only 2 bits. 3 and control signal 4, but it has actually only 2 bits, right? So if G1 bit is on, I'm just giving you an example, don't take it as it is. So if this G1 is 0, then this decoder will select what? This decoder will select basically, like there is some logic, it will select 0 1 or something like that. And if this G1 is 1, then this decoder will select 1 0. It will turn on other signal. So I have implemented that logic. First it will select the CS1 if it is 0, it will select the CS2 if it is 1. So I have got a decoder. Okay, so how many bits did I require? I require only 2 bits and 2 decoders as well. So obviously this will cause some delay, but it's my advantage, right? I reduce my size has been reduced to from 4 bits, it has been reduced to 2 bits. Okay, but what is the disadvantages? The disadvantages is 0 decoder to 2 decoder. So memory less but slower, and I need to implement hardware logic, right? So that is also a disadvantage of this particular thing. So I hope you understood what is the difference between horizontal and vertical microprogramming. So let's do a few questions on this. Arrange the following configuration CPU in decreasing order of operating speeds. I know we have studied 3 types of control unit, right? One is hardwired control unit, another one is horizontal microprogramming, another one is vertical microprogramming. Now, in hardwired, everything is hardwired, so it will be very, very fast. We don't have to go to the lookup table and have a memory access, right? We don't need to do that. So hardware will always be faster. So which they are telling me in decreasing order of operating speed. So highest operating speed will be of hardwired. So in the first element, it should be hardwired. I can see these 2 options are hardwired. Now I move on to the next element. Horizontal microprogramming or vertical microprogramming. In horizontal microprogramming, the control signals are directly in the control word. So even though it is slower than hardwired, yes, but it is faster than vertical microprogramming. Just reason I have explained here. We don't need a decoder. It will take some time, right, to decode that. So horizontal microprogramming will be faster than vertical microprogramming, but will take more memory. But we are not talking about memory here. We are just talking about speed. So horizontal microprogramming will have more speed than vertical. So option B will be correct. So through this question, I just wanted to clear the concept. In horizontal microprogramming, does not require use of signal decoders? Yes, it is correct. It does not require use of signal decoders. Results in larger size micro instructions than vertical microprogramming. Yes, we require large size micro instructions because like each bit, like all the control signals are present in each bit, right? So we have huge number of bits in the micro instructions of the control word. So next is uses 1 bit for each control signal. Yes, that is what I told, right? Yes, it uses. So obviously all of them. So don't always in the examination hall be in a hurry that you read the first option, it is correct, and tick and you went ahead. Read all the options. Okay, let's do this question. So this question is also interesting one. We have like from this question we'll understand a very, very interesting concept. I will explain that. A instruction set of a processor has 125 signals. So instruction set has 125 control signals, which can be divided into 5 groups of mutually exclusive. So if one is on, the other will always be off. Okay, signals. Group 1 has 20 signals. So G1 has 20 signals. G2 has 70. G3 has 2 signals. G4 has 10 signals. And G5 has 23 signals. Okay, how many bits of control word can be saved by using vertical microprogramming over horizontal microprogramming? So how many bits I will require to explain 20 control signals, right? So this is a decoder. So in a decoder logic, basically how many bits I will require? So this, the right hand side is 20, right? It should give me 20 bits for the control signal. So left hand side, how many bits I will require? It will be depending on the rate. It will be like, if you have studied digital electronics, it will be log of base to 20, correct? Not this, upper bound of 20. So upper bound of 20 is simply equals to 5 bits, right? So here I will have 5 signals. Okay, this will be 5:20 decoder that will decode from 5 signals to 20, correct? So I will have 5 bits here for the group 1, G1. So I will just draw the control word here in vertical program, but horizontal all the control signals will be present, right? So in vertical, okay. So here what it will be is, basically what I will do is, I have the control word G1 I have, then G2 I have, then G5 G3 I have, then G4 I have, then G5 I have. Okay, so this, for this I will require 5 bits. Similarly for this, how many bits I will require? For this, how many bits I will require? 70. So what will be log base 2 of 70, upper bound is 7 bits, right? This will be requiring 7 bits, okay. And what will be the log base of okay, this is correct, yeah, 7. What will be the log base of this 2? This will be only a single bit. This will be only a single bit. So this will be a single bit. This is for this group. So this is becoming a messy. And for here it is log base 2 of 2. It will be a single bit, right? That has already been proven. So by side I will write the bits actually. That will be helpful for us. That will be helpful. So this will be equals to 5 bits, 5. This will be equals to 7. This will be equals to 1. And G4 I can directly do now. I can directly do, what is log base? What is log base? 10. So log base 10 will simply be 4, right? I will require 4 bits. And what is log base 23? Again I will be requiring 5 bits. I will be requiring 5 bits. Okay, so total how many bits I needed? So here 5 plus 7, 12, 12 plus 9, 21 and 22. So total bits in microprogram, vertical microprogram is 22 bits. This is whole a control word, right? But if I would have used horizontal microprogramming, how many total bits I would have required? Ignoring like 22 bits is for vertical, only for the control signals, right? Only for the control signals. There will be next address, all those things will be there. I am ignoring that because that will be same for everything. That will be same, right? That will be same for the vertical microprogram and horizontal microprogram, correct? In horizontal microprogram, for control signals specifically, I would have had to given all the bits for the control signal. How many total control signal bits? 20 plus 70 plus 2. 20 plus 70 plus 2 plus 10 plus 23. So this will be 20 plus 70, that is 120. 120 plus 2, 122. 122 plus 10, 132. 132 plus, okay, just hold on. 20 plus, sorry, this is 90. This is 90, 92, 102, then 125. So total I have 125 bits. So how many bits did I save? So yes, these are for control signals. It will have the next address bits, it will have the mux, that is there, right? That is there, but that is same for both. That we don't save, we save only on the control signals. So bits saved, how much? 125 minus 22. So total of 103 bits were actually saved. I hope you're observing the difference, right? How many bits we are saving. Obviously there is some time loss here, there is some decoding logic, more decoding logic gets into here, but we are saving this many amount of bits, 103 bits. This will be your answer for this particular question. So I hope you understood decoder concept. If you don't know, please go and study digital electronics. So we have to find out the width of the control memory of a horizontal microprogram control unit given for the following specification. So we have 16 control lines for processor consisting of ALU and 7 register. So we have 16 control lines for this particular ALU and registers. So we have 16 control signals, correct? And this we have to calculate for horizontal microprogrammed. Okay, so 16 control signal for horizontal microprogram. And we have a conditional branching facility by checking 4 status bits. So I will have 4 status bits. I will have to provide 4 status bits according to which the control unit will branch. So this is 4 bits here and here, 16 control signal bits. I'm using horizontal, so I have to provide all the bits. I cannot use decoding logic. Provision to hold 128 words in the control memory. What do I mean by 128 words? So control memory has, like, each row has control words, right? So how many rows I have? I have total 128 rows. So I have only 128 of these rows. So how many bits I will have for the address? How many bits? It will be log of 2 128. So this will be 2 raised to power how much? 7, right? I will have 7 bits or 7 address lines. Okay, so total for horizontal microprogramming, a microprogram control unit, how many bits I will require? So total bits, right? They are asking me what is the width of the control memory? Width of the control memory, or each control word, what is the width of the control word? Each control word, that is 16 plus 4 status bits plus 7 address. So like your control memory will be consisting of this, right? Control memory will be here. I will have 16 control signals, then I will have 4 status bit, then I will have what? Then I will have 7-bit address. Okay, so this will be total 27. So 27 bits will be the width of the control memory. Now if they would have asked what is the size of the control memory, okay, what is the size of control memory? Size of control memory, what you would have written? You would have simply done 2 raised to power 7 into 27. So this would have been the size of the control memory. If you want to convert it into kilobytes, no, not kilobits, if you want to convert it into kilobits, what you'll do, you'll do 2 raised to power 10 into 27 by 8. So it will be like whatever is 27 by 8, I will calculate it. It will be 27 by 8. So 3.375 kilobits. Okay, answer is this. Answer of the question is this. Okay, this is the answer, 27 bits. If they would have asked what is the size of the control memory, then you would have written it like this. Okay, 3.375 kilobits. Okay, I'm just solving the extra portion of this particular question. Now let's solve the next question. So we have this question: consider a CPU where all the instructions require 7 clock cycles to complete execution. So all instructions will require 7 clock cycle. Any instruction will require 7 clock cycle. Okay, there are 140 instructions in the instruction set. So I have 140 instructions. So how many bits I will require for this instruction? I will see 140 instructions. So how many instructions I will require? Total number of instructions will be log upper bound of 140. How many bits I will require to define this many instructions is 8. Correct, I will require 8 bits. and I have 125 control signals. 125 control signals are needed to be generated by the control unit. So this will be generated by the control unit while designing horizontal microprogram control unit. Single address field format is used for branch logic. So a single address field will be used for branch logic. So like they have told me, like we are using a horizontal microprogram, right? So if I am using a horizontal microprogram, how will my control word be? First I will have control signals, then I will have next address field, okay, and I will see if they are telling me about mux and all. If they are not telling me mux, I will not write the mux bits, okay. If they are telling me, I will write the mux bits. And I have how many different instructions I have? Total 140, right? I will record 8 bits for 140. So what you will answer is, no, this is not 8 bits, sorry, this is incorrect. This is 8 bits, yeah, 8 and 9, yeah, this is 8 bits only. Yeah, 9 will be 512, yeah. So what you will answer? You will answer here 8 bits, okay. And what they are asking? They are asking that what is the minimum size of the control word and control address register. So 8 plus 125, 5 is 133. You are not seeing that in options. And control address register also is not present, okay. Control address register should also be 8 bits, right? Its address field should have been 8 bits, so it is not present. So what went wrong here? What went wrong? I made a silly mistake. They gave me this information, right? 7 clock cycles, and this is instruction. This is not micro operation. Control word stores the micro operation. So this is wrong. This thing is wrong. This thing is wrong. So I will write here. I write down the important point that control word stores micro operation. Okay. Control word stores micro operation. It does not store like instructions. It only does micro operation, right? So how many, like all instructions have 7 clock cycles. So 1 clock cycle is 1 micro operation. Remember, 1 clock cycle is 1 micro operation. So total number of micro operations, how many total number of micro operation I have? Total number of micro operation is 7 times 125. 7 times 125. So not 125, sorry, not 125. I have total how many? 140 instructions. So 140 instructions has 7 cycles each. So how many cycles or how many micro operations I have? 7 times 140. So it will be 980. So this many number of micro operations I will have. So for this, how many bits I will need? Total number of bits. Because I have to store this micro operations, right? Each micro operation will be stored in each control word. Each control word corresponds to each micro operation. Total number of bits for micro operations. Okay, so this will be the address line bits, because I have to store those control words, right? It will be log, upper bound of log base 10 980. So this will be equals to 10 bits. So actually I will require 10 bits to store all those data, right? This is the address line bits. So like what am I talking about? So I have control memory here, right? I have control memory here, and this many micro instructions I have. This is I1, I2, something like that, right? Micro operations I have. So total how many I have? Total I have 980. So how many bits I need to define for each of these address fields? Only 10 bits, right? 10 bits will be what? It will be 2 raised to power 10. It will start from 0 to 2 raised to power 10 minus 1, that is 1023. 1023 should be enough. So total 1024 I will have values, out of which only 980 I am using. Unused are there. I don't care. I will leave it empty. I don't care about that. Okay. So actually my control word will consist of control signals, which will be of 125 bits, and it will consist of address, next address instruction. So it will be 125 bits and 10 bits. Okay. So what are they asking? They are asking me the minimum size of the control word. Minimum size of the control word, you have to minimum at least provide 125 bits, 135 bits. You can provide more. Here in the address field, right, you can provide 11 bits. it will be able to store more instructions. Okay, I am not using it, that is my decision, but you are providing 11 bits. But minimum is you have to provide minimum 10. If you provide 9, I can only describe 512 instructions. 512 instructions. I cannot describe the other remaining out of 980. I cannot describe the other ones. Okay, so I have to at least provide 10 bits. So that's why minimum size of the control word will be 135, and the size of the control address register you have to at least provide 10 bits. Same reason. So option D will be correct. Okay, just be careful about the information, and like this happens with me also. Sometimes the questions of the COA are very big. You miss out on some information. You miss out on some important information. Just be careful regarding that. Okay, so let's read the next question. Okay, so this question is also very good. This question is also very good. We need to be very careful in this question. Okay, so I will solve this question. So here a microprogram control unit is required to generate a total of 25 control signals. So I have total of 25 control signals. Assume that during any micro instructions, at most 2 control signals are active. During any operation, right? During any micro operation, at most 2 control signals can be active. So it can be CS1, CS2. Okay. It can be CS2, CS3, it can be anything. So how many combinations I have? I have 25 C2 combinations. Out of 25, any 2 will be always active. I can choose any 2. Okay, this many number of combinations I have, right? Now what are they asking? Assume that during any, okay, this is immediate. Minimum number of bits required in the control word to generate the required control signals. Minimum number of bits. Whenever they are talking about minimum number of bits, then for to generate a control sequence or control word, which one I will choose? I will obviously choose the vertical microprogram. Whenever they are asking me minimum, first start of my thought process will be, we will choose like what type of architecture we'll choose. We'll choose vertical micro program. Okay, so next is what required in the condition to generate control signal. So how many minimum will require? So let's start off, right? I can group them up. Okay, so in horizontal what we would have done in horizontal, simply I would have done here 25 bits, right? All 25 bits would have been separate control signals. So 25 bits would have been there in horizontal. But obviously we will not use horizontal because I am saving on space. Okay. Now what if I choose vertical? Now in vertical, like I know thinking this for the first time will be difficult. I also wasn't able to figure it out for the first time. So in vertical, your first thought process will be just add them as groups. Okay, G1, G2, and like total we have 25 signals, so I can add total of 13 groups. And if I will assume that if one is on, other one will be off. Okay, but the problem with this approach will be that I don't know like which are mutually exclusive, because they have told me that at most 2 control signals will be on, but which control signals together? They have not mentioned me the combination. Okay, so this approach of 2 control signals each is wrong. Okay, because I don't know, because I don't have the information about the grouping of the control signals, right? I don't have that information. So I don't have that information. Now if I don't have that information, so what thought process I can do? So first thing what I can do is I need to choose minimum, right? I cannot choose a single group. What I can do is I can choose 2 groups. Okay, in vertical, if I choose 2 groups, G1 and G2. And if you tell me that in group G1, you tell me you are choosing 13 control signals, and in group G2, you are choosing 12 control signals. But they are telling me at most two control signals will be on. At most two control signals will be on. Now, if two control signals are on, then what will happen is, if I here, let's say in this G2 group, right, I have CS1 and CS2. Now they can be on together as well. The first rule for a vertical microprogrammed group is the signals should be mutually exclusive. If this is on, then this should not be on. But do I know? I don't know. They have not given me that information. They have told me that at most two signals will be active. So CS1 and CS2 can be active together, because I don't know if they can be together active or not active. So this option, this idea is also gone. But one thing I can do is, I can have this decoding logic, right? I can have this decoding logic, so I'll keep it. What kind of decoding logic? That if I choose here 25 control signals, and here are also 25 control signals, so I will develop a logic such that only, like, at most two can be on, right? So only one of the control signals here will be turned on, okay, and the other control signal here will be turned on. So the logic will be developed like that. So one more thing can happen. They have told me at most two control signals are active. It can happen that none of the control signals are active. So I have to choose another state for that none of the control signals are active, okay? +1 where 0 control signals are active. Here also +1 where no control signals are active. 0 control signals are active. So that can also be a state, right? No control signals are active. Okay, so that state also I have provided. Now, what kind of decoder I will require? So again, I will do the same logic, that is log of 225. That is equals to what? That is equals to 5 bits. So total how many bits I will require? 10 bits plus 10 bits, that is 5 plus 5, that is 10 bits. So minimum number of bits that you will require, okay, control word length or control word width, okay, it will be 10 bits. Option C. This is a gate question actually. This is a very, very old gate question, and I do agree the wording and all these things coming out of the brain at that examination hall is difficult. That's why I would have not come into my brain, okay. I would have also skipped this question, because this is a very, very difficult question, and understanding this kind of thing, right, takes patience and takes a lot of time. So I also would have skipped this question. I wouldn't have solved this question. So don't worry if you were not able to decode the logic. I also was not able to decode the logic, okay. So it's fine. It's totally fine. Just understand how to do this type of question. Next time when it comes, you have this in your mind. Okay, I can solve the question like this. This part is also very, very important. That what happens if none of the control signals are on, okay. So that particular state also you have to choose. So let's read another question. The micro instruction is to be designed specifically none or one of the 3 micro operations of one kind, none or up to 6 micro operations of another kind, okay. So none or one of the 3 micro operations of one kind will be active. Basically they're mentioning. So this can be defined as a group G1 where I will have 4 states, right? 4 control signals where either none of them are active or one of the 3 are active. So I have CS1, CS2, CS3. Either none of them are active. If none of them are active, I have to choose another special control signal, that is will be control signal 0, that specifies that none of them are active, okay, or one of the 3 are active. So either one of the 3 are active, right? Anyone. So all these 4 situations cannot happen once, right? All these are separate entities. Either none of them will be active or one of the 3 will be active. So this can be grouped together, okay. This whole thing can be grouped together. Why am I talking about groups? Because in the question they are telling me the minimum number of bits. Whenever they're talking about the minimum number of bits, then I have to think about vertical programming and grouping. Now, They're telling me none or up to 6 micro operations of another kind. None or up to 6 micro operations of another kind. None or up to 6 micro operations of another kind. So I have the control signals CS4, CS5, CX6, CS7, CS8 and CS9. So I have 6 different control signals and all 6 of them can happen, up to 6. They have told me up to 6, any 6 of them can happen. Can I group them? No, I cannot group them. Okay, and again they are telling me none. For none, right? For none, I have already taken a state here, right? I have already assumed a state for none here. Okay, I will also draw the control word. There also you will understand this better. This is my control word. Okay, this is my control word. Why I have group G1, which has all the 3 control signals: control signal 1, control signal 2 and control signal 3. Also I have another state known as none. Okay, if none of the 4 control signals are on. Now I cannot group them. These signals I cannot group, right? This I cannot group because it is not possible. So because any one of them can be on anytime. Okay, so it will be G3, G4, G5, G6. Okay, 1 2 3 4 5 G7. Now we will say you have to add another group G8 that also supports this none action, right? None of them should be on. Actually that none has been taken care here, right? I have already chosen the none here. If none of the control signals will be on, that has been already taken care in this group 1, because if all of these are off, so that means only none is the possible state, right? So none will be on in this group G1. So it has already been taken care of. So I will not take care it again. So total how many bits I will require in this particular group? As I am using minimum, as I require minimum number of bits, that's why I am using vertical microprogramming. Okay, so it will be log of the number of states. How many number of states I have? 4. So it will be 2. Okay, so here how many bits I will have? 1 2 3 6 bits. So minimum length of the control word. Okay, minimum number of bits. Control word length, or sometimes they call it width. Minimum is 8 bits. Okay, this will be the minimum width of a control word. 8 bits or a byte. So this is also an interesting question. I hope you understood the concept of this particular question from the previous question. The previous question is difficult. You can leave it if you are not able to grasp the concept totally. Let's solve another question. So we have this question where the micro instructions stored in the control memory of a processor have width 26 bits. So each control width, right? Each control each control signal or a control word width is 26 bits. Each micro instruction is divided into 3 fields. Micro operation of 38 bits. So each micro instruction is divided into 3 bits. Micro instruction, or sometimes they call it micro operation as well. So here I have the opcode, basically opcode. This is 13 bits. A next address field X and a mux select field Y. So this is a next address field X and Y. So this is address and mux select lines. There are 8 status bits in the input of the mux. So in the input of the mux there are 8 status bits. How many select lines I will require? So they have told me mux input is 8 status bits or 8 bits, and output of mux, I know it is it is always a multiplexer, so it will be one line. So how many select lines I will require, or how many bits I will require to control the mux? It is log base 2 of 8 upper bound, so it will be 3 bits. So I will require 3 mux select lines. Okay, that will be S0, S1 and S2. How many bits are there in the X and Y field? So in the Y field I have got the value, that is 3, this is my y. And what is the size of the control memory in number of words? So I have to read this visualize this diagram. So I am seeing this is a bus, right? All this is a bus. So this mux has 8 inputs, and these are the select lines and only one output. Okay, so it has total. So this x, right? This x is the going into the control address register. So this x is the input to the control address register. Okay, so I have 8 select lines here. And how many bits I have here? How many bits I have here? 3. I have 3 bits here, right? I have 3 bits here. Here I have 3 bits because this is the select line. This is the input to the mux. This is 3 bits, right? And this is 13 bits. Each micro operation opcode length is 13 bits. And they have told me that the control word width is 26 bits. So this overall thing, right? This whole thing is 26 bits, out of which 13 bits is opcode and 3 bits is mux select. So obviously I know the length of this whole thing is 26 bits, out of which I know this is 3 bits. So what will be the remaining one? It's very simple, right? It will be only 10 bits. So address line, number of address lines or bits, address lines or bits will be simply equals to 26 total width of the control memory minus the y, mux select lines. That will give me the x, right? This is the y. Okay, sorry, I have the opcode length as well, right? I have the opcode length as well minus the opcode length. So this will give me 10 bits. This is actually 13. Give me 10 bits. So what are they asking? They are asking me, first of all, what is x and y fields? X is 10 bits. X is 10 bits. So 10 bits is here. So these two are the possible options. Next, y is 3 bits. Y, both of them has 3. Now what is the next thing? The size of the control memory. How to write the size of the control memory? What will be the size of the control memory? Size of the control memory, size of control memory. We know how to calculate the size of control memory, right? How to calculate the size of the control memory? The size of the control memory will be the total number of addresses, total number of control words. How many I have? 2 raised to power the address field bits, that is 2 raised to power 10 into how much? Okay, what have that in words, right? Total in words. So you have to take care in words. So like how is my distributed? This is in, and what is the size width of each control word? It is 26 bits. But actually what are they asking? They are asking me what is the total size of the control memory in words. So control memory has this control word 1, control word 2, like this. How many it has? It has from 0 it has to 2 raised to power 10 minus 1, because this many address bits I have, right? Total how many it has? Total it has 2 raised to power 10. So this is in bits, but they are only asking me how many control words do I have in words. They are asking me how many, like size of the memory in words, size of the control memory in words, how many number of words, how many number of control words do I have. So each word is 26 bits, but I don't need to do this conversion, right? Total I will have 2 raised to power 10 control words, because this many address field I have. Each word is 26 bits, that is fine, but they are not asking me in bits. They are asking me how many words I have. I have 2 raised to power 10 words, that is 1024. So option A will be correct. So just be careful, what are they asking exactly? That also you need to be careful about. Okay, so this is also a very, very good question. Okay, so like in what unit they are asking, this also you have to be very, very careful. Now let's solve this next question. A CPU has only 3 instructions, I1, I2, I3. Which are the following signals in time steps? This I1 is this, I2 is this, I3 is this. Which use the following signals in clock cycle T1 to T5. Which of the following functions will generate the hardwired control signal for signal in? So like which of the logic functions? This is simple, right? This is just Boolean algebra. You can directly solve it. This is very, very simple, right? They have written in terms of what? In terms of instructions. So I will check in which in each instruction in which time zone my AN is common. So that I will check, right? So it's very simple, right? You can do it. It's just simple Boolean algebra. So AN is equals to IN should be here. Okay, in IN, in which time periods I have AN signal? In T1 time period I have AN signal, so I'll write here T1, or, and I have T3, right? T3 only at T3, T1 or T3. Okay, so we'll log this T1 or T3, correct? So next, what do I have? Or this is not IN, so this is I1. Now in instruction I2, do I have AN? Yes, I have AN here in T3. So it will be T3 into I2. In instruction I3, do I have AN? Yes, at T2 and T4 and T3. So T2, T3 and T4, T2, T3 and T4. This will be my instruction I3. Okay, so this is basically my logic family. So if I see T1 and T3, T1 and T3 is okay, T1 T3 is not present anywhere. Okay, actually one common thing I observed, that T3, right, it is present in all of them. So this T3 can be directly converted into, this will be T1 I1 plus I2 will be gone actually. Oh, I know I2 will be present, plus T3 or T2, T4, I3, because I don't care whatever instructions I have. T3, in T3 time period, in third clock, the AN signal is always high. The AN signal is always high in T3 clock period. So it doesn't matter if T3 is on, right? This AN signal will always be high. If I make T3 higher, if I make T3 1, it won't care about the other bits. If T3 is on, that means I know AN is 1, right? I can understand from here as well. At every T3, I'm saying AN signal is always on. AN signal is always on. So if T3 is on, AN will automatically become on 1. Okay, so that's why this only becomes T3. How does it become? Like we do it like this, that here T3, I1 or I2 or I3. Only I have this 3 instructions, right? It doesn't care whichever instruction it is, it will always be on. That's why I1, I2, I3 is simply 1. Okay, I hope you understood this point. Now T1 I1 is present here. T2 I3, yes. T4 I3, yes. T4 I3 is present. T3, yes. T3 is also present. So option A will be correct. You can check the other options. Other options won't match. Here I have T1, T2, T3, I3. T1, T2, T3, I3, no, right? T1 is not here. T1 is not with I3, so this is gone. T1, T2, I1. T1, T2, no. T2 is not with I1. This is also gone. T1, T2, I2. T1, T2, I2, no. T1 is not with I2. Okay, T1 is not with I2. So all the options are gone. So simple, like it's simple Boolean algebra logic only. So basically, I will just like show you an example what is happening in the hardware circuit. What is happening? So basically, I have a control unit here. Okay, and this is like a decoder circuit. So I will have instructions I1, I2 like this, I3, and then I will have the timing signals as well. Okay, T1, T2, T3. Now what it will do is it will give me the output. It will give me the output of what? AN will be here, then other logic, right? BIN will be here. Each will have its own control signal, and this is what I am implementing. Control logic. I am implementing the control logic in hardware. This is hardware, right? So it is not programmed inside the lookup table. It is not there. So it will become very complex, because every time I have to like write this logic family, then decode, it will be very, very complex, right? Hardware will be very, very complex. That's why we generally avoid hardware unless and until we require very, very fast operation. Now we'll understand about this CPU design, right? CPU design. Like we have two things, two types of instruction set computer. One is reduced instruction set computer, another one is complex instruction set. This is just theoretical point. Okay, this is just theoretical point. That's it. In reduced instruction set architecture, we have fewer instructions, focused on simplicity. As the name suggests, reduced. In complex, we will have larger instruction set for complex operation. Here, our length of the instruction will be fixed. Whatever we have studied this RISC, right? Where our length of instruction was fixed. Our opcode was variable. But length of instruction will be fixed. That's why it is easy. Here, the length of instruction will be variable. Then the decoding of the instruction, right, will be more difficult. Complex instruction that may involve multiple operations. So the decoding of the instructions will be very difficult. Just like index scaling, we can have index scaling and base address register, all those things, right? We can implement in complex instruction set architecture. It has limited addressing mode. It cannot support all the addressing mode because it is very simple. It's simple and straightforward. We cannot use all the addressing mode. It supports various addressing modes like index scaling and all those things. Okay. It is easier to implement using a hardware control unit because as the instruction set is easy, the decoding logic is also very easy. Here, the decoding logic is easy. So if the decoding logic is easy, that means like it will be easier to implement in hardware. But as the decoding logic is easy, we don't implement in hardware control unit for complex set instruction CISC. We implement it in microprogram. Okay, microprogram control unit typically executes one instruction per cycle, may require multiple cycles per instruction because as the instruction itself is very difficult to understand, it needs to decode and there can be multiple things in one instruction. There can be multiple micro operations. Okay, arithmetic operations are register to register only. Allows register to memory and memory to register arithmetic operations. This is the difference. This theoretical point you should know for placements and as well as gate. Larger number of registers are available, few registers are available because mainly we'll focus on more memory and other things. Highly efficient for pipelining. What do you mean by pipelining? We'll understand this in the next lecture. What is pipelining? Don't worry about this right now. Okay. So there are few theoretical points, few theoretical questions about CISC and RISC. The main difference between CISC and RISC is /R that a RISC processor typically has fewer instructions. Yes, the full form is reduced instruction set. So obviously it will have fewer instructions. Correct. Has fewer addressing modes. Yes, it has fewer instructions, fewer addressing modes. Like CISC supports complex addressing modes. Has more registers. Yes, it has more registers for faster operation because mainly we allow only register to register computations. We allow mainly register computation. Okay, is easier to implement using hardwired logic. Yeah, yes. Our RISC processor is easier to implement using hardware logic. Why? Because decoding logic is decoding logic is simpler. Decoding logic is simple. So option D will be correct. All the options will be correct. A, B, C, D. Now let's solve the last question of today's lecture. So we have this question. Consider the following processor design characteristics. Register to register arithmetic operations only. Fixed length instruction format. Hardwired control unit. So it is a characteristics of RISC processor. Which of the following are above characteristics of RISC processors? All of these are characteristics of RISC processor, right? So 1, 2 and 3, all of these will be correct. Okay, option D. So these type of question can come on gate and placements. Be a bit of theoretical concept about CISC and RISC processing. Okay, that's about it about control unit and RISC and CISC processor. I hope you have enjoyed the control unit. We will have finished the control unit. Next, a very important topic will come, that is pipelining. So don't skip it. Be fully attentive on that because you can expect question on placements and on gate from pipelining. It is a very important topic. Thank you for watching and I will see you in the next lecture. Until then, happy learning. Hi everyone and welcome back to my channel. So today we'll start a new topic of computer organization and architecture. So today we'll learn instruction pipelining. Okay. So before starting today's lecture, I want to say this is a separate topic than all the previous topics, whatever we have learned. And please pay close attention to this because this is a very important topic for both gate and placements. Because questions will get asked because this is a topic that has actually use case in the actual industry. So that's why this topic is very important, and many students do get confused with few like sections of this topics like hazards. So we will understand everything very clearly. This is important for both gate and placements. Okay, so let's start. Like we can observe a picture here, right? What does this picture want to say? At the I hope at the end of this lecture you will be able to understand the difference between this and this. So I'll just give you a bit of overview. Basically what the first picture is doing, it is doing all the tasks, right? Here I have some I have 4 people with 4 laundry bags. All of them want to wash their clothes. So there can be 2 ways to go about this. One is, one person A goes here to the washing machine. He drops his laundry to the washing machine. Then there is another machine, that is dryer. Then he takes out the clothes after the clothes have been washed and gives it inside the dryer, and then it dries. Then finally he takes out the clothes. Okay, and he finally goes to home. And after this whole transaction, I again call the person B. Okay, but there can be another way to do this as well. So while the first person is doing, we don't make any changes. Okay, first person does his puts his clothes in the washing machine, then he puts his clothes in the dryer, then he went out. But as soon as the person takes out his clothes from the washing machine and puts in dryer, this washing machine, right, this is free actually. This washing machine is actually free. So what we can do, we can tell person B, come here. Okay, you can put your clothes in the washing machine because the washing machine is currently free. It is not getting used by anything, right? Dryer is getting used by person A, but washing machine is free. So you can utilize that time for which the person A is drying up his clothes in the washing machine. Then as soon as the clothes gets dried up, the person A takes out his clothes and the person B again puts his clothes in the dryer. Okay, then again the washing machine is free. Okay, so like this happens. We'll see more examples. I'm just giving you a overview. What happens? What is the difference between this? This is sequential. This is sequential processing because one process is totally independent of other. Person A washing the clothes is totally independent of person B washing the clothes. Okay, both things are totally independent. Okay, but here actually few things are dependent because when the person A is using the dryer, person B is using the washing machine. So few things are interrelated. We will understand those. So here what is happening is, this is a mode of sequential sequential processing, and this is a mode of what? Parallel processing. So actually we have a few classification. This is a very old classification that Flynn gave. Now, like basic things, they have just named these things. For the first classification of computers is single instruction, single data. What does it mean? A single processor executes a single stream of single instruction stream to operate on data stored in a single memory. So standard non-parallel computers use this. So the data comes in, like the instruction comes in, the processor processes the instruction, it does some operations on the operands, and then finally after this instruction I1 has been fetched, then only I will fetch the instruction I2. So how we go? First I fetch I1, then after fetching I1, after completing instruction I1, after executing instruction I1, I go to I2, then after executing instruction I2, completing instruction I2, I go to I3. So all of this, right, are happening in serial, okay, sequentially. Nothing is happening in parallel. So after only I finish my instruction I1, my first task, then only I will go to task 2. I will not go to task 2 simultaneously. How do we go simultaneously? I will show you with example. Today's lecture is about that only. Now next type of classification is single instruction multiple data. A single instruction operates on multiple data streams simultaneously. So what happens is, instruction is same, but I have to perform the same instruction in multiple data points. Let's say add AB. Okay, I have add AB here, or add like 2000 each, and 1000 each. And after every instruction, this address is getting incremented by 1. These are all addresses. Go to this memory location and add the operands. So then the next instruction will be 2001 each plus 1001. So I can actually do this. What I like, my processor is computing sequentially only, but it is processing multiple streams of data simultaneously. It will take all the data simultaneously, then add. Okay, it can do that. So this has this is what we do in pipeline. Okay, this is exactly not parallel processing. But this is like what I will show you example, like this example, right? Exactly, we are not doing parallel processing because we are not executing two instructions parallelly. No, we are not doing that. But what we are doing is we are allocating resources. So first I observe that washing machine is free. After person A has finished washing his clothes, he will put it to dryer. So washing machine is free. So I will allocate that resource until when the washing machine is free to person B. So here what happens? The resource allocation happens. So I'm doing some operations simultaneously, but what I can say is they are not exactly parallel. What do you mean by that? We'll understand that by the example, but just understand this is what we use in pipeline processing. Okay, pipeline processing, where we process the data simultaneously. Next is multiple instruction and single data. So like this is not possible sometimes to have, like we have multiple instructions and I'm operating on single data. This is mainly theoretical model because like if you have multiple instructions on the single data, your I1 instruction, let's say your I1 instruction is A plus B, right? So it will change the contents of AB. It can. So there is just, it is a theoretical concept of multiple instructions, single data stream. Actually, we don't use this. Generally, it is used in fault tolerant systems where same data is processed using different algorithms. Okay, so the use case is this. Then is multiple instruction, multiple data. So this is actually what is known as parallel processing. So this is actually true parallel processing. This one is also a parallel processing, but not exactly, because I am not exactly processing these two things parallelly. No, but a few things are common here, right? So this is in the gray area. Okay, so this is the true parallel processing where I have multiple processors for executing different instructions and they are happening parallelly. So this is true. True parallel processing. So like there are many types of parallel processing, so we'll understand those. So first one is array type, where employs an array of processors to execute tasks on multiple data simultaneously. So this is like MIMD. Okay, this is like MIMD that I have just told you at the end here, right? This is just that. Another type of parallel processing is there. Okay, so like what is that? That is like, what does parallel processing helps? Why does parallel processing help us? It helps because we can do simultaneously data processing of multiple instructions. So obviously our execution time of the whole program gets reduced, right? If your compiler, like if you have 100 lines of code and each line is an instruction, so it will take you, let's say each line takes 100 seconds. But if you have multiple processors which are like processor 1, let's say, is executing instruction I1, I2, I3, and processor 2 is executing instruction I3, I4, I5, or something like that. Okay, so obviously the execution time of the program gets reduced, so you save time. Okay, you save execution time, which is very, very important. Now what is parallel processing? What is the other type of parallel processing known as pipeline processing? So this is more like single instructions and multiple data. Okay, so this pipeline processing is actually not helpful everywhere. It is not helpful everywhere. We'll understand this. So this is like wherever I have a type of single instruction and multiple data, so I have to, like, similar instructions are there and I have to do it on multiple datas, then this pipeline processing will be helpful. We'll understand that slowly. It breaks down sequential process into sub operations performed across multiple stages. Like what is the example? Example is assembly line in factories, like producing cars on a assembly line. So in a like car, right, in an assembly line of a car, what happens first? Like, I exactly don't know the process, but first you build up the structure, right? Or somewhere engine gets built, somewhere the suspension gets built, somewhere the tire gets built, and at the end finally you all what do you say, assemble that. So the engine getting built and the suspension getting built, are they sequential or they can be run parallelly? They can be run parallel, right? Because at some place I will have some production site for engine, and at some place I will have some production site for suspension. So those can happen parallelly. So we'll see those. And producing cars is what? It's a repetition of same thing, right? We're repeating the same thing only. If I am producing a car, we are exactly repeating it 1,000 times. A single instruction is producing, let's say, car XYZ, right? And we have to produce the same car only. Why will we produce a different car? Okay, so with the help of example, we'll understand this. Let's take a basic example. Pipelining is a method of decomposing a process into smaller subtasks, enabling simultaneous execution across different stages. Okay, so let's take example. You are making a sandwich. So to make a sandwich, there are 3 steps. Okay, so this is my instruction. Sandwich making is my instruction, and I have broken down my instruction into small stages. These are actually known as, in technical term, known as pipeline stages. Okay, here they have also told different stages, right? Or subtask, you can also say subtask. So to make a sandwich, first you have to cut the bread. Okay, it takes you around 2 minutes. Then what you have to do, you have to apply butter and filling inside the sandwich, whatever filling you want. Like you want some chicken filling or some paneer filling or some like only vegetable filling. Okay, anything filling between those 2 sandwich, you fill that. So it takes, let's take an example, it takes you around 3 minutes. And to pack the sandwich, finally that has been done. You have to, like, it's like assembly, right? You pack the sandwich totally and give it to the end user, or you yourself want to take it to the like you or take it to office or class. After on lunch you will eat that. Okay, so these are the different stages. Now each of them takes 2 minutes, 3 minutes and 2 minutes. Okay, so if I am not using any pipelining, right, making each sandwich, so let's say you want to make 10 sandwich, making each sandwich will take you how many minutes? Pause the video, answer in the comments below how many minutes. If you are not using, like, for those people who know pipelining a bit, they can answer. Who don't know, don't worry, I will tell you the answer. Okay, I will explain. So without pipelining, how much time will it take to make each sandwich, and with pipelining, how much time it will take for a new sandwich to get ready after the first one? How much time the next sandwiches will take for me to get ready after the first one if I am using pipeline? So without pipelining, it is just sequential processing. So first I will cut the bread, then I will apply the butter and filling, then I will pack the sandwich. So first sandwich is done. Then only after the first sandwich is done, then I will come back to the second sandwich. So each sandwich is taking how much? 2 plus 2, 4 plus 3, 7 minutes. 7 minutes. Now, someone smarter, okay, like a big company CEO or something, came to your place and told you, yeah, Rakesh, actually we can do it a bit better. What we can do is, we have this 3 tasks, right? 3 stages we have. So we can assign individual person to each of these stages. So there is person A to cut the bread, there is person B to apply the butter, and there is person C to pack the sandwich. So there is person A, B and C. Now they are different person, so they can do tasks simultaneously. So that is what we will do. So here what we do is, in timeline between 0 to 1, the first sandwich, person A will do what? Person A will cut the bread, and person B and C will simply sit idle because they don't have anything to do, because bread hasn't been cut yet. So as soon as person A cuts the bread, he sends it to person B. So person B gets the cut bread, right? Now what is the task of person B? The task of person B is to apply butter. So person B applies butter. Okay. Just I will technicalities I will come to later on. For now, just understand the basic things. Okay. Okay, one thing. This has been a bit wrong actually. I will just edit this small thing. This is wrong. This is wrong actually. I will update this. Don't worry about time right now. I will update this. Okay. So, what I can say is, this is taking 3 minutes. Okay, fine. Or what we can do, right? We can actually change a small data point. Okay, no, we don't want to change the small data point actually. That is enough. I told you, right? Person A has cut the bread and he has sent to person B. Okay, so person B currently, so this is from minute 0 to 2. Minute 0 to 2, and person B from minute 2 to some other minute. Person B is doing what? Person B is applying filling to the sandwich 1, but simultaneously person A right now is like he is free, right? Person A is free, so I can give him the sandwich 2 and tell him, but you are free right now, so cut the bread right now. You can cut the bread, right? For cutting the bread you don't need anything else, so I will give him the sandwich 2 and he can cut the bread. But in the same, like from the same time, person B is also doing the work, but person C is idle right now. Okay, person C is idle. Now I come back to third stage. Okay, I will not tell you the time right now. Time is a bit I will tell you the time. Time is a bit confusing. But at the third situation, third step, so person A has finished his cutting his sandwich 2. He will send it to again person B, because person B also has finished his filling. Person B will send it to person C for final like packing the sandwich, right? So now all the 3 persons are doing the work simultaneously, right? But they are doing different works. So here there is simultaneous execution across different stages. They are not doing the same task. They are not adding, like let's say there is an add instruction, right? So they cannot add simultaneously, but they are doing like separate task. Okay, different stages. So this is like this is cutting, like person C right now is packing the sandwich. Person B right now is filling the sandwich for the second sandwich 2, and person A is cutting the sandwich for the third sandwich. So parallel operation is happening. Now you might say, why is this so much useful? Why is this so much useful? The useful comes here, right? Comes here at the output. So for the first stage, it doesn't make any difference. Okay, it will take the same time. For the first stage, it will take the same time. But for the second stage, for the first sandwich, it will be same only. For making the first sandwich using pipeline instruction or non-pipeline instruction, it will take the same time. But for making the second sandwich, right, it will not take us much time. It will not take us much time. So why? Why is that after this, right, after this packing portion is happening, at every cycle, like after every jump, I'm getting a new sandwich ready. Because all 3 are actually working parallelly. Okay, all 3 are working parallelly here, but they are doing different tasks. So as soon as I come here, right, so as soon as this person C will send this sandwich to the output, to the tiffin box, person C will again receive sandwich 2 instantaneously, and person B will receive sandwich 4, and person A will receive sandwich 5, like that. It will go on. After every cycle or every jump, I am getting a sandwich ready. Now what is the duration of this jump? That we'll understand. So basic idea, I hope you understood. We have more examples, don't worry, we'll understand this more. Okay, so one thing is there, I want to do task parallelly, but I want to do different tasks. So how much gap should I give to each person? So person A and person B and person C, I would give them some time, right? Because if, for example, you tell person A you take 2 minutes, person B you take 3 minutes, and person C you take 2 minutes, what will be the problem with this? If they don't have a common time, right? If all the 3 stages don't have a common time, what will be the problem? So first here person A does from 0 to 2, does cut the sandwich, and he finishes the sandwich. So from 2 to what? This is the important. 2 to what? he will like from 2 he will send to person B who will apply the filling. So from 2 to apply filling, how much time do I need? I need 3 minutes. So it will be 2 to 5. Okay. But there is a problem. In 2 minutes, right? This person A will say, man, I have finished cutting my sandwich. What I will do? You have told me to not sit idle. So I will send this sandwich to the person B. But this person B will tell me, I am still working on something, right? I am still filling the bread. You have given me 3 minutes to fill the bread, but only 2 minutes have passed, right? After like this sandwich 2, cutting of sandwich 2 will be finished by when? It will be finished by 4 minutes. Still I have 1 minute left for this person B to finish filling. Okay. But person A will say, instruction came from the CEO. He has told to apply like this, that whenever I finish my job, I will send it to the next stage. But person B will tell, I don't have free space right now. I have to first fill the sandwich, do this task, then I can fill the next sandwich, right? So there is a problem here. So we like nullify this problem, to get around this problem, what we do, we have a common time. And this is also known as synchronous pipelining. This particular thing known as synchronous pipelining. What we do is, we take the maximum of all these stages. If I take the maximum, right, there cannot be any overlap, because it can't happen that I have taken the maximum time and person B, like person A will finish cutting the bread in more than that. Person A will finish cutting the bread in only in 2 minutes. It will not take 4 minutes, right? If I choose the maximum out of these 3, my duration cannot go above that. So I will choose the maximum so that I have enough headroom for no overlap and no confusion. So what I do, I will choose a maximum. So this maximum of T1, T2 and T3. Okay. This step is actually known as also synchronous pipelining, because everything is in sync. Synchronous pipelining. All the time is same. It is not different across each stage. That's why it is called synchronous pipelining. So a new sandwich is ready after the first how many minutes? This problem we haven't yet solved, but what we have solved is, we have found out the duration of each stage. So we'll choose the maximum. Maximum here is 3 minutes, right? Out of all these stages. So I'll choose 3 minutes. I will choose 3 minutes. Okay. So that's why I actually deleted this previously. So this will be, each stage will be 3 minutes. They are also sometimes known as cycles. So from 0 to 3, I will give the person A to cut the bread. And you will say, sir, person A will sit idle for 1 minute. It's okay. It's fine. That is fine. Okay. Why that is fine, we will understand that later as well. But it's okay. Let person A sit idle for 1 minute. That is fine. But I cannot give it after like 2 minutes only. That is the issue, right? There will be some overlap. Person B will crib about that thing. Okay. So from 3, again, each cycle will be of 3 minutes. So this will be from 6 to 9. Nine to 12. This will be from 12 to 15. So what is happening here is, from 3 to 6, like after 3, sandwich 1 goes to person B, and at 3, sandwich 2 comes to person A. So now person B will take 3 minutes totally to filling, and then it will send to person C. So there is no overlap. And as soon as it sends to person C, person A, after 3 minutes, that is at 6 minutes, it will send to person C the sandwich 2, and person A will receive sandwich 3. So after this, right? After this, what is happening is, after every cycle, after every 3 minutes, a new sandwich is getting ready. If I observe here, person C is receiving the sandwich 1 at 6 minutes. Then it will again take 3 minutes. I will give it 3 minutes to complete its task, and it will hand it over to the lunch box. Then again, At 9, person C will receive the sandwich 2. Again, it will hand it over to the lunchbox after 12, after 3 minutes. Again, at 12, it will receive the sandwich 3. Again, it will hand it over to the lunchbox. So at every 3 minutes or at every cycle, my sandwich is getting ready. So each instruction gets gets execute, to be technically correct, gets execute in just every clock cycle. So isn't it so fast? Because how much time it is taking me for each sandwich to get ready? 3 minutes. 3 minutes. Okay, this is 3 minutes. Isn't this huge? This will be even huge when the tasks are very larger. Okay, and I can use pipeline on those. But there is a just caveat that you need to understand is we can only use pipeline processing for similar types of tasks. If you are repeating it 100 times, then only pipelining is useful. Just like I'm making sandwich and it is a repetitive task, right? So if I'm making sandwich, it is a repetitive task, we can use pipelining there. Okay, because making 100 sandwich will take me very low amount of time, because after every clock cycle a new sandwich gets made up. Okay, so that is where this pipelining comes into the picture, useful for repetitive operations on multiple data inputs. Only useful for repetitive. This is the most important point. I know you will forget this point. Okay, pipelining is useful only for repetitive operations, not for everything. Okay, so here this is a bit wrong. Total time for each sandwich, right? So how much total time did it took me to make 3 sandwiches using without pipelining? Each sandwich will take 7 minutes. So total 3 sandwich will take total 21 minutes, right? Because it is without pipelining, everything is working individually. Okay, independently. With pipeline, you will observe that the first sandwich gets ready at 9th minute. Okay, first sandwich gets ready at 9th minute. After that, right, my sandwich 2 only takes 3 minutes more, and my sandwich 3 also only takes 3 minutes more. So this is a bit wrong. Only the first sandwich will take me more time to make, that is 9 minutes, and after that every sandwich will only take me just one clock cycle, that is 3 minutes. So it will be totally 15 minutes. Okay, so obviously I'm saving 6 minutes, and which is huge. It is like almost 30% savings. Okay, so I hope you have understood the thing that I wanted to explain using this operation. Okay, so here, right, I just want to write down neatly so that you can understand. If you ever come back to device at this stage, this is ideal. Person B is ideal and person C is ideal. But in this period, right, in this time period from 3 to 6, only person C is ideal because instruction 1 hasn't been executed by the person B. And after this, right, from this stage onwards, okay, from 6 to 9, you can observe all the 3 persons are doing some work. So it is known as parallel operations of different stages. They are different stages. Parallel operation of different stages. Okay. So let's now understand what happens actually in our programs. So we use, like, this concept is known as pipelining. Like this concept, right? This concept of parallel processing, each processing happening in different tasks, is known as pipelining. Okay. So this is a concept. Okay. Why do we call it pipelining? Because if you observe, it is just like a pipe. Why it is like a pipe? If I place a pipe here, right, and for the first time this pipe is empty, then I put sandwich 1 here. Okay, so the sandwich 1 comes in this is, let's say, this is the stage 1 of the pipe, this is the stage 2 of the pipe, and this is the stage 3. So S1, S2, S3. So it takes the bread comes here, stage 1, then it goes to stage 2, then it goes to stage 3. So my first bread is here, then the second bread comes after that, it goes to stage 2, and the third bread comes here, it goes to stage 1. So it takes some time for the pipe to get filled. After that, what happens? If the pipe is filled, right, if the pipe is filled, okay, this is my bread, bread 1, bread 2 and bread 3. 3 breads are filled. So after that, if I put in one bread, right, this is bread 4, the first bread will come out here, correct? Then again, if I put the fifth bread, the other bread will come out here, bread 2 will come out. So it's just like pipe. As water enters, it takes some time for the water to get overall filled in the pipe. Then the water just flows, right? Water comes in and goes out, comes in and goes out. There is no delay. There is no delay actually. So that is the concept that we're using. That's why it is called pipelining, because it just flows like through a pipe, right? Each instruction flows through a pipe. Okay. So we in COA, we use this concept known as pipelining. Pipelining is a technique used to break sequential processes. They have to be sequential, do remember, into smaller sub operations which are executed in different stages, also called as segments. Each stage works on a separate part of the process. Each stage works on a separate part of the process, allowing multiple inputs to be processed simultaneously. So here, right, from minute 6 to 9, multiple inputs are getting processed, right? Sandwich 1, what is happening to sandwich 1? Packing is happening for sandwich 1. What is happening for sandwich 2? Butter and filling is happening for sandwich 2. What is happening for sandwich 3? Cutting of the bread is happening for sandwich 3. So parallelly, a lot of things are happening between this 6 to 9 period, right? So that's why it is telling here that we are doing process simultaneously. Okay. So here task is divided into multiple sub operations. All segments operate parallel except during the first time. Okay. The first time this sandwich 1, the pipe has to be filled, right? Except for the first time, each stage operates parallelly. Okay. So except initially when the, just hold on, except initially, okay, I think my spelling is also wrong. When the pipe gets filled, so it takes some time to get filled, right? Except that every stage like it processes simultaneously. Okay. So increases efficiency by overlapping tasks. So here, like, tasks are overlapping because from this minute 6 to 9, period 6 to 9, multiple tasks is happening. This is doing packing, this is doing butter filling, this is doing cutting. So multiple tasks are happening simultaneously. That's why we do overlap, but not of same task, because this person A can only cut one bread at a time. It cannot cut two breads at a time. So it has only two hands. So I only give it the task of cutting, but one bread at a time. So that's why it increases efficiency by overlapping tasks, the different task. Okay, the different task. This improves the system throughput. What is system throughput? The definition of system throughput, we will understand this in today's lecture. Don't worry about this. So what is happening here? Generally what we do is, like in instruction pipelining, I have multiple stages. So let's say I have 4 stages. So each instruction I1 will come here. Then there will be one buffer register that stores the instruction, right? Or the operand. Then instruction phase happens and it processes that stage, like that stage has been processed. Then it doesn't, we directly don't feed it to the next stage. What we do, we keep it at a buffer register. Why? Due to this, right? Due to this differentiating, due to this maximum. Because person A has finished, he has finished his task. He will say, I have finished his my task, I want to send. But person B won't allow to receive, right? Because he hasn't finished his sandwich 1 yet filling. So what we do is, we have a placeholder. We have a register. When as soon as person A finishes, he finishes his task in 2 minutes only, but we place it in buffer register. Okay, we place that finished task in buffer register at a plate. Let's say at a plate, right? There is person A. I will show you the example. Where can I show the example? Here, okay. I can use a new page. Okay, so I have here person A, okay, he's cutting the bread, then I have a plate in between, right? So person A finishes his task in 2 minutes and then he keeps the bread in a plate, okay, and it remains in the plate for 1 minute. Then again what happens, I have person B, he can only take after 3 minutes, right? So he will take this bread after, like the bread has been here for 1 minute, then only it will take the bread, and again it will do some operation, like it will fill butter and all those things, and after that there is a plate, okay, but this time the bread won't stay here for much long, because that is the maximum time that I have given for each instruction, right? So what will happen is instantaneously this bread will come here and it will not stay here, and it will go to the next stage, and again it will take 2 minutes, and then again there will be a plate. Again there will be a plate here. Okay, so like this plate is just the buffer register. I just wanted to show you an example what is actually happening. The buffer register, it stores whatever computation has been done into a register, and then we pass it on to the next stage, okay, so that everything can happen smoothly, everything is in sync, everything is in synchronizing properly. Okay, so the same thing is written here only. Okay, same thing is written, this is not something different. Okay, so anyways, this is not of much use, we can delete this page. So let's take a actual computer example, and with this we'll understand this like example more better. So we have a task, compute di, it is an array, okay, let's, like, d is an array, x is an array, y is an array, z is an array. So it is only useful for similar type of instruction. So we are doing similar type of instruction for I equals to from 1 to 6. I am doing same type of instruction. What I am doing, I am taking the first element of x array and adding it with the first element of y array, then multiplying this whole thing result with the first element of z array, and then I am storing it in some d array of the first element, and I am repeating this process. I am just doing the same thing only for different datas. Datas are different, but instruction is same. So pipelining is useful only for similar types of instructions. So pipelining, although I have mentioned this, like I have repeated this many times, but still I wanted to clear this thing. Pipelining is useful for similar type of instruction. Okay, so can I break this down into sub operations? I've already in my mouth as well, I have told you, like, how can we break it down into sub operations. First, what we do, we load the data into registers R1 and R2, this xi and yi. Then we can perform the addition operation and store the result in some register R3. Then I can load this data zi into register R4. Then finally I can do the multiplication operation of the contents present on R3 and R4. Then finally I can store the result in R5. So these are each sub operations. So there are total 4 stages. Okay, there are total 4 stages. Here I think you have seen something, that instruction fetch, instruction decode, instruction execute. So this is just like how a instruction cycle is, right? So we break down our instruction cycle into 4 stages, and we use instruction pipelining. Okay, that I will come to later on. For now, just understand this basic thing, right? That we have broken down this whole instruction into smaller stages. Okay, so how can I write the micro operations? What are the micro operations? So for the stage 1, the micro operations are what? Micro operations are, I am storing the value of xi in R1 and storing the value of yi in R2, and then I am adding R1 and R2. That is another micro operation, and storing it back in R4. So R4 is getting stored by R1 plus R2, not R4, sorry, R3. Then I am loading the zi value on R4. So R4, the value is getting loaded. Okay, zi value is getting loaded. Then what I'm doing, I'm multiplying R3 and R4 and storing the result in R5. So R5 is getting stored by the result R3 into R4. Okay, so these are the micro operations that are happening in each stage. So like that is what is written. Stage 1 we load this thing, stage 2 we perform addition, stage 3 perform multiplication. Okay, and like this, right? Okay, this loading, like I have, like what we can do, we can club the things, we can also club few things if it is possible, because these two tasks, right, seemingly it depends on the architecture, but here I have taken a assumption that I can perform these two in a same stage, in a single stage, adding the contents of R1 R2 and storing it in R3 and storing the contents of Zi in R4. I can do this simultaneously, so we don't need 4 stages. So that like this also we can reduce the number of stages. So what is happening in hardware level? So this is just a pipe, right? So this is the hardware diagram actually. So what we do is, first my xi and yi will come from will get loaded into R1 R2. Then I will have a adder, and then this result of the adder will be stored in R3. And then finally what I'll do, I will like this R4 and this R3, right? This is happening simultaneously in stage 2, storage of value of Zi in R4 and this getting the result in R3. This is happening in stage 2, and then finally I am passing it by a multiplier at the final stage, which is then the result of this is stored in R5. Then obviously that is my DI. So I hope you have understood the hardware level diagram. What is happening hardware? So this is just like a pipe, right? Just like a pipe. Okay, just like a pipe. This is just like a pipe. Why this is just like a pipe? Because data is flowing in here and it is coming out of this, right? And after the first iteration, each time it will just take me whatever each stage takes the time. Okay, for like fetching a new instruction, it will not take me much time, because for the first time only water needs to come in and fill the pipe. After the pipe gets filled, it will not take me much time for the water to get out, as the water comes in from on the other side. Okay, in and out. So this is the hardware level diagram. So let's together solve. Okay, let's together solve in each stage what is happening. So what happens is, we actually perform operations according to clock cycles. So each clock cycle will perform a task in each stage. Okay, so in the first clock cycle, in stage 1 what will happen? In stage 1 I will load my x1 and y1. All the other stages will be idle, person A, B, C. Okay, so I will load here. Load my x1 and y1. Stage 2 will be simply idle. Nothing will happen, right? Because stage 1 hasn't even processed the data, so we cannot do anything in stage 2. And stage 3 will also be sitting idle. Okay, so this is just the first iteration, right? Then in second clock cycle what will happen? Second clock cycle, stage 1 has performed its task. It has loaded the value in x1 or y1. It will pass this same thing into stage 2, like this here, right? Stage 1 has performed its task. It will pass it to the stage 2. Okay, so stage 2, what is the task of stage 2? The task of stage 2 is adding x1 plus y1. Okay, addition. Then also the task and loading it in R3. Actually, this is log, right? Yeah, this is log. So adding x1 plus y1 and loading this value in R3. Also loading the value of z, that is z1, in register R4. So this is the task of stage 2 in cycle, clock cycle. This is t equals to clock cycle 1 second, 2 second. Each cycle takes 1 second, you can assume. Okay, in second clock cycle also, I will not keep stage 1 idle. Okay, stage 1 has done its job in first clock cycle. It has sent the data to the next stage. So I can simultaneously send x2 and y2 in stage 1 in the second clock cycle, because it is just sitting idle there. It has already performed loading and just send it to the next stage. So in second clock cycle, this is just sitting idle. So what I will do, I will just load x2 and y2. Okay, I'll just simply load x2 and y2. Okay, but again stage 3 will still be idle because again the previous stage hasn't processed its data, so for it to receive, right? Stage 3 will be idle here. In the third clock cycle, what will happen? Stage 3 will receive the data from the stage 2 because it has performed the operation, it has done its job. So what was the task for stage 3? The task for stage 3 was simply perform the multiplication operation and store it in register R5. So what it will do? It will do R4 R3 into R4 and store this thing in R5. Okay, so simultaneously in the third clock cycle, what will stage 2 do? It has performed this operation in the previous cycle, right? It has already performed its operation in the previous cycle. So what it will do? It will take the values of x2 and y2 and perform the same operation. It can do it because it has performed this operation in the previous cycle. So of x1, y1. So what, again the same thing will happen here, that my R3 will get loaded, okay, with x2 plus y2 and R4 will get loaded by z2. There is a problem here that will come to later on. For now, just assume there is no problem. Okay, so why am I telling you a problem? We will understand in the hazard chapter. So this is happening, right? So in stage 1, what will happen? Again, I will load my registers R1 and R2 with this, right? So what I actually, these were the micro operations. R1 was supposed to get loaded with x1 and R2 was supposed to get loaded with y1. And here my R1 is supposed to get loaded with x2 and R2 is supposed to get loaded with y2. And here my R1 is supposed to get loaded with x3 and R2 is supposed to get loaded with y3. Okay, so that is the case over here. So now simultaneously what can happen here in this clock cycle, fourth clock cycle, what can happen? Simultaneously it can actually get the perform, okay, it is okay, something is this x2 y2, sorry, I'm wrong, that's why I was wrong, right? Actually this will be here, this, right? This will be just y4 x4. Now at each clock cycle a new instruction gets fetched. Okay, this will be 4, this will be 5, this will be 6. Okay, now here also same thing is happening. I am applying operation on the previous instruction, right? So previously this has already fetched x3 and y3, so I can do operations on x3 and y3 actually. x3 and y3. Okay, so it will do x3 y3 z3, and this also is the same. Again this will come where? Here, right? This will come, this operation will happen here. So this will do R5, this is the same only, this is doing the same only. Okay, nothing different. So this is R3 getting stored here of x4 and y4. This will be 5. Okay, so like this will go on like this. I will not complete all the examples. Okay, this will go on. So what is happening? Basically, first I fetched the data here, then it came to the next stage in the next clock cycle. Then again, after operation on this next stage, then again I went to the next clock cycle, and then finally I got my output. Same thing is happening here as well. Same thing is happening here as well. At each clock cycle, my data is flowing through the next stage, right? So it's just like a pipe. Data is coming in this pipe, okay, and then the data is coming out of the pipe, okay. So that is what is happening. So this is how a pipeline works. Basically, I hope you understood with a basic example. And here I have 6 iterations. So homework is you can complete this table for 6 iterations. And as soon as I get here 6 iterations, right, the first few stages will be idle because they don't have any new data to fetch from, because I have only 6 data, right? So now let's do a basic comparison. If I would have used a non-pipeline processor here, right? Non-pipeline processing, that is sequential processing. Sequential processing. Okay, sequential processing. So if I use sequential processing, what does that mean? That means that each of the instruction will individually take its own time. Each are independent. So first of all, I will not do like this, that okay, this is currently fetched, stage 2 has this operand, so I will fetch the x2 and y2 in stage 1. No, I cannot do. First of all, these whole thing has to be finished, then only I can fetch this x2 and y2. So each are independent. So how many clock cycles each stage is taking? 1 clock cycle. My assumption is 1 clock cycle. So what will be the total time? Total time T, okay, for non-pipeline. It will be equals to what? It will be simply time taken to perform each instructions multiplied by the number of instructions. Okay, so everything is individual. First instruction will take 3 cycles. Next instruction will take another 3 cycles, total 6 cycles. Next instruction will take another 3 cycles, 9 cycles. So each instruction is taking how much? 3 cycles. And total how many instructions I have to do? How many data elements I have in the array? 6 elements, right? Total it is going from 1. It is going from 1 to 6. So how many elements I have? 6. How do I calculate the number of elements? Just remember this basic thing. To calculate the number of elements between 2 numbers, what you do? You write the final number minus the initial number plus 1. Okay? This is, remember this thing, this will be very, very helpful in future. Trust me, this will be very, very helpful. This is final. This is initial. And this plus 1 will be constant. This plus 1 will always be there. This calculates the number of elements between 2 numbers. So this actually becomes how many? 6. Total 6 instruction, number of instructions I have. So it will be total 8 cycles. Now for the same case, if I now have a pipeline processor, okay, this one, let me add a new page. That is a huge problem actually. Just hold on. There's a huge bug here. Okay, yeah. If I apply my concept of pipeline processing, then how much time it will take me? This will be pipeline processing. If I apply pipeline processing, right? So total how many cycles I will require? So for the first time, I am requiring 3 cycles. First time I am requiring 3 cycles. But afterwards, after how many cycles I am getting a new result? After 1 cycle only. So for the first time, I required 3 cycles. Okay. Then as soon as I get my first result, right? After that, I only take 1 cycle to get the next result. Okay, I will only take one cycle. So what is the significance of this 3 cycles? What is this 3 cycles actually? This 3 cycle is actually the number of stages. This 3 cycles is the number of stages. Okay. So, and as soon as I get my first instruction, how many instructions left? 5 instructions are left. Total there are 6 elements, right? Only 5 elements are left. So how many total number of cycles it will take me? Total number of cycles will be equals to, for a pipeline processing, will be equals to number of stages. So this time is taken for what? This time is taken to execute the first instruction. Okay, to complete the first instruction. To execute the first instructions. After this, I will just take one cycle for each instructions. So how many instructions are left? One instruction has already been executed. How many are left? Let's say I have n instructions. If I have n instructions, right? So like if I have n instructions, a non-pipeline system will take how much? It will be t n into tn. This is my non-pipeline. What is this tn? Tn is the time. Tn is what? Tn is the time taken to perform each instruction. Written over here, right? Tn is the time taken to perform each instruction, and I have n number of instructions. So it will be ntn. And here, how much time it will take? Here, actually, like although I have written as cycles, I can write this in terms of time as well. Okay, this is written as cycles, but time cycle, it's the same thing only. Okay. So here, what is actually happening? Like what you can do is you can also skip the number of time taken to perform each instruction. Yeah. So total each okay, because I have 18 cycles, right? Yeah. Here, what you can do? Number of stages is fine. Plus after each cycle, I'm getting a new instruction. So I will require how many cycles? Total I have n instructions. One has already been executed. How many are left? N minus 1. So it will require me n minus 1 cycles. So remember, this is the number of cycles. Okay, cycles. Let's assume that each cycle takes some TP time. Each cycle time is TP time. Some common time has been given. Okay, I have given some common time TP. So total time for pipeline. Okay, pipeline processing of the same task. It will be what? It will be, we write this number of stages. This has a notation that is k. We denote it in terms of k. K plus n minus 1 into TP. TP is the time taken for each cycle operation. So here, how many cycles we are actually requiring? Here, if you observe, I have 3 stages, and after that, how many instructions are left? Only 5 instructions are left. Total pipeline cycles, how many pipeline cycles I will need? 8 cycles. So in our example, I had 3 stages plus 1 instruction has been executed. So I have 5 instructions left to be executed. So it will be 5. This will be equals to 8 cycles. But here in parallel, in sequential processing or non-pipeline processing, it is taking me 18 cycles. So I'm saving 10 cycles. What if I tell you, you increase the number of instructions of similar instructions? What if this n increases? If this n increases, let's take an example. Okay, let's take an example. If n is 10 now, so I have 10 array size, right? Array size is 10. I'm performing the same task on 10 data points. Okay. So now how many cycles will take me? So this is non-pipeline and this is pipeline. How many cycles it is taking me? If n is 10, right, it will take me 10 times whatever the time of each cycle is. Okay, because like whatever the number of stages are. So each instruction has 3 stages, so it will be totally 30 cycles. It will be total 30 cycles. Okay, 30. But for pipeline, how many number of cycles it will take me? For pipeline, I have the first instruction will take total of 3 cycles. Fine. But then how many cycles it will take? Just 1 cycle for each instruction. How many instructions are left? N minus 1. Total I have 10 instructions. 1 has been executed. 9 I have left. That is n minus 1. That is 10 minus 1 is 9. So it will be 3 plus 9. That is 12. If I increase n to 100, how many cycles it will take me for the non-pipelined architecture? It will be 100 times the number of stages for each instruction, that is 3. Total cycles it will be 300 cycles. For pipeline, how many? For the first instruction, again it will take me only 3 cycles. For every other instruction, it will only take me 1 extra cycle. How many instructions are left? 1 instruction has already been executed out of 100. 99 and 9 are left, that is 100 minus 99, that is 99. 100 minus 1, that is 99. So it will be 102. Can you observe the difference here? This is almost 1/3, right? This is almost 1/3. This also is 1/3, but little greater than 1/3. This is almost 1/3. So I can observe the number of cycles, right, is very, very lower compared to non-pipeline architecture. So what is the difference like between non-pipeline system and pipeline system? So basically we get increased efficiency. As task increases, the pipeline processing becomes significantly faster than non-pipeline processing, as can be observed with the basic comparison, right? And performance difference. In non-pipeline processing, each task is completed sequentially, while pipelining overlaps operations, reducing the idle time and maximizing throughput. Basically it utilizes all segments, right? In sequential, what was happening? When I was going sequentially, right, first I was utilizing stage 1, stage 2 and stage 3 was idle for sequential or non-pipelined system. Then as I reached stage 2, in the second cycle, stage 1 and stage 3 are idle. But in pipeline, what do? We make stage 1 work. But in sequential, the stage 1 is idle because we are utilizing each instruction independently. Okay. So here, what we can do? Then at stage 3, what is happening? If I am using non-pipeline system, then my stage 1 and stage 2 will just sit idle in the third clock cycle. Then again this will repeat. So at each clock cycle, 2 segments are idle. So that is so much waste of resources, because these stages can work on the next instructions, right? Which have similar data, which we use in the pipeline system. So that's why pipeline is better than non-pipeline, but for only similar types of instructions. Because this instruction is same, right? I'm doing this same operation on a array of data. So this operation doesn't change. If this operation changes, then the advantages of pipeline processing will also change, because this has changed, right? So it will be not sequential anymore. Data in, data out won't be same. Just like you have a pipe for water. Okay, this is a pipe. I will just show here only. You have a pipe for water. Now you won't be using the same pipe to carry oil. Okay, pipe for oil will be separate. Okay, it will have some different thickness, all those things. And sewage, you have another pipe for sewage, right? Sewage and waste, whatever it gets, sewage. So that also will have a different type of pipes. So different types of pipes will be different, but for the same item, right? It will go through water, it will go through oil, this will go through sewage. That will reduce with pipelining. But if the instruction itself is different, right, then obviously that our advantages, whatever we have gained with pipeline processing, won't be there anymore. Okay, but still it will be same as sequential only. Okay, but still it will be better. Like if I have a pipeline system will always be better than a non-pipeline system. Okay, so that is what is written in the here, right? Pipelining versus non-pipelining. So if I see a graph, right, as I keep on increasing my number of instructions, what do I see? This is the time taken for a non-pipeline processor, okay, or the number of cycles. I see that gap, right? This gap keeps on increasing as the number of instructions get increased, right? Because in case of pipeline, the number of instruction gets increased and it is linear, so does the processing time. But in case of sequential, the number of instructions are getting increased and each instruction has 3 cycles, so it is getting increased by thrice. So number of cycle is getting increased by thrice. Here number of cycles only is incremented by 1. Okay, so that is the difference. That is the power of a pipeline processing that has been represented here by the graph, comparison of the graph. Okay, so there is a term known as pipeline cycle time. Now we are going into the technical terms of a pipeline processing. Okay, so what is pipeline cycle time? Pipeline cycle time refers to the time required for one stage of the pipeline to complete its operation and pass its result to the next stage. Okay, this cycle time is determined, this is also known as cycle time, is determined by the slowest stage in the pipeline, since all stages operate in synchronization. As explained at the starting of the lecture already, that if I have 4 segments, and each of these segments has different time, like obviously, right, for fetching the instruction, it will take lesser amount of time, let's say 5 nanoseconds. It is just fetching the instruction from the memory. Decoding, it is going into the control unit, right? It may take more time, so it is taking it 8 nanoseconds. Execute, it depends, right? It depends on the type of instructions. In our case, our assumption is execute is taking 6 nanoseconds. And write, then after I execute, the ALU has done some arithmetic operations. It needs to write back to the memory, right? So it takes 4 nanoseconds. So these are just assumption. Now, can you tell me what will be the pipeline cycle time here? Obviously, many students may think I will choose 4 nanoseconds. It is best because it is taking the least amount of time. But if I choose 4 nanoseconds, right, all these stages, stage 1 to 3, all this will not be able to complete their task within this 4 nanoseconds. So obviously I will have to choose a slower, so that all the other stages can complete its own task. It's okay that yes, if I choose my pipeline time TP, okay, TP to be 8 nanoseconds. If I choose my TP to be 8 nanoseconds, then obviously what I can say is that this stage 1, right, it will have 3 nanoseconds of idle time. 3 nanoseconds of idle time, because it will obviously be done with its own task by 5 nanoseconds. It's okay, that's fine. But obviously I cannot choose 4 nanoseconds because it won't be able to finish its own task within 4 nanoseconds. It needs 1 more nanoseconds, right? So obviously it's better to sit idle than to not finish the task itself, right? So that is what our aim is. So we write this as TP clock, we write. Okay, so what we do is like this, right? This is what, if you know, this is basically a instruction cycle, right? Instruction cycle. So what we'll do, we'll utilize each instruction and we'll process them using pipeline. So although this execute, right, this execute is different, but each instruction has this 4 types of stages, mostly 4. It may depend. Okay, we'll see more examples, we'll understand that. But mostly they have 4 to 5 things only. First, it fetches the instruction, then it decodes the instruction, then it executes the instruction, then it writes back. Okay, if there is a memory read, memory write, all those things are there. If I need to fetch the operands as well, that will take some extra stage. That is for a separate discussion. But mota, basically, they contain this number of stages. Okay, so they're containing 4 stages, and I can use my concept of pipelining in this instruction cycle. Okay, so that is what we do. We use the concept of pipelining in instruction cycle because all instructions will have similar type of stages only, mostly. Okay, just the execution will change and the decode, internally things will change on depending on the operands and the instruction, but these 4 stages will be similar only. Okay, so what will be pipeline execution time? Already we have computed it, right? So if I have n task and I have k segments, right? So for the first, how many cycles it will take? How many cycles it will take for the first instruction to totally execute. It will take it k cycles. Then how many cycles will it take to execute the next remaining instructions? Total I have n tasks. Already I have finished my one of the n task. So how many tasks are left? I have n minus 1 task. So it will be plus n minus 1. So this is the number of cycles that the pipeline processor will take. But what is the pipeline execution time? I know this is the number of cycles. I know how much time does each cycle consume. So if I just simply multiply this by TP, I will get my pipeline execution time. So this will be multiplied by TP. So this will give me the pipeline execution time. So TP execution. TPX. Okay. TPX is the pipeline execution time. Now, obviously you can remember this, but if you understand this conceptually, you don't need to remember. First, if you this tells everything about pipeline processing. This first letter tells me that how many number of stages I have. So I finished the number of stages. So one instruction has been done. Next, remaining n minus 1 instruction will take how many cycles? Same number of cycles. Number of instructions will be equal to number of cycles, that is n minus 1 cycles, because at every cycle I am getting a new I'm getting the result of a new instruction. So this is the total number of cycles that I have already derived as well. And this is the time taken by each cycle, pipeline cycle time. And this will give me total execution time. Very simple, right? And in a non-pipeline processors, every task is executed sequentially. So here, I know many students get confused that this TP and they confuse with this TN. This TN and this TP are different. Sometimes they can be same, but mostly you will assume it to be different. Okay. What is TP? TP is the pipeline cycle time. That is time taken for the pipeline to complete each segment. Okay. Each segment. And what is TN? TN is the time taken to perform single task for a non-pipeline system. Now, how do I understand the difference? With example. Okay, with example I will understand. But first, let us derive the formula. So here, right, this will be TP execute. Okay, and this will be TNP non-pipeline execution time. What will be this? Just write this. Just the notation can be more better. So non-pipeline, right? Each instructions. To perform each task, I require Tn amount of time. If I have n number of tasks, so how many tasks I have? N tasks. So how much time will it take me? It will take me n times Tn. Okay. Now what is the difference between Tn and Tp? I will tell you now itself. What is the difference between Tn and Tp? Okay. For some reason this got generated here. That is bad. This won't let me come here actually. Yeah. This will be okay. That is bad. It's some weird bug this is having actually. Sorry, just hold on, give me a minute. Okay, this won't let me do it. Okay, so some weird bug we have. Okay, so where is it? So what I can say is, if I just take the example of this case, right? If I just take the example here, I have already told you what is my TP. Let's say my number of tasks is 10. If n is 10, okay. Let's take example. N is 10. So if n is 10, then what will be my T execute for a pipeline system? How many stages I have? 4 stages. Stage 1, stage 2, stage 3, stage 4. 4 stages I have, plus n, total number of tasks is 10 minus 1 into cycle time, pipeline cycle time. So what should be the ideal? Obviously you can choose higher cycle time than this, but you cannot choose lower cycle time than this. This is a minimum 8 nanoseconds that you have to at least give for all the stages to completely perform properly. You can choose higher, you can choose 10 nanoseconds, that's fine, but your system will be slower. So obviously we'll choose the minimum best one, 8 nanoseconds. So pipeline cycle time will be 8 nanoseconds. So this is actually 13 times 8. So that is 24 and 10. So it is 104 nanoseconds. Okay, for the pipeline system. Now if I have a non-pipeline system, same example, n is equals to 10. What is my Tn now? What is the definition of Tn? Definition of Tn is the time taken to perform single task for a non-pipeline system. So what will be the time taken to perform a single task, right? The stage 1 will take 5 nanoseconds. So after 5 nanoseconds, I can directly go to stage 2 because it doesn't have any foundation that stage 2 is currently performing some other task. No, everything is independent. Everything is happening sequentially. So I can, after doing this operations, fetching the instruction, I can directly give it to stage 2 because it is ideal. It is already free. Everything, only one stage works at a time. So this stage 1 has happened. So 5 nanoseconds has gone and instantly I gave it to the stage 2. Then after 8 nanoseconds, then again I instantly gave it to stage 3. So total how much time I consumed? 5 plus 8, 30 nanoseconds. Then this consumed total 19 nanoseconds. Then again I instantly gave it to the stage 4, that is, it will again consume 4 nanoseconds. So how much time I will take? It will take total 23 nanoseconds. So each instruction takes 23 nanoseconds, and after that, after finishing only this, again I will give the next instruction. It will again fetch that. So each instruction takes 23 nanoseconds. 23 nanoseconds. Each instruction takes 23 nanoseconds, remember. So how many, like, and they totally independently do the computation, right? So how many number of instructions I have? 10, right? So total execution time will be what? Tn non-pipeline execution will simply be 10 times 23 nanosecond. It will be 230 nanosecond. So I hope you have understood the difference between Tn and Tp. It is not necessarily true that always my Tn will be equal to Tp. As we go along, as we move along the subject, you will understand that sometimes Tn is equal to Tp, and then there only the confusion arises. The Tn will always be equal to Tp. No, it will not always be equals to Tp. Tn is not equal to Tp in most cases. Sometimes they will be, but most cases they will not be equal. Okay, so I hope you have understood the difference. It is taking me 230 nanoseconds and this is taking me only 104 nanoseconds. So half the time. I am saving 50% of the time. So there is a metric to compute how much time am I saving. So that is what is my speed up ratio. Okay, so this should be speed up ratio actually. Speed up ratio is nothing but the ratio of two execution times of a non-pipeline system over a pipeline. So what it does is it measures by how much factor I am faster. Okay, that is what my speed up measures. It's just a metric. It just computes that. What is the difference? So how do you remember which one will be at the top and which one will be at the bottom? Always remember that your speed up ratio will always be greater than 1. Okay, speed up ratio will always be greater than 1. Why? I will explain that. So not always actually, not always. Okay, no. Always remember that you want your speed up ratio to be as high as possible. You want your speed up ratio to be as high as possible. If you want your speed up ratio to be high, so the top one, right, should have a higher number. So execution time, right, of a pipeline system, most cases is always lower. So obviously lower number will be at the denominator and the higher number will be at the numerator. So lower number will be at the denominator and the higher number, because execution time of non-pipeline system will always be higher. So now can I derive a formula? No need to remember the formula. Okay, you can always derive the formula for the speed up ratio. So very interesting points will come out here. So first point is, if I want to write my speed up ratio, right, what would be my speed up ratio? It is execution time of non-pipeline system. What is the execution time of non-pipeline system? I have already told you that it is n times Tn. I have already defined what is Tn, what is n. I will not define here again. And what is execution time of pipeline system? It is k plus n minus 1 into Tp. Okay, remember this is the actual formula. Okay, this is the formula, this is the main formula. Okay, if you want to remember, you can remember. But sometimes what we do is, our number of instructions is very higher than the number of stages. Why? Here only we can see, right? If I have chosen, like here only, here I was choosing number of stages to be 100. Sorry, number of tasks to be 100, and number of stages were merely 3. So very high. Generally that is the most cases. What will happen is, then what we do is we make our n to be very higher than k. That is, number of tasks is very higher than number of stages. Okay. So if n and k are given, you will use this formula of speed up ratio. If n and k both are given, you will use this. So I will write here, if both n and k are given. Now, if for some reason they haven't given you n or k, then what you will use? Then what you will do? Then what you can do is this. You assume n to be very larger than k if they haven't given you n and k. If n is very larger than k, right? So what will happen is, this k minus 1 I can ignore. If I am doing 10,000 plus 3 minus 1, can I ignore this 3 minus 1 too from the 10,000? Yes, I can. So basic limits concept, right? So I will ignore this. So then what I will get is, my speed up ratio will approximately become ntn divided by ntp, which will be approximately equals to tn by tp. Okay, that is what it will come to. Now, if I have a balanced pipeline system, okay, balanced pipeline system. So I will tell here, for a balanced pipeline system, each stage will take same time or cycles. Okay, so that means what? That means if this is a balanced pipeline system, right? So each stage will take same time. So if this is 5 nanoseconds, all the other will be 5 nanoseconds. So if it is balanced, right? If I want to convert this into a balanced pipeline system, then my S1 stage 1 will be 5 nanoseconds. Just a assumption. Stage 2 is 5 nanoseconds. Stage 3 is 5 nanoseconds, and stage 4 is also 5 nanoseconds. Now, if all the stages are 5 nanoseconds only, then what can I say? Then what will be my Tn? Tn is basically sum of all the stages, right? Time of all the stages. Sum of time of all the stages from I equals to 1 to I equals to k. If it is a balanced, right? If it is a balanced, then each stage time period is what? This is also known as TP, right? This is also known as the TP. As it is balanced, it will also be called as TP. Everything is same. So I will choose TP to be this 5 nanoseconds only. Correct? So this can be written as simply TP plus TP plus TP k times, right? K times. This will be equals to what? K times TP. Okay? This becomes K times TP because TP is same and it is a balanced system. Only valid for a balanced system. So my Tn actually will become Tn. Generally the formula for Tn is, here I will write the formula. I will write everything at once here. Formula for Tn generally is basically the whatever I have written at the top, that is sum of the time taken of all the stages. Okay, and I equals to 1 to k. Okay, k is the number of stages. But if Tn is also not given, right? Then what we can write is, for a balanced system, I told you this. So for a balanced system, my Tn will become what? My Tn will become what? My Tn will actually become K times TP, just proved at the top page. Okay. So what will be my speed up ratio? What will be my speed up ratio? So my speed up ratio will become S. It was NTN divided by NTP. NN gets cancelled and TN is equals to K times TP, right? TN is equals to K times TP. So it becomes, it was NTN divided by NTP and NN gets cancelled. So this is KTP divided by TP. So it becomes K. So my S becomes K. And when will this happen actually? This actually has a name. What is the name of it? The name is S ideal, also known as ideal speed up ratio. Okay, ideal speed up ratio. So this is not ideal pipeline time, this is ideal speed up ratio. So this is ideal speed up ratio, right? What does it mean? What does it signify? If my n is very, very large, then obviously the number of total execution time, right, will almost be equivalent to n only, n cycles only. It will not be equals to n plus k minus 1 because n is very, very large. So as I increase my n, we reach an ideal state where it is like the number of cycles taken will be n plus k minus 1. So that's why it is known as ideal speed up ratio, because we can never reach it. This assumption is, what is the assumption? Assumption is n is very, very greater than k minus 1. That is my assumption basically. So that's why this is known as ideal, because we idealize many things in under ideal conditions only this will happen. And obviously this formula is only valid for a balanced pipeline system. Balanced pipeline system. So sometimes what will happen, gate will give you question on this. Okay, so the few criteria have to be met, then only you will be able to write your speed up ratio directly equals to k. Else you will not be able to write your speed up ratio equals to k. Assumption is that if I want to say you practically, right, what is happening is the assumption here is that my pipe, right, this pipe is actually already filled. That's why my n is greater. That's what the physical significance of n greater than k minus 1 is. Pipe is already filled, so all stages are already working parallel. Okay, so pipe is already filled, so I am instantaneously getting some output whenever I am giving some input. So that is the assumption that we are telling, that this is my ideal speed up ratio. Ideally this should be the maximum. My speed up ratio, remember, my speed up ratio, actual speed up ratio will always be less than S ideal. Okay, my speed up ratio will always be, just hold on, less than S ideal. So this is how you can verify whether you have solved the question correctly or not. If you're like, you can always compute the S ideal. S ideal will always be equals to k. Also S ideal, right, there can be two ways to go about it. Sometimes S ideal can be equals to this, or S ideal can be equals to this as well. Okay, there are two things here, do remember, can be equals to Tn over Tp. Okay, so remember, like generally we choose this as S ideal only whenever Tn and Tp are given. So if you are able to find out Tn and Tp, how do you find out Tn and Tp? So this you will use when the pipeline is unbalanced. Pipeline unbalanced and TP and TN are given. TP and TN are given. Okay. So what is TP basically? TP generally you will look for the word as cycle time. Cycle time. That is what my TP is. And what is TN? TN is basically sum of the number of stages, right? Each stage, how much each stage time it will consume for I equals to 1 to I equals to N. That simply, not I equals to N, sorry, that I equals to K. That's simply it. Okay. So that is what my TP and TN are. So with the help of this much knowledge, can we solve few questions? So we'll solve the first question, first numerical. A non-pipeline system takes 40 nanosecond to process a single task. So what does this information give you? It gives me the information about TN. To process a single task, it takes 40 nanoseconds. So TN will be equals to 40 nanoseconds. Next, let's read the question. A pipeline system with 5 segments. Whenever segments, number of segments is given, what does number of segments signify? That is equals to my key. That is equals to 5. And a clock cycle of 8 nanoseconds. Whenever they say clock cycle, right? This is a clock cycle. Assume this to be your TP. TP is the like time taken for each cycle to occur. Okay. So clock cycle is this. You will assume this to be TP only. Next is used to process the same task. Okay, it is used to process the same task. Calculate the speed up ratio of the pipeline system for 120 tasks. Additionally, determine the maximum speed up achievable by the pipeline system. That is ideal speed up. Okay. So first I will calculate the speed up for n equals to 120. So formula I know, or I can directly write all the things. What is speed up? Speed up is the execution time of a non-pipeline system divided by the execution time of a pipeline system. What is the execution time of a non-pipeline system? It is n number of tasks into time taken to execute individual tasks divided by what is the total time taken by the pipeline system to execute the same number of tasks. It will be k for the initial task. It will take me k number of cycles plus number of how many tasks are remaining, n minus 1, and how many cycles I will require, same number of tasks. It will be n minus 1 into time taken for each cycle, that is TP. N is simply 120, Tn is simply 40, K is simply 5. It is a 5 segment pipeline system. N is again 120 minus 1 into TP. TP is 8. So this will be 120 into 5 divided by the 124, yeah. Okay. So this will be simply 4 into 30. Okay. 4 into 30 divided by 31 into 5. So what will it come out to be? So I can quickly calculate. Just hold on. Quickly calculate. It will be equals to 30 divided by 31 into 5. So it will be 4 point speed of ratio, right? That I have gotten. It is 4.8387. And what is S ideal? S ideal will be when my number of tasks is very, very high. S ideal is when my n is very, very larger than k minus 1. So S ideal in this case will be simply almost equals, if n is very, very larger than k, right? So this also will be almost equals to n. So it will be Tn by Tp, right? Tn by Tp. So this will almost become Tn by Tp. So Tn is simply what? Tn is 40, right? Tn is 40. Tp is 8 nanoseconds. So 40 by 8 simply becomes 5. So S ideal will always be larger than S, like what do you say, S calculated, right? And this also is equals to the number of stages But it is not necessarily always this will be the case. This will not necessarily be the case. Here this is equals to number of stages. If S ideal is equals to number of stages, then what we can accomplish from that is it can be a balanced system. It can be a balanced system. I cannot say surely. Why? Because if I have 5 segments, combination of 5 segments, each can be 8 nanoseconds. That is also possible. Or one can be 9 nanoseconds, other one can be 7 nanoseconds, and all the others can be 8 nanoseconds. That is also possible. So it is not always that it will be a balanced system. I cannot comment about that. What I can comment, it can be a balanced system. But if this S ideal is not equals to my number of stages, number of segments, if my S ideal is not equals to K, that is number of stages, what I can comment, I can confirmly say that the system is not a balanced pipeline system, right? It is not a balanced pipeline system. Okay, so that is the important point that I wanted to take away from this. And many educators, they don't teach. Even CS guys, trust me, even CS guys don't know about this. They just know the formula, they just mug up the formula and just put in the question, and their question gets solved, and that's it. They don't understand conceptually what is happening. So there is another term that I have been talking about from the starting of this lecture is throughput. So now we'll understand the definition of throughput. Throughput is what? Throughput is a number of tasks completed per unit time. If you remember, previously I told you that many stages were sitting idle, many segments were sitting idle during sequential execution, okay, of series execution, right? But in pipeline, all the stages are actually happening simultaneously, okay? All the stages are happening simultaneously. So throughput has increased because I am performing more number of tasks in the same amount of one single cycle. In single cycle in pipeline, I was doing 3 things, right? That making of bread example. But in sequential, at a particular time per unit of time, I am only performing one task. Okay, everything is happening series. So in case of a pipeline system, what can I say about the throughput? Can I talk about any formula? Yes, I can. Obviously, you can formula everything, but basic definition you should know. This much is enough. Then you can derive the formula in the examination hall as well. It is equals to number of tasks by total time. So how many tasks am I accomplishing in time? So let's say I am performing n number of tasks. N task. I am performing n tasks. And what is the time taken to perform this n task? It is, if you remember, it is k plus n minus 1 into TP. So just taking the ratio will give me throughput. That's it. So if I just take the ratio throughput, it will be n tasks divided by total time taken, that is k plus n minus 1 into TP. So that is throughput. You can derive a formula, or it's totally time fine, right? Now assumption is if my n is very larger than k, right? If n is very larger than k, again I can ignore this k minus 1 here. This will become n by n into TP. So overall this becomes what does my throughput become? Throughput becomes 1 by TP. That is what is written in the next page actually. Okay, here I have added extra pages that are actually not required. So that is what is written over here. If my n is very larger than k minus 1, then my throughput becomes 1 by TP. That's it. Okay, that's it. Basic information that you should know. But basic definition of throughput you should know. That's it. From there you can derive this formula. No issues. Okay. So what are the factors that affect my speed up? There are many things that can affect my speed up, right? So first thing is hazards, like data dependency, control dependency, or structural issues can reduce speed up. We'll understand hazards after understanding synchronous pipelining. Okay, we'll understand this. Don't worry. What are hazards? We'll understand. But that they can affect my speed up. So we want our speed up to be as near as ideal speed up, right? We want it. But sometimes this can cause the speed up to be lower. Basically, overall, it causes the execution time of pipeline system to be more higher. Okay. Uneven stages increases the cycle time, lowering the throughput. So if I have uneven stages, right? If I have uneven stages, so what will be my pipeline cycle time? Pipeline cycle time will be the maximum of everything, right? So what is happening here? My TP, I know my throughput is inversely proportional to TP, and my TP is what? My TP is the maximum of times of all the stages, right? Stage 1, TS2, and so on. So obviously, if I have uneven stages, and like if let's say stage 1 is 7 nanoseconds, and the stage 2, all the other stages is 3 nanoseconds. So just due to this single stage 1, I have to give the cycle time. I have to give all the other stages as well 7 nanoseconds. So the number of tasks that I am performing per unit time, per unit cycle time has reduced now, because TP has increased. If TP increases, my throughput will reduce as it is inversely proportional. Okay, that is the basic thing that we wanted to talk about here. Setting up the pipeline and managing tasks introduce delay or overhead. So doing all these things, right? This also is a headache, because you have to manage the tasks, and sequentially there can be few hazards. What type of hazards? To manage those hazards also, it will cause some delay, and those delays are known as overheads. Okay, we'll understand what delay they can cause and what type of problem is there in pipeline processing. Obviously, if you are getting so many good stuff, there will be some disadvantages. Everything has some advantage and disadvantage. It depends what advantages you want and what disadvantages you don't want. Okay, then you choose that particular architecture. How do you optimize? Adjust the design so that no stage is significantly slower than the others. Okay, so all the stages are balanced, because here I just showed you one case. If stage 1 is 7 nanosecond and all the other stages are 3 nanosecond, just due to the stage 1 I have to provide 7 nanoseconds to all the stages. So all the other stages will set ideal for 4 nanoseconds. That is waste of so much time. So we don't want our stages to be unbalanced. We want them to be balanced. Use parallel techniques to handle bottleneck. We'll understand this later on. Don't worry. We incorporate techniques like super pipelining or dynamic scheduling to optimize performance further. So this is not in our syllabus. These are just few theoretical points that you should know. Okay. Main thing is we have to balance the stages. That is the main thing. Now there is another term known as latency. Now what is latency? Latency is the time required to process a single task. How much time does it require to process a single task? So my assumption will be that I am calculating this latency when my pipe is fully filled. What does it mean? That means I will write here, I am calculating the latency when my pipe is fully filled. So what is this? This means technically what does it mean? It means n is very greater than k minus 1. N is very greater than k minus 1. Okay. So if n is very greater than k minus 1, how much time does it require me to process a single task? If I go back to our starting example, if I go back here, right? What was you observing? After, even if n is not very greater than k, right, then also it will work. After every cycle, I am getting the output of a single input, right? After each cycle, I am getting output. So how much time it required me to process it a single task? One cycle. After each cycle, I am getting output. So after each cycle, I am getting an output of the task. The task has been completed. So how much time did it take me? One cycle. Okay. So latency will be one cycle. So if my n is, even though if my n is not very larger than k minus 1, then also it is okay, right? So just not very large. Okay. just my pipe has to be fully filled. When my pipe gets fully filled, when my n is greater than k minus 1. That's it. After fetching the first instruction, right? After fetching the first instruction, it's done. It is done, correct? So that's it. So latency for a pipeline system, right? Latency for a pipeline system it will be simply TP. But what about latency for a non-pipeline system? To process a single task, how much time is it requiring me? Okay, it is requiring me n times tn, right? Not n times, so tn, because each task takes n tn time. So for a non-pipeline system, the latency will be tn. For a pipeline system, the latency will be tp. So you can write the speed up as a ratio of latency of non-pipeline to the latency of a pipeline system. Okay, so you can write that as well. So now you can come to synchronous pipeline. What is synchronous pipeline? It is nothing but what we have studied. That's it. Just it has a name known as synchronous pipeline. So synchronous pipeline is a type of pipeline where all the stages are synchronized to operate using a common clock signal. So what we do is we choose a common time period for each stage, right? What we are doing? We are choosing the maximum time, right? For each stage, like I'm just computing the time taken by each stage, and then I'm choosing the maximum out of those stages. I'm choosing a common time, right? So that is what it is doing. It chooses a common clock signal, that is a common time. So TP, but generally what we do is in synchronous pipeline, TP is the maximum of time of all the stages, correct? Each stage of the pipeline performs its operation in a fixed time interval known as the pipeline cycle time. So like although we have already known it, okay, I've already solved a question using this concept only, that pipeline cycle time. So each stage will complete its task within the pipeline cycle time. Okay, each stage completes its operation within the pipeline cycle time. Registers are placed between stages to temporarily hold data and maintain synchronization. So we place registers here, okay, as explained in the starting slides as well. If you have seen, there were registers. What they do, they just store the data, because actually internally what will happen, this stage, right, will finish the task, let's say very earlier, let's say in 2 nanoseconds, but my pipeline cycle time is 5 nanoseconds. So we don't want to keep that data here. Whatever result it has done, we don't want to keep it here. We want to store it in some register. From there we will take it. Okay, so the data is will get stored at the register at 2 nanoseconds, and then I will wait, and then finally at 5 nanoseconds this data will be given to the next stage. Okay, so that is what we do. This is also known as this intermediate like buffers. Okay, registers are also known as intermediate buffers actually. Intermediate okay, this registers add a small delay, because obviously I'm storing the data, then again I'm sending it back, so this will cause some delay. That is also known as a register delay. That will be included. This will be included in the pipeline cycle time. So our TP after this register delay, our TP will be what? This will be equals to maximum of each stage time, whichever will be the highest, plus the register delay, obviously. That we have to consider, because let's say one stage takes 7 nanoseconds. All the other stages take 3 nanoseconds only. One stage takes 7 nanoseconds. It will have some also delay, right? To store it in data, then again to take it back from the register. So let's assume the register delay is very small, 1 microsecond, or it's generally very small. Okay, so we will add it. So our final cycle time TP will be maximum of this plus the T delay. So just this thing that you need to keep in mind. Okay, so that is what we do. So why are buffers required? So I have told here as well that the buffers are required to synchronize. That is the task of synchronous pipeline, right? Buffers are used to synchronize the pipeline stages. They store the data, hold the data, then again when it is required for the next stage, they give it back. For synchronization, I can write here simply synchronization, okay, of the pipeline system. Okay, so just remember, they will only be used in a pipeline system. Buffers will not be used in a non-pipeline system. Buffers will not be used in a non-pipeline system. Why? Because the reason that we kept buffer was to synchronize everything, right? That was the main reason that's why we used buffers. Synchronize what? Synchronize stages from pipeline. But in non-pipeline system, we don't need synchronization, because as soon like each task is operating separately. We don't like my stage 1 is not doing some task and performing some task, and then again at the next clock cycle stage 2 is performing some task, and like stage 1 is also performing some task. It doesn't happen in non-pipeline system. In non-pipeline system, only one stage performs a task in a complete cycle. All the stages don't perform, so it's okay. We don't need a buffer to temporarily hold the data and then give it back to the next stage. What I do, as soon as I perform some task in the stage 1, I instantly give it to the next stage. I don't need to hold and then give it back to the next stage, because the stage 2 at that point of time is not doing anything. It is just idle. It is waiting for the stage 1 to give it to something. So it's totally fine. Right? So we don't need any registers or buffers in a non-pipeline system. That is the important point that I wanted to tell you here. Okay. So like what was the formula? General formula for TP. Just remember these two things. TP, it will be maximum of all the segment delays, whichever one is maximum, plus my delay of the register, buffer delay. I can write this better. Buffer delay. Okay. And what will be my non-pipeline time? Non-pipeline time will be summation of all the segment delays. So let me take an example here. So if let's say I have 4 segments, so k is equals to 4 and ts1 equals to 2 nanoseconds, ts2 equals to 3 nanoseconds, ts3 equals to 4 nanoseconds, and ts5 equals to 1 nanosecond. Okay, and my buffer delay this is not ts5, sorry, this is ts4. Buffer delay TBD is equals to 0.5 nanoseconds. So what will be TP here? So my TP, like here also, okay, I have already given an example here. Okay, this example was already there. Anyways, okay, we had 1, 2, 3, 4, 3 stages. I can give this. I will take this example. So here, what will be my TP? TP will be maximum of all the segment delays. That is this 3, 4, 1 and 2. What is the maximum? Maximum is this, right? 4. So it will be TP will be equals to, in this case, TP will be 4 nanosecond plus obviously the buffer delay will be there to synchronize everything. 0.1 nanoseconds. So it will be 4.5 nanoseconds. What is my TN here? TN, right? I don't need buffer here. I don't need buffer. Now you might say, why am I not adding buffer delay for all of the stages? TP is what? TP is the cycle time of one stage, right? So that's why in one stage only one register delay will be present. That's why we only add it once. In TN, I need to add all the segment delays, but I will not include buffer because for a non-pipeline system, we don't have buffer. So just I will add all the segment delays. So it will be 2 plus 3, 5 plus 4, 9 plus 1, 10. So it will be 2 plus 3 plus 4 plus 1 equals to 10 nanosecond. That's it. That is how you compute TP and TN. Okay, I hope you understood this point. Your TN will always be sum of all the segment delays. Excluding this, I should write excluding the register delays obviously. So we, for a non-pipeline system, we will not use registers. Okay, this is the important point that you should know. Okay, so yeah, that is what is here. That is what my synchronous pipeline is. Okay, so one more thing is that if the system is balanced, then my TN will be equals to what? TN will be equals to KTP if all segments are balanced. Balanced meaning all segments have same segment delays. Pipeline balanced, all segments have same delay. And just one more information, if you are using a pipeline system and there is register but they haven't given the delay of the register, then what you will assume? You will assume register delay to be 0 if nothing is mentioned about the delay, right? You assume it to be 0. Generally it is very low. Okay, so what I wanted to do is do few questions. So I wanted to do a few questions, and in the like after you take the screenshots, okay, you try to attempt and tell me your answers in the comment below. Write down in the comment below your answers and check, tally your answers with my answers. This is the first question. This is the second question. Third, then this is the fourth one. Just take a screenshot and try to attempt and then tally your answers with mine. Okay, fourth, this is 72nd, right? Yeah, fourth, then fifth, then sixth, then seventh, then 8, then 9. Okay, this is the last one, 8 one. Okay, you try to attempt all the questions and now I will come back with all the solutions. Let us do this first question. So we have a 5 segment pipeline with segment delays 8 nanosecond, 10 nanosecond, 7, 9 and 11. So I will write that down, that my K is equals to 5 and my TS1 is 8 nanoseconds, my TS2 is 10 nanoseconds. Okay, just hold on. TS2 is 10 nanoseconds, TS3 is 7 nanoseconds, TS4 is 9 nanoseconds, and TS5 is 11 nanoseconds. Okay, so what we have to we have to determine the total processing time for 800 tasks. So here my n is equals to 800. Using the pipeline system, also calculate the speed of the pipeline as compared to the corresponding non-pipeline system for same number of tasks and compare it with the ideal speed up. So first of all, I will calculate the execution time of a pipeline system. T P execute. Correct. So this will be equals to what? This will simply be equals to, like I already know that to perform the first task it will take me k cycles. To perform the other n-1 task it will take me n-1 cycles into TP. So what will be TP here? They haven't not mentioned register. So my TP will be equals to max of TS1, TS2, TS3, TS4, or I can directly write it instead of doing this: 8, 10, 7, 9 and 11 nanoseconds plus the delay of the register, but no delay has been mentioned, so I will assume it to be 0. So my TP will be maximum of this, that is 11 nanoseconds. So what will be my execution time? It will be k is 5 plus 800 minus 1 into 11. So it will be 804 into 11. So it will be 8844 nanoseconds. Okay, or this can be written 8.844 microseconds. Now what about the non-pipeline system? If I have a non-pipeline system, how much time it will take me to execute the same number of tasks? So T NP, capital NP EXC, it will be simply n times Tn. Now what is Tn? Tn will be sum of all the stage delays, right, or the segment delays. It is 8 plus 10 plus 7 plus 9 plus 11 nanoseconds. So this becomes 20 and this becomes 25. So this becomes 45 nanoseconds. So n is how much? 800 into 45 nanoseconds. So 45 into 800, this is 36 000 nanoseconds, or I can write 36 microseconds, right? And what is the speed up? Speed up ratio S will be simply higher by lower, right? So higher, what is higher? Higher is 36, that is n non-pipeline execution time divided by the T pipeline execution time. Okay, so this will be equals to 36 micro divided by 8.844 micro. Everything is in microseconds. So this will be into almost equals to 4.07. okay, this is the speed up ratio. This is the actual speed up achieved. Now what is the ideal speed up ratio? S ideal, right, will be when my n is very greater than k minus 1. So then what will happen is the speed up will approximately be equals to Tn over Tp. So it will be approximately equals to Tn is how much? Tn is 45 and Tp is 11. Correct? All this in nanoseconds. So it will be 45 upon 11. So this will be 4.09 ratio. Okay, so our ideal is this. We are very close to our ideal, but it is not greater than that. So obviously we cannot go beyond our ideal speed up ratio. So I have compared my ideal speed up and like speed up achieved. Okay, this is also a term known as pipeline efficiency. Pipeline efficiency is speed up achieved by speed up ideal. Okay, how much closer I am to my ideal speed up. Okay, so the pipeline will be more and more efficient. Let's do the next question. So in this question we have the following 4 processors. Assume that the pipeline register has 0 latency, basically they don't have any delay. Then which processor has the highest clock frequency? What is clock frequency? What is clock frequency? Clock frequency, if you remember, f clock is basically 1 by clock time period, right? 1 by t clock time. Frequency is just the inverse of time period. What is t clock? T clock is the TP, right? Because it is known as the cycle time of the pipeline cycle time. So they are telling me which one has the highest clock frequency. So they are asking me which one has the highest clock frequency. That means which one has the lowest clock time period or the lowest pipeline time. Okay, so which one has it actually? So obviously my pipeline time, how do I determine the pipeline time, pipeline cycle time? I choose the maximum of all the stage latencies. Latency meaning delay. So here for the TP1, what will be my cycle time? TC1, it will be what? It will be maximum of all of this, that is maximum is 2 nanoseconds. Here as well maximum is TC2 is 1.5 nanoseconds. Here as well maximum how much? It is 1 nanoseconds. TC3 is 1 nanoseconds. Here maximum is 1.1 nanoseconds. TC4 is 1.1. Now out of this 4 I have to choose the minimum. Which one is the minimum? This third P3 processor. So here like it's very simple, right? Very simple. Don't do it using very difficult maths or something. Processor 3 will have the peak clock frequency. Okay, as its time period is the lowest. Okay, so let's move on to the next question. These are all very simple questions. You also will be able to solve it. So here we have like a instruction pipeline with 4 stages, each with combinational circuit delay. So each stage has delays. Okay, and also it has a pipeline register which delays 1 nanosecond. They are provided as a delay. So now the delay comes into the factor. Okay, now each stage has like separate delays. Okay, so what are they asking us? The pipeline registers are required between each stage, and at the end of the last stage, delays for the stages at the end of the last stage, delays for the stages and for the pipeline registers are given as what? Are given in the figure. What is the approximate speed up of the pipeline in steady state under ideal conditions compared to corresponding non-pipeline implementation? Okay, very interesting question. They're asking me steady state under ideal conditions when compared to non-pipeline implementation. So in nowhere they have given me the number of instructions or number of tasks. So what I will assume obviously they are telling me ideal, so my assumption will be n will be very greater than the number of stages or segments. Okay, so what does my speed up ratio then become? My speed up, if you remember it very well, if you don't remember, you can directly write it is the execution time of non-pipeline system over a pipeline system. What is the execution time of a non-pipeline system? It is n times tn. I can write directly as well. It will be tn times tp, but still I want to write it in front so that you don't think that I am just mugging up the thing. Okay, so it is k of a pipeline system. What is the execution time? K plus n minus 1 into tp. So this my n is very higher than k. N is very higher than k minus 1. Okay, so if n is very higher than k minus 1, then my ideal speed up approximately becomes Tn over Tp. Okay, it approximately becomes Tn over Tp. So we have to find out Tn and Tp. So first let us find out Tp. That will be the easier one. Tp will be what? Tp will be maximum of all the segment delays. Okay, so this is 5, 6, 11, 8. So 5, 6, 11 and 8, plus obviously I have taken into consideration the register delay. Now register delay will not be different because it's the same register, right? It is not doing something different. It is just storing the data, capturing the data. So register delay will be same because it is doing the same, performing the same task. But few instructions may take more amount of time to decode. Few instructions may take less amount of time to decode. So that is different. That can be different, right? But register delay will be same. It will not be different. So register delay is 1 nanosecond. So all this is in nanoseconds. So maximum of 5, 6, 11, 8, that is 11 plus 1. So it becomes 12 nanoseconds. So it becomes 12 nanoseconds. So my TP actually becomes 12 nanoseconds. What about TN? What will be TN? So TN is basically the time taken for me to perform one instruction for a non-pipeline system. I have told you for a non-pipeline system, I will not consider register delays because for pipeline system only we need registers. For non-pipeline system, there is no requirement of registers, right? Explanation has been provided at the starting of this lecture. So TN will just be the summation of all the delays, right? So it will be sum of 5, 6, 11, 8 nanoseconds. So this will be 5, 5, 10 and this is 11, 11, 22, 30. So this will be 13 nanoseconds. Okay. So my S ideal, right? S ideal will be what? Ideal speed up. It will be TP upon TN. So this will be equals to 12 by 30. So this will be 4 by 10. Okay, I am wrong actually. This is the opposite, right? Sorry. It's the opposite. It's TN over TP. Higher over lower, right? It cannot be lower. So it will be 30 over 12. So this will be 10 divided by 4. This will be 2.5. So ideal speed of achieve will be 2.5. This will be your answer. Okay, very simple. Like these questions are very simple actually. These questions are very simple. And let's solve the next question. So in the next question, what have they told me? They have given the stage delays. Okay, in a 4-stage pipeline, that is 800, 500, 400, 300 picoseconds. So stage delays are given. It is a 4-stage. So as soon as you read the question, right, you write down the information. So my K is 4. My stage delays are 800. So my TP will be what? TP will be maximum of 800 plus 500. No, sorry, plus, not plus, comma 400, comma 300 pico seconds. Okay, so the first stage with delay 800 picoseconds is replaced with a functionality equivalent design involving 2 stages with respective delays. The first stage is replaced, that is 800 picoseconds, with a functionality equivalent design involving 2 stages. So this 800 picosecond, right, stage 1, this has been further divided into 2 stages. Why? We'll understand why we do this. Okay, 1 to 600 picosecond, another 1 to 350 picosecond. Now you might say overall it is consuming more time, 950 picoseconds, but actually it can actually increase our throughput. What is throughput? Throughput is the increase of the instructions executed per unit time. Okay, so how it will increase the throughput? So very simple, right? Very simple. What we are doing is, in case 1 where I didn't break down anything, right, I had 4 stages. Right? This was 4 stages, 1, 2, 3, 4. Okay, so K was equals to 4 in case 1. And what is my TP? TP will be this, right, maximum of this, that is 800 picoseconds or 0.8 nanoseconds. Nothing has been mentioned, registers have not been mentioned. I will assume it to be not there. What is my throughput? Throughput is 1 by TP, correct? Or like you can write n minus k, that formula you can do, but generally like you can understand throughput is instructions executed per unit time. So in a single cycle I execute instructions, so it will be throughput will be 1 by TP, 0.8 nanoseconds. So this will be 1 by 0.8. Okay, this will be my throughput in the case 1. In the case 2, what is happening? In the case 2, what is happening? In the case 2, my through k number of stages has, like I have further divided this into 2 stages, right? So overall how many stages I have? This has been gone. This is this. So total 5 stages I have. K is equals to 5. And what is my TP? TP now will be maximum of 600, because I have further divided that into 2 segments, right? 350, and the others are same only, this 500, 400 and 300. 500, 400 and 300. Okay, so these are same. Okay, so this will be equals to, now what is my TP? TP is 600 only, right? This is my TP2, this is my TP1. 600, not nanosecond, picosecond. So this is in picoseconds. I can directly write it in nanoseconds. So it will be 0.6 nanoseconds. So my TP2 will be equals to, my TP2 will be, this is TP1, it will be 1 by TP2, right? So that is 1 by 0.6. Now they have asked me what is the percentage increase in throughput. Obviously this TP2, right, has reduced. If TP2 reduces, the throughput reduces. Okay, or this is also a formula for clock frequency. Okay, you can also say throughput is a formula for clock frequency. That also you can say. Okay, so what will be the percentage increase or change in throughput? It will be TP2 minus TP1 divided by the old, that is TP1, into 100. So this will be equals to how much? This will be simply 1 by 0.6 minus 1 by 0.8 divided by 1 by 0.8 into 100. Remember, all this is in, like this is nanosecond, so this will be in what? Gigahertz, right? Gigahertz. So just remember, but as we are calculating in like unitless, because there is a throughput in the denominator and numerator as well, so units will simply get cancelled. So what it will become is this, right? So this will become 8 by 6, that is 4 by 3 minus 1 divided by the 1. So it becomes 1 by 3 into 100 simply. So it becomes 33.33%. So the answer will be 33.33, because they have asked in percentage only, by how much percent throughput increases. So obviously that is the advantage. I'm able to do more tasks. Okay, because TP has reduced. Previously I was not, like this stage was taking so much time that there was more idle time here, right? Because I was giving 800 seconds for each stage. So this stage also got 800 seconds, this stage also got 800 seconds. So the maximum idle time for a particular, for all the stages, like I'm just choosing the maximum one, is here in this case it is 500 picoseconds for this last stage, right? But if I break it down, the first stage, if I break down the first stage, then what is the maximum idle time? The maximum idle time then becomes, this is the case 1, and in the case 2, the maximum idle time, now what is my TP now? TP is 600 now, it is not 800 anymore. So maximum idle time can only be 300 picoseconds, right? Because I have given 600 picoseconds for this particular stage, but it doesn't require 600 picoseconds. It only requires 300 picoseconds. So obviously it will only take 300 picoseconds. That's it. Okay, so that's very simple. That's why the idle time of the maximum idle time has reduced. So obviously the throughput will increase because now they will execute more tasks. Okay, in a per unit time they will execute more number of tasks. So that is the importance of throughput basically. Okay, so let's do the next question. So in the next question we have a non-pipeline processor with a clock rate of 2.5 gigahertz. So what does it mean? Okay, we will understand that later. The non-pipeline processor has a clock rate of 2.5 gigahertz. F clock is 2.5 gigahertz and average cycles per instruction of 4. Okay, so I hope you know what is average, like CPI. CPI is what? CPI average they have given me as 4. Okay, so from this, can I say how many cycles does each instruction take? Okay, so or what is a TP basically, or what can I say? Cycle, like F clock is this. This can be written as what? This can be also written as cycles per second, right? That is the definition of frequency, cycles per second. And they have told me how many cycles each instruction take. So can I, from this information, can I find out the total time of each instruction for a non-pipeline processor, that is TN? What will be TN equals to? TN will be equals to CPI average, that is the number of cycles per instruction. Okay, because I need to find out the execution time of a single task, of a single instruction. So number of cycles I have got into the time taken by each cycle, or T cycle. What is T cycle? T cycle is just the inverse, right? T cycle will be just the inverse of this. That is, T cycle will be 1 by F clock simply. Okay, so this will be 4 times 1 by 2.5 gigahertz, or this will come out to be nanoseconds because giga is nano. Okay, so this will become what? This is 4 by 2.5. I can multiply this by 2 by 8 by 5 nanoseconds, or 1.6 nanoseconds. So this is my TN actually. For a non-pipeline system, this is the time that it is consuming. Next, but due to internal pipeline delay, okay, so sorry, the same processor is upgraded. Now it is upgraded to a pipeline processor with 5 stages. So I have upgraded this non-pipeline processor to a pipeline processor with 5 stages. So my K will be 5 simply. Next, what they're telling me? They're telling me, but due to internal pipeline delay, the clock speed is reduced to 2 gigahertz. So for some reason, due to resistors or anything, the clock speed, F clock P has now reduced to 2 gigahertz. Okay, it has now reduced to 2 gigahertz, right? Just hold on. Yeah, everything is fine. 2 gigahertz, right? So from this information, can you tell me what will be the TP cycle time? It will just be the 1 by F clock, right? This I have told you why this will be like this. I have already told you at the starting of the today's lecture, right? So it will be 1 by 2 nanoseconds, or 0.5 nanoseconds. Okay, so that is the case over here. So obviously my TP will change, things will change. Now what are they asking? They are asking me, assume that there are no stalls in the pipeline. Just ignore this line. What is stalls? Stalls comes due to hazards. Just ignore this line. It's not important. The speed up achieved in this pipeline processor. What is the speed up achieved in this pipeline processor? So speed up will, what is the formula for speed up? It is T execution of a pipeline system, sorry, non-pipeline system, over the T execution of a pipeline system. So this is equals to what? How do you calculate? Now it has also asked me the speed up achieved, but they have not told me the number of tasks. So if they have not told me the number of tasks, what can I assume? I can assume that my n is very greater than k minus 1. They have not told me. So then what does my speed up become? I have done this, like I have defined this, derived this many times in this lecture. So it will be directly Tn over Tp. So what is my Tn? Tn is simply 1.6 nanoseconds, right? And what is my Tp? Tp is simply 0.8 nanoseconds. So not 0.8, sorry, 0.5 nanoseconds. So your speed up achieved will be 3.2. Okay, you can clearly see that your like if I break this down, right, how many number of stages I have? 5. So if I do k times Tp, right, k times Tp is 5 times 0.5, that is 2.5 nanoseconds, which is not equals to Tn. So it is not a balanced pipeline system. Okay, it is not a balanced pipeline system. So I hope you understood. Like I went a bit fast, but I hope like everything is simple, right? Just you have to find out the Tn and Tp, because here they have not mentioned me the number of tasks. So I'll assume n to be very high. If n is very high, then my speed up changes to ideal speed up, that is Tp over Tn. Okay, if they would have told me that it is a balanced system, then it would have been, speed up would have been equals to k, but it is not. Always remember this formula. If you want to remember anything, always remember this formula only, because if it is a balanced system, automatically this will get converted into k. Why? Because your Tn will automatically be equals to k times Tp. Tp will get cancelled and you will be left with k only. So if you want to remember, you can remember this formula. That's enough. Okay. So I hope you understood this point, and this is also very important point, that for a non-pipeline system they have mentioned the clock frequency. So it is the cycles per second. Okay, and each instruction takes 4 cycles. So overall, how much time will each instruction take or each task take? That is 1.6 nanoseconds. For pipeline, how much time will each task take? If n is very larger than k minus 1, obviously each task will only take 1 cycle. Why? Because after every cycle I am getting an output. Something is coming into the pipe and something is going out of the pipe every instant. Okay. So that's why each cycle will take Tp amount of time. So Tn over Tp will be 3.2. I hope you understood this point. Let's do this question. Comparing the time T1 taken for a single instruction on a pipeline CPU. Okay. T1 is the time taken for a single instruction on a pipeline CPU. So what will be my T1 equals to T1? If I am only doing a single instruction, so n is 1. So simply it will only take k times Tp, right? Comparing with time T2 taken on a non-pipelined but identical CPU. What does identical CPU means? Identical CPU means they have same clock frequency. You have bought CPUs, right? You know few specifications of CPUs. This is a 3.2 gigahertz CPU, AMD Ryzen 3.2 gigahertz CPU, or like your chips. Phone chips has 3.2 clock speed, 3.2 gigs of clock speed, or 3.4 gigs of clock speed. What is it? It is CPU, right? So if it is same CPU, the clock speed will be same. Now, if the clock speed is same, that is their F clock is same. That is their T cycle, right? Cycle time is same. Cycle time is same. Okay. If the cycle time is same, then what are they asking? They are asking, what can we say? So this, right, T1 will become what? T1 will become k times T cycle actually. What can we say? T1 will be less than equals to T2. T1 will be greater than equals to T2. T1 will be less than. How can I say this? Okay. So what you can do, you can assume few cases here. So if I assume few cases, let's take like a 4-stage pipeline system. Okay, this is 6, 7, 8 and 9. Okay, just assume any number. 6 seconds also you can assume. I'm assuming any number. And let's take another case that is all balanced. And again I have 4 stages and all of them has 4 seconds of segment delays. Now, how much will this one take? How much will this one take? Its TP will be what? TP will be 9, right? So my assumption is clock cycle is this. So the clock cycle will be decided by TP only. TP will be here, in this case TP will be what? Maximum 9, assuming no resistors. But what will be Tn actually? Tn, right? Tn will be 6 plus 7, that is 13 plus 8, that is 13 plus 8, 13 plus 8, 21 plus 9, that is 30 nanoseconds. Okay, or 30 seconds, anything. But what is my time? Execution time of a pipeline system. Execution time of a pipeline system for a single instruction, it will be k times TP, that is 4 into 9, that is 36 nanoseconds. So here I can observe that execution time, that is, this is my T1, right? T1 is greater than T2. And here, if it is a balanced system, right? If it is a balanced system, here what will be my TP? TP will be 1. Tn will be what? It will be sum of all the stages delays, that is 4 nanoseconds. What will be my T execution of pipeline system? This is my T2, right? Tn is simply my T2 because I am only executing a single instruction. That's why. T execution here will be simply k times TP. I have 4 segments, so it will be 4 nanoseconds. So here my T1 is simply equals to T2. So for a single instruction, what I can say is, for a single instruction, my T1 will always be greater than or equals to T2. So option B will be correct. Mathematically also we can prove, right? So what is my execution of a non-pipeline system? Non-pipeline T execution of a non-pipeline system. Okay. T execution of a non-pipeline system is what? It is simply equals to n times Tn, right? And if it is a single instruction, it will be simply equals to Tn. And this is equals to sum of all the segment delays. So let's say this is T1 plus T2 plus T3 plus T4. And let's assume that maximum out of T1, T2, T3, T4 is T2. Just my assumption. Okay. The same thing, T execution for a pipeline system, it will be for a single, generally the formula is this kn minus 1 into TP, but for a single instruction n will be 1, so it will be k times TP, and TP is what? TP is simply T2. It will be k times T2. So this is also 1, 2, 3 k only. K only. So here my k is 4. That is my assumption. So this will be 4 times T2. So what I can observe, that this is my T1 and this is my T2. What I can observe is this is 4 times my T2, and I am also adding 4 times here, but not T2 actually, not the highest value. I am adding lower values. So obviously if I am adding lower values, let's say T2 is 30 nanoseconds. Now all these are 10 nanoseconds. So this will become 10 plus 10 plus 1, 30 plus 30, 60, and this will become 4 times 10, right? 4 times 30, that is 120 nanoseconds. So always my T1 will always be higher than T2 for a single instruction, only for k n equals to 1. Remember, only for n equals to 1. So that's why I have chosen option B. So this is only valid, remember, only valid for n equals to 1 instruction. It is not valid else. Okay. So very simple thing. A 4-stage pipeline has delays this and registers have delayed this 5 nanoseconds. Assuming constant clocking rate, the total time taken to process 1000 data items on this pipeline. Very simple, right? Again, you have to choose the maximum. Basically, TP will be what? TP will be maximum of all this. It will be maximum of 150, 120, 160, 140 nanoseconds plus register stage delay. Each stage has 5 nanoseconds of delay. So this will become 160 plus 5 nanoseconds. So this will become 165 nanoseconds. TP will become 165 nanoseconds. Now, assuming the constant clocking rate, the total time taken to process 1000 data items on this pipeline will be. So obviously, it is asking me execution time of a pipeline system. What is it? It is simply equals to Ka plus n minus 1 into Tp. So how many stages I have from the delay, right? I can see it has 4 stages. So K is equals to 4. 4 plus n. N how many? 1000, I think. It is 1000 data items. 1000 minus 1 into Tp. Tp is 165 nanoseconds. So this will become 1003 into 165 nanoseconds. So this will, I will just quickly compute this. What have they asked? In microseconds, right? So almost it will be almost equals to 165 micro only. 165.495. So almost equal to this. Option C will be correct. I have just converted it into micro. That's it, right? So these are all very simple questions, and I know you will be able to solve it. So let's take another question. We have two designs, D1 and D2, for a synchronous pipeline processor. Okay, both are synchronous pipeline processor. Only two designs we have. One design D1 has 5 pipeline stages. So my K1 is equals to 5 with execution time. Each stage execution time is 3 to all this, right? So obviously, what will be my TP? TP1 will be maximum of 3 to 4 to 3 nanoseconds. Okay. While design D2 has 8 stages. So K2 is 8 and my TP2 will be what? It has 8 stages, right? Each with 2 nanoseconds execution time. So TP2 will be simply 2 nanoseconds because maximum of 2 nanoseconds of all, each has 2 nanoseconds, right? It will be simply 2 nanoseconds only. How much time can be saved using design 2 over design 1 for executing 100 instructions? So how much time can I save in design 2? Because overall it has 8 stages, right? So each instruction it is taking 16 nanoseconds for the first instruction only. After that, it is only taking 2 nanoseconds. So that is the advantage. Here the maximum will be 4 nanoseconds. Correct? So each after the first instruction, each instruction will take 4 nanoseconds to fetch. So how much, what is it telling? How much time can be saved on design T2? So it is asking me to find out T execution in the second design minus T execution in the first design for n equals to 100. So this will be what, like formula is same, right? It is like first instruction K1 minus n, that is n equals to 100 minus 1 into TP1 minus, okay, this should be actually 2, sorry. Yeah. How much time am I saving? How much time am I saving? How much time can we save? So obviously I will write this actually T1 minus T2 because they are asking me how much time have I saved. So T1 obviously will take more time. Design 1 will take more time than T2. So that will give me the amount of time that I have saved actually. So it will be K1 TP1 then K2 minus n minus 1 into TP2. So this will be equals to K1 is 5 minus n. N is basically 100. Sorry, this will not be minus. Sorry, if this will be plus, right? Sorry, plus 100 minus 1. What is TP1? TP1 is 4 nanoseconds, correct? Minus all this is in nanoseconds only. K2 has 8 stages, but it won't matter much because my overall cycle time has reduced, right? It is 2 nanoseconds only. So this will be 104 into 4. So this is 416 minus this is 214 nanoseconds. So this will be 202 nanoseconds. So total I am saving in the, if I use the design tool, I will save 202 nanoseconds. So sometimes this has disadvantages like breaking it down into multiple stages, but most cases if I keep my segment delays consistent, then obviously I am saving huge amount of time because the idle time has reduced, explained in previous question as well. So how much time have I saved? 202 nanoseconds. These are all very, very simple questions. Okay, so let's do this last question. So we have a 3 gigahertz processor with a 3-stage pipeline and stage latencies as tau 1, tau 2 and tau 3. So my clock, right, frequency of the clock, f clock, is 3 gigahertz. Okay, fine. And it is a 3-stage pipeline. So K is 3. And each stage has latency or delay of tau 1. So like the first stage has tau 1, second stage has tau 2, third stage has tau 3. And they have given me the relationship between each stage delays. So this is a very, very brilliant question. Please focus. Please focus here. Okay. So they have told me that tau 1 is actually 3/4 of tau 2 and tau 1 is also twice of tau 3. That is a relationship that they have given me. Now, what are they asking? If the longest pipeline stage, I don't know what is the longest pipeline stage out of this, tau 1, tau 2 or tau 3, they tell me it is split into 2 pipeline stages of equal latency, the new frequency will be. So first of all, first thing is I have to identify what is the longest pipeline stage. Okay, that is my first task. How do I find out what is the longest pipeline stage? So I have tau 1, tau 2 and tau 3. They are related here, right? So it is telling me that tau 1 is 3/4 of tau 2. So obviously my tau 1 will be less than tau 2. Let's take an example. Let's take tau 1 to be 1. Okay, or tau 2 to be 1 nanosecond. If I take tau 2 to be 1 nanosecond, what will be tau 1? Tau 1 will be 3/4 nanoseconds, which is less than tau 2. So obviously tau 2 will always be less because obviously I am multiplying it with a fraction with tau 2. So tau 1 will always be less than tau 1. What about the second? It is telling me that tau 1 is twice of tau 3. So obviously I can say that tau 1 will be greater than tau 3. Why? Just take an example. Tau 3 will be 1 nanosecond. If tau 3 is 1 nanosecond, tau 1 will be twice the 1 nanosecond, that is 2 nanoseconds. So tau 1 will be greater than tau 3. Simple, right? Tau 1 is 1 nanosecond, tau 1 comes out to be, so tau 3 is 1 nanosecond, tau 1 comes out to be 2 nanosecond. It is greater than. So it will be greater. So out of these two inequalities, I can completely see that tau 1 is greater than tau 3 and tau 2 is greater than tau 1. So I can arrange this like this. Tau 2 is greater than tau 1 is greater than tau 3. So my largest segment delay will be tau 2. So obviously that is what my TP will be, right? TP will be what? They have not provided any register delay. So maximum of tau 1 tau 2 and tau 3. Now what is the larger of these three? Larger of these three is tau 2, right? Tau 2 is the highest. So obviously my TP will be tau 2. Obviously my TP will be tau 2 simply. Okay. And I also know f clock. And what is f clock? F clock is simply equals to 1 by TP, correct? So from here I can directly find out my tau 2 and I can find out everything. So 1 by f clock, that is 3 gigahertz or nanoseconds, is equals to tau 2. Correct? I have directly found it out because it is 1 by f clock. Now next what they are telling me? They are telling me if the longest pipeline stage is split into 2 pipeline stages with equal latency. So this tau 2 has been split into 2 stages of tau 2 by 2 and tau 2 by 2. Then what they are telling me? Then they are telling me the new frequency will be. So now this will become what? This will be 1 by 6, 1 by 6. What about tau 1? Tau 1 is 3 by 4, tau 2, right? Tau 1 is 3 by 4, tau 2. So what is tau 2? 3 by 4 into tau 2. What is tau 2? Tau 2 is 1 by 3. It is 1 by 4 nanosecond. And what is tau 3? Tau 3 is 1 by 2 of tau 1, right? Tau 1 by 2. Tau 3 is tau 1 by 2. Tau 1 is 1 by 4. So tau 3 will be 1 by 8 nanosecond. Tau 3 will be 1 by 8 nanosecond. So tau 3 is 1 by 8 nanosecond. So finally, what will be the new TP2? TP2 will be the maximum of 1 by 6, 1 by 6. Like I can write it like this. It will be maximum of 1 by 4, 1 by 6, 1 by 6 and 1 by 8. Because I have broken down the longer stage delay, right, to 2 delays. So TP2 will be what? This will be the highest, right? 1 by 4 simply. So now what will be the clock frequency? This is nanoseconds. F clock will be what? It is the inverse. F clock 2 will be the inverse of 1 by TP2. So it will be 4 gigahertz. Frequency has increased, right? Because obviously throughput also has increased. So answer will be 4 gigahertz. This will be the answer. So very simple question, but elegant question, right? Because many things are unknown. You have to identify the question perfectly and find out the result. Okay. So basically that's it for today's lecture. I hope you have enjoyed today's lecture, and from the next lecture onwards we'll understand few hazards and a lot more things about instruction pipelining. This was just the introduction and questions on instruction pipelining. Thank you for watching, and I will see you in the next lecture. Until then, happy learning. Hi everyone and welcome back to my channel. I am Anish and today we'll start the second part of our instruction pipelining topic. Okay, so today we'll learn about hazards in a pipeline. So we have learned what is a pipeline architecture, what is instruction pipelining. So what are the problems that we face? Obviously, if we are gaining so much from a particular architecture, there will be some disadvantages. So this is one of the disadvantages, hazards. Okay, so from the picture you can see that something is going wrong here. What is exactly going wrong, that we'll figure out. So what is instruction pipeline basically? What is the instruction pipeline? Pipelining, which we already know, is used to improve the efficiency of instructions execution by overlapping multiple stages of an instruction cycle. By overlapping multiple stages. So what do you do is simultaneously I am doing some operation for stage 1 on some other data, and also I am doing some operation on stage 2 on some other data. So in the same clock cycle, stage 1 is also working, stage 2 is also working, stage 3 is also working, stage 4 is also working. All the stages are working. So that's why overlapping. I'm overlapping multiple stages. Okay, we understand this better in the example that will come. Okay, just after this. It is especially useful when the same processing is applied over multiple inputs or instructions. As explained in the previous lecture as well, pipelining will be useful only when we are doing similar kind of operation. Just like I take an example, right, where it was a plus b times some other z variable. Okay, something like that. We are doing that on like different operands, but we are performing the same operation only. Okay, so that is what we do. An instruction pipeline applies the concept of pipelining to the instruction cycle. Okay, we apply the concept of pipelining to the instruction cycle. It breaks the instruction execution into stages, with each stage working on a different part. Okay, so up until now what we have studied, I've told you that yes, we will use the pipelining concept. We are doing some different operations, but actually what we do is we do instruction pipelining, because at the starting of a instruction cycle I have explained that instruction cycle has many stages. Okay, namely these are the stages. There can be other as well. I have told that at that lecture, but mainly we will consider these stages. First is the instruction fetch. In the first stage, that is the instruction fetch, where we fetch the instruction. What is the instruction? From where I will get the instruction? PC will store the instruction, right? So I fetch the instruction, then I decode the instruction and I calculate. Like this is just a standard instruction cycle. There can be other types of instruction cycle as well. Don't worry, they will mention this in the question. They will tell you how many stages each instruction cycle has. So next is decode and address calculation. So I will decode the instruction and then I will calculate the address of the operands. Okay, so all those things can happen in stage 2. In stage 3, I will do the operand fetch. I will fetch the operands from the address that is calculated in the previous instruction to our own registers. Then I will do execute. I will perform the operations on those operands. Then I will write back the result. So this is a standard typical 5-stage instruction pipeline. So what I can do, pipeline is a generic concept, right? It can be used anywhere. So pipeline is a generic concept. I will write here. Pipeline is a generic concept and can be used anywhere. Okay, but we are using what? We are using it instructions. Okay, this instruction can be anything, right? This instruction can be anything, addition, subtraction, anything. But net a instruction has total of 5 stages. So I can divide all this into 5 stages and then I can apply my concept of pipelining. So if I apply the concept of pipelining, that particular thing in the instructions of a computer, that is known as instruction pipelining. So this is what? Implementation of pipelining in instruction cycle. Okay, so let's understand this with an example. Okay, so we have a pipeline execution here. So this is instruction 1. Obviously each instruction can be anything, right? They can be anything, but one thing is constant, they will have always 5 stages. That has been defined in the architecture. They will always have 5 stages. So in the first clock cycle, the instruction 1, the processor will fetch the instruction of instruction 1. Okay, and I have 5 stages, right? I have 5 stages. In the next clock cycle, what will happen? As I have 5 stages, what will happen is, in stage I have kept 5 person, right? One person is responsible for fetching the instruction, other person is responsible for decoding, third person is responsible for operand fetch, fourth execution, fifth write back. So person A now will fetch the instruction of the second I2, right? Second I2, instruction 2. And person B will decode the instruction now of the first instruction. So in second clock cycle, 2 things will happen parallelly. In third clock cycle, 3 things, right? I will do the operand fetch of the first instruction. Person C will do this. Person B will decode the instruction. Person A will again fetch the instruction. Okay, so everything is happening parallelly now. Everything is smooth, right? Everything is happening smooth. So if everything is smooth, once I reach this stage, right? Once I reach the 5th clock cycle, I will do 5 operations parallelly. Okay, everything will happen parallelly. Okay, but what if I tell you there is a problem? Okay, this is smooth. This we have already discussed in the previous lecture, right? Each thing, like after this point, right, I am getting a new output after each clock cycle, right? Because this has done is in 5th clock cycle, I1 is doing write back. In 6th clock cycle, I2 is doing write back. In 7th clock cycle, I3 is doing write back. So at each clock cycle, I am doing some write back. I am getting some results. Everything is smooth. But what if it was sequential, right? The CPU knew that I had to first perform I1, I2, I3, I4. Everything was sequential. Okay, everything was sequential, that I had to perform I1, I2, I3 and I4. Now, what if I tell you this I3, right? I3 is a branch type instruction. Branch type instruction. what is branch type instruction? Branch type instructions means basically once I get here, right, I3, it will check some condition, and if that condition is true, it will branch to a new instruction, right? It should not execute I4. It should not execute I4. But I have already done few things. Like I am at this particular situation, right? I have decoded, the control unit has decoded the instruction I3, and it got to know that this is a branch instruction. But the stage 1 already has, person A has already fetched the instruction, right? I4. I4 has already been fetched, and at this particular moment, the control unit has got this information that the instruction I3 is actually branch type instruction. So at this moment, he, you know that word, right? He fucked up. Okay. So I will not say that word. Okay. So now the control unit say, oh my god, now what will I do? I have already continued to fetch the instruction I4, but actually I don't know if the next instruction should be I4 or something else. Let's say it should branch to I7 if the condition is true. Okay. So what will happen here? So a hazard has been caused here, right? Hazard. Why? Because after I3, right, I4 is supposed to not go through if some condition is true. There is some conditional branch. Okay. So we have to see how do we mitigate this hazard. First, let's understand this hazard more. Okay. So instruction I3 is normal instruction. No worries about that. It's normal add operation. So no worries. It is independent, right? Instruction I2 is also normal operation. It's normal subtract of two register values on memory location. Okay. Instruction I3 is a branch type instruction. Okay. Its target instruction is 6. Let's say its target instruction is 6, but it will be only executed only if the branch is taken. That is only if the condition is true. Like there will be some condition associated with the branch, like if I equal 1 or I equal 0, something like that. Condition is true. Okay. So what will the person A do? Will it fetch the instruction like here? It is supposed to fetch the instruction here, right? IF. Will I fetch my instruction here? Will I fetch my instruction here for I5? Because if the condition is true, right? If the condition is true, all this is just a waste. This time, right? All this is just a waste. Okay, if I decode my condition, then I got to know, okay, I had to go to instruction 7. So why will I fetch instruction 4 and 5? I will directly go to instruction 6, not 7, sorry, 6. Why will I fetch instruction 4 and 5? It's just a waste, right? These should not have been processed, correct? So we have to, what we do is, the general notation that we follow, or the general, guideline that we follow is, we wait until the condition is calculated. Okay, wait for the condition. We wait for the condition to get evaluated. If it is true, we'll see. If it is true, then we'll fetch the instructions instruction I6, sorry. If it is false, we'll fetch the instruction I4. So we have to wait. We have no other choice than wait. So what we do? How do we solve this? Instruction 3 is a branch instruction. The pipeline must wait until the branch condition is evaluated. When does it get evaluated? In the execution stage. This is just now for different questions, the branch condition can be evaluated in different stages. You will understand by reading the question. Okay, but generally for a standard 5-stage instruction pipeline, the branch condition is evaluated at execution stage. Generally, it can change as well. Okay, so my branch condition will be executed here, right, in cycle 6, because I was here. In cycle 6 only, my branch condition for instruction 3 will be executed. Will be evaluated. So after this particular cycle, only I will be able to know whether I need to go to instruction 6 or instruction 4 or something else. Okay. So actually, I have to wait. So I cannot instantly do instruction fetch after this, right? I cannot do. I have to wait for this 3 cycles. Okay. So that I get my information execution. Then only I go to the next instruction phase. I have to wait. So I put here stall cycles. It is known as stall cycles. So actually how many stall cycles I have to put here, right? I was supposed to do instruction fetch in this particular cycle, 4 cycle for the instruction 4, but I'm not able to do. So I will put a stall cycle here. Stall cycle meaning no operation. It is not doing anything. That particular person A is idle. Stall cycle, person A is simply idle. Okay. So here I will write in cycle, this is the 4th cycle, this is the 5th cycle, and in the 6th cycle. So from 4, 5, 6, I will sit idle, right? My person A will sit idle. So cycle 4 to 6, 4, 5, 6, I have to give stall cycles, right? Because at this 6th cycle, right, this is supposed to fetch the instruction I5, but we will not. We will just put a stall cycle. We will not do any operation. It will be no operation. So all this will be just stall cycles, okay, until the execution phase. All this will be stall cycles. As soon as I get my execution right, like this is internally inside the computer, that as soon as I do the execution and I got to know that my branch condition is what, if it is like my assumption is branch condition is true, okay, this instruction we do some we evaluate some condition and assumption is branch condition is true. As soon as I got the result, what I'll do, I will directly fetch the instruction I6 after this cycle. I will directly fetch the instruction I6 after this cycle. So I'll go here and fetch the instruction. I will not wait. I will not literally wait. Okay. So that is the case over here. So I will just wait until this execution phase, and after, as soon as I execute this, right, I will directly go to my instruction fetch for the target address. If it was I6, I will fetch the instruction I6. If it was I4, I will fetch the instruction I4. Okay. So actually, it is very simple of me to do all this, analyze all this and say, but computer actually is not that intelligent. Okay. Computer is not that intelligent. So how do we solve those problems? We'll see. Like this computer itself, it won't be able to understand, okay, like as soon as the condition has been fetched, then I will, like, putting the stall cycles is only possible solution. Okay, that is what we do generally, that is what we follow. But without putting stall cycles, if you say that you don't want to put the stall cycles, you directly want to compute this execution, okay, directly want to compute this condition and directly want to fetch the next instruction. So there are a few ways, but generally those we avoid. Okay, we'll see. So this is for the case if branch is taken. If the branch is taken in the 7th cycle, what we'll do, I will do the instruction fetch of the 6th instruction. If branch is not taken, okay, if branch is not taken, what will happen? Like this will, anyways, I was supposed to do instruction fetch here, but it will be a stall cycle. I was supposed to do instruction fetch here, it will be a stall cycle. Again, I was supposed to do instruction fetch here, it will be a stall cycle. So how many stall cycles I will have? Total of 3 stall cycles, right? 3 stall cycles I will have. Okay. Because my instruction fetch is supposed to be here. Sorry, my instruction fetch was supposed to be here actually, but currently it is here. So how many stall cycles I had to give? Sorry, 2 stall cycles. Sorry. My instruction fetch was supposed to be here. Currently it is here 3 stall cycles. This also will be stalled, right? So total I will give 3 stall cycles. My instruction fetch was supposed to happen here, but it is happening in the 7th cycle, right? So how many cycles were just abandoned? 4, 5, 6, that is 3. 3 cycles were just kept abandoned, right? They were just stalled. No operation. No operation. So if, let's say if the branch was not taken, then I would have fetched the instruction I4. If the branch was taken, then I would have fetched the instruction I6. Okay. So branch hazard introduced delays, stall cycles in the pipeline. In this example, 2 extra, actually this will not be 2, 3 extra stall cycles. Three extra stall cycles were added due to branch condition, right? And the pipeline was emptied after the branch instruction was encountered. So emptied meaning only from this point pipeline again started of filling the water, right? So what happened was that my water was flowing through the pipeline, right? Water was flowing through the pipeline. What happened there? A blockage came. What was the blockage? Stall came, right? This was due to the branch instruction. Okay, this was due to the branch instruction. A blockage came. So a blockage came here, right? And this blocked. This paused all activities. Then again this blockage got over once I got my condition. Once I evaluated my condition, right? Then only I took out this blockage, and then again the pipeline was empty. That is, this water was again flowing. That's the meaning, physical significance of this particular thing. Okay. This increases the total processing time as all stages of the pipeline must restart process with the new target address, because basically it increases the processing time, right? So I was supposed to fetch my instruction here, but now I'm fetching it after 3 cycles. So obviously it increases the execution time, which will obviously reduce the processing time. So all this is the disadvantages, correct? Minimizing branch hazards using techniques like branch prediction or speculative execution can significantly improve pipeline performance by reducing or eliminating the need of emptying the pipeline. But this is actually we will not study, and this is very difficult to implement as well. Branch predicting, how will you predict the branch of a particular condition? That is just like gambling, right? You are gambling, so it is very difficult. Okay, so new architecture do this, but there are few methods to this. They do. Okay, that will obviously out of syllabus we won't study. So these are few techniques which we do. So basically I haven't told you the basic definition of stall cycles. Now I will tell you the basic definition of stall cycle. Stall cycles are extra clock cycles introduced into a pipeline when an instruction cannot proceed to the next stage due to a dependency, hazard, or resource conflict. Okay, so here, right, actually I was supposed to get my instruction fetch on cycle 4, but I am getting my instruction fetch on cycle 3. Actually one thing is wrong. Okay, this stall cycle, right here I'm supposed to get at cycle 4, but I'm getting at cycle 7. So how many stall cycles I had to give? This, yeah, 3. So this was the first stall cycle, this was second, third. So these 3 I had to give 3 stall cycles. The extra clock cycles that I had to give to resolve a data hazard, dependency hazard, or a resource conflict. So we'll learn more about hazards, don't worry. We'll learn more about hazards, don't worry. Okay. During these cycles, the pipeline effectively pauses while waiting for the necessary data or condition to be resolved. We pause, right? We pause our operation until the condition has been resolved. Then only we resume our pipeline. Okay. This temporarily reduces obviously pipeline efficiency because throughput reduces, right? The overall execution time increases, throughput will reduce. Simple as. So common causes of stall cycles. There can be mainly 3 common causes of stall cycles, or there can be mainly 3 types of data hazards. 3 types of hazards in a pipeline. First is data hazard. An instruction depends on the result of a previous instruction. An instruction depends on the result of a previous instruction still in progress. What do I mean? So we'll go more deeper into this. But let's say instruction I1 is perform R1 plus R2 and store it in R1. And instruction I2 is R1 minus R3 and store it in R3. So actually this instruction I1, during the instruction fetch, I got to know, okay, I have to do like this. I have fetched the instruction. Then during the decode cycle, I got to know I have to perform this operation, right? And instruction I2 has to perform subtraction on same register R1. So this instruction hasn't been completed yet and R1 value hasn't been updated yet, because what was supposed to happen, that in C programming, right, you will write the code like this: R1 plus R2 and R3 equals to R1 minus R2. So in C programming, what you are supposed to do is this is R3. You were supposed to simply get this updated value, update the value of R1, then subtract from this, right? Subtract the updated value from R3. But here what is happening, as things are happening simultaneously, if you observe here, right, what is happening, I'm doing instruction fetch. So here I have fetched that I have to do that some instruction has been fetched. In this decode cycle, I got to know that I have to do R1 plus R2 and store it in R2. Here I got to know I have to do R1 minus R3. Here I am executing that. I have still not updated the value of R2, but here I am doing operand fetch. So I am fetching the value of R2, the old value. Okay, so that's why there is a hazard. We cannot do. We have to stop until this write back or execution, depending on the question or how they have given the information. Until then only I can proceed with the next instruction. Else I will not be able to start the instruction. We will come to this. Don't worry. We will come to data hazards, control hazards. What is control hazard? Just what we have shown in the example right now. If a branch instruction comes, it has to wait. Our pipeline has to wait until that instruction has been evaluated. Structural hazard. If multiple instructions compete for the same hardware resource. So multiple instructions are telling that they need the ALU, right? In simultaneously, like what happens in this pipeline, right? All the stages are operating simultaneously, right? All the different stages. But what if in different stages they conflict for the same resource? We'll understand with the example. There we will see that they're conflicting for the same resource. So obviously you are here, right? You are only a single person. Your friend is telling you to go to the sports game, okay, the stadium, and your girlfriend is telling you to go to movie. So you are only a single person, right? Physically. Virtually you can go physically, right? So either you can go to sports movie or either you can go to the sorry, not sports movie, what I am saying, either you can go to the sports or either you can go to the movie. Now you have to decide which one you do. So one thing you can do, first you go to the first you go to the movie because your girlfriend will be upset. So first you go to the movie, then you go to the stadium, okay, and go and watch with your friend. So first you are only single resource, right? First you allocate some time to your girlfriend, then you allocate some time to your friend. So that's how resource allocation works. Simultaneously you can do. So that is what this structural hazard is. We'll come to this. Don't worry, we'll come to all this in today's lecture only. So if we have stall cycles, right? If stall cycles are there, then what will be my total execution time? So if I have stall cycle, any number of stall cycles, right? Any number of stall cycles of, let's say, n stall. What will be my total execution time? So before finding out the total execution time, first I will write the total number of cycles in pipeline. I'm only talking about pipeline. So what is the total number of cycles? Okay. What is the total number of cycles? Total number of cycles is basically for the first instruction. I will need k number of cycles because k is the number of stages plus how many instructions are left, n minus 1, because one instruction has already been executed out of n instructions, plus n stall. Okay, because these were supposed to be the extra stall cycles that I needed to provide. Okay, yeah, am I correct? These are supposed to be the extra stall cycles that I needed to provide for the either resolving a hazard basically. Okay, so that is the case over here. So now what will be the total execution time? T execution of the pipeline. It is simple, right? It will be basically all this total number of cycles minus 1 plus n stall into TP. That's it. Okay, into TP. So what you have to understand is there is a formula that you can remember, or it's okay if you don't remember as well. What you have to understand, what will be this install? How do you find out this install actually? Let's just take an example. Here my I was supposed to fetch my instruction here, right? here, okay, but my execution is happening here. So how many stall cycles I have to provide? Only after this execution only I will be able to start my next next instruction fetch. So I have to provide 3 stall cycles. So if your execution is at the 4th phase, then you have to provide 3 stall cycles, right? Because one cycle is already taken care with the pipeline, because each instruction take 1 cycle only. So that has been already taken care. So if your execution is at the 4th stage, then you require 3 stall cycles. If your execution was at the 2nd stage, then how many stall cycles you would have required? You would have only required, no sorry, 4th. If your execution cycle was here, right, here, how many stall cycles you would have provided? Here, 1 here and 1 here, right? 2 stall cycles. So I hope you are getting a formula. What is the formula? Formula is the execution stage number minus 1. Because 1 is for what? 1 cycle is anyways embedded in the pipeline, because each instruction, each micro operation or each stage takes 1 cycle. That is already taken care of in this particular formula, right? So what I can say is nstall, you can remember the formula, or it's okay. It's okay if you don't remember the formula. Nstall will be like, now it depends, right? When does the branch condition gets evaluated? It can be evaluated in the execution phase stage, or it can be evaluated in decode stage. It can be evaluated anywhere. It depends on the question. If nothing is mentioned, you will assume execution stage. Okay, nothing is mentioned, but generally they will mention. So it is the stage number of branch condition evaluation. Evaluation minus 1. Okay, condition evaluation minus 1. Okay, so that is what these are the number of stall cycles. Now here, right, something is written. It's that is the same thing is only written here. If the branch condition result is evaluated in the ith phase of the instruction, then ith phase of the instruction cycle, then number of stall cycles due to that branch instruction only, okay, will be I minus 1. Okay, so if no information is given, you will assume it to be in the execution phase. So we write here, if no information is given, then assume it to be in the execution phase. Okay, so yeah, so what are the few impacts of stall cycle? So obviously, right, your total execution time increases. If your execution time increases, then your throughput will reduce, because the number of instructions that you can do per unit time will reduce. Stall cycles reduces the efficiency of pipeline. We'll understand what is efficiency of pipeline later on, don't worry. As it increases total execution time, this is intuitive, right? I hope you understand. Fewer instructions are completed per unit time due to idle cycles introduced by the stalls. Hence there is a reduction in throughput. So these are the consequences of stall cycles and hazards. Okay, these are the disadvantages of a pipeline. So obviously we have to make do with that. So we'll solve this question. From there the concept of stall cycle will be cleared more. Okay, consider an instruction pipeline with 5 stages without any branch prediction. So we don't do any branch, we don't predict the branch. Okay, we have to wait for the evaluation of the branch condition. Fetch instruction, decode instruction, fetch operand, execute instruction, and write operand. So this is a standard 5-stage instruction cycle. They will tell you how many stages it has, and also they will tell you the stage delays. Also they have told this there are intermediate storage buffers as well. Each stage and delay is 1 nanosecond. Okay, everything is mentioned. A program consisting of 12 instructions is executed in this pipeline processor. Okay, Instruction I4 is the only branch instruction and its target branch is I9. If the branch is taken during the execution of the program, the time needed to complete the program. Now here they have not told me that at what stage I am executing or evaluating the condition of the branch. Okay. So what are they telling if the branch is taken? So I will assume obviously at execute instruction I am evaluating the condition. So I write down the data points. My K is 5. It is a 5-stage instruction pipeline and it doesn't have any branch prediction. And my TP will be what? TP will be max of 5, 7, 10, 8, 6 nanoseconds plus the registered delay, right? What is the registered delay? Delay of each buffer is 1 nanosecond. And I have 12 instructions. So this will be 10 plus 1. So this will be 11 nanoseconds. Okay. And I4 is the only branch instruction. And my assumption is, what is the stage or phase where I am evaluating the condition execution, right? So what is this phase? This is the 1, 2, 3, 4th. At 4th phase, I am evaluating, assume at 4th phase evaluating condition. Okay, so how many stall cycles I need to give? 3. So n stall will be 4 minus 1, that is 3. How did this 4 minus 1 came? I have explained. I will not waste my time here. Okay, so what will be the what are they asking? Total time. So what is the total number of cycles actually? Total number of cycles, n cycle will be what? It will be k for the first instruction. And they have also told me that actually branch is taken during the execution of the program. So directly from I4 I am going to I9. So total I have 12 instructions. So 12 instructions I have, and out of those I'm executing I4, but I'm not executing I5, I6, I7, I8. I'm directly going to I9. Correct? I'm directly going to I9. Just hold on. One thing I want to check. Yeah, this is fine. So I'm skipping this 4 instructions, right? So out of 12, I'm skipping 4. So I'm only, my pipeline is only executing 8 instructions. And I had to give stall cycles as well. So that I will compute later on. So this is n actually, number of instructions that the pipeline is executing. K plus n minus 1 plus n stall. So k is already given, k is 5. Okay, so this will be 5 plus 8 minus 1 plus 3. So this will be 13 minus 1, 12 plus 3, 15. So total it is taking me 15 cycles. Okay, now what will be the execution time of the pipeline system? The execution time of the pipeline system will be n cycle into time taken by each cycle, that is TP. So it will be 50 into TP is 11 nanoseconds that we have just computed. So it will be 165 nanoseconds. So option B will be answer. So these type of simple questions also come in hazard side instruction pipelining. Okay, this is a basic hazard question. Okay, now we'll go more deeper into the hazards concept. So pipeline hazard, right, are what are situations that disrupt the smooth execution. So everything was happening smoothly. At each cycle I was getting a new, like I was able to execute a new instruction, only I was taking one extra cycle, but I had to put stalls because there were some problems in the execution of the instructions, right, multiple instructions. What were the problems? Problems were like branch prediction, branch was there, data dependency also will be there. Now we will study the data hazards, and structural hazards. Structural hazard means same resource. Okay, so we'll see that. So what happens, it leads to delays or inefficiencies. Okay, so hazards, these are actually what, these are problems. These are the problems that I face while implementing my pipelining, instruction pipelining, occur when the next instruction cannot execute in its designated clock cycle due to some issue, right, like branch prediction or something. These delays introduce stall cycles, also called as pipeline bubbles. Why pipeline bubbles? Because my pipe, right, pipe was supposed to be smooth here, like water was supposed to flow smooth here, but there were a few bubbles here due to hazards. It got stopped, bit of water flow got stopped at that particular region due to a hazard. Okay, that's why it is known as bubbles, pipeline bubbles as well. Okay, so this things we learned, there are mainly three types of hazards. Okay, so first one is the data hazard, or also known as data dependency. So let me take an analogy. Okay, in a team, person A is working on task 1 that produces data for person B's task 2. So you are working on a project. Okay, so like what happens, let me give you an example of a like in the semiconductor industry, right? So I am designing a particular chip. I'm designing a chip. Okay, if I don't design the chip, then how will the person, like I am designated to design the chip, and person B has been designated to test the chip. Whatever I have designed, he or she will test the chip, right? If I am not able to design the chip, how will the person B test the chip, right? If I have not even designed the chip. So there is some data dependency, right? Only until the time until which I am able to finish designing the chip, then only that person will be starting his test, right? Else how will he or she start the test? So that person has to wait for me to finish my task, then only that person can start his or her task. Okay, so there is a data dependency between the two tasks, two instructions, right? That is what is happening. Person B cannot begin task 2 until person A finished task 1, causing a delay. In pipelines, data hazard occurs when one instruction depends on the result of the another instruction that is still in execution, still in progress, causing a stall until the required data is available. Okay, just like that, right? I told you, right? An example. Let's take example here. Here, this occurs when the instruction depends on the result of a previous instruction that is still in the pipeline. Instruction 1, add R1, R2, R3. So I have to add R1, R2, R3, and I have to write the result in R1. Then instruction 2 tells me to subtract R4, R1, R5. So what it does is it reads from R1, right? It writes to R1, it reads from R1. Okay, so we subtract R4, R1, and then store it to, like, sorry, we do something, right? We do something, add something, and then store. Okay, that, but important point is we are writing back here to R1 and we are reading from R1, right? So what was supposed to happen is that I was supposed to update my value of R1, then I use that value in the second instruction. But if I simply do the pipelining, right, there will be some problem. So like what it is doing R1, like is storing the value R2 plus R3, and my R4 is basically R1 minus R5. Okay, so obviously I had to use this updated R1 value here. But if I just simply use my pipelining, what will be the problem? Let's see. First I will fetch the instruction I1. It has been fetched. Then I will decode, control unit will decode, and simultaneously I will fetch my instruction I2. Here I will do the operand fetch. So what will this operand fetch do? It will fetch R2 and R3, right? That's what it will do. Okay. And here I am decoding in the instruction. So control unit understands that, okay, I have to do what? I have to simply perform subtraction operation. That is what this decode operation understand. This is addition operation. Here I am executing. So here the ALU will be in use where it will execute R2 plus R3, and let's initially assume that initially R1 was equals to 0 initially. Okay. And here, right, what was supposed to happen? Here operand fetch was supposed to happen, right? After decode, operand fetch was supposed to happen. If I do operand fetch here, what I will fetch? I will fetch the operands, right? I will fetch R1 and R5. So currently what is the value of R1? You will say currently the value of R1 is R2 plus R3. I will say wrong. You are wrong. Why? Because I have not updated the value of R1 yet. This is the stage where I update, write back. At write back, I update the value of R1. I computed, I evaluated my operation, and then I have to write back in the 6th cycle. I haven't yet written back to the register. So if I do the operand fetch here, it will simply fetch R1, that is 0, and R5 will be still there. R5 will be some value, which is wrong actually. I don't want this. I wanted R2 plus R3 here, right? I didn't wanted this. So that's why I cannot simply have a operand fetch here, right? Cannot fetch the operand here because I will fetch the wrong operands. So here I will fetch the wrong operands. Okay. So I have to wait. I have to wait till write back. After this write back only, the operands will be updated. Registers will be updated. Okay. So after this only, after the 5th clock cycle, I will start my operand fetch. Okay. After here only. Actually what we do, there is a term known as operand forwarding. As soon as I do the execution, right, it can actually directly forward it to the next instruction. There is one shortcut. Okay. There is one shortcut. So that's why I have only put one stall, but I have basic idea you have got, right? So after this write back, I am supposed to start my operand fetch. I cannot simply start my operand fetch here. Decode instruction can be here, but operand fetch I have to wait till write back, or there is a concept known as operand forwarding that I will come to in the next few slides. That does what? That after this execution, right, that instantly gives it to the next instruction. So now let us understand with the example what will be the exact problem. Okay, so here, if let's say for 3 cycles, right, my initial values are given. Okay, for 3 cycles, first, second, third cycle. Just assumption this is not exactly this first cycle. I'm just assuming initially the R2, R3, R5 values are this. So initially I want to perform what? Actually, what result should I get? What do I want to perform? I want to perform this operation and this operation, right? So actually what should have happened? So correct scenario. So in the correct scenario, what should have happened is first I should have added R2 and R3, okay, and stored it in R1. So R1 equals to, like I will write here the operations, R1 equals to R2 plus R3, and R5 is equals to R1 minus R4, I believe, R4 or something else. Sorry, R4 equals to R1 minus R5. So what I can say, for this first cycle, R2 plus R3 will be 3, right? 1 plus 2, it will be 3, and R4 should be R1, this is 3, minus R5. R5 is also 3 here, right? In the first cycle, R5 is also 3. So it will be 0. Okay, this is the cycle 1. And in next cycle, what should happen? In next cycle, again, the values of R2 and R3 and R5, all of them will be updated. So R2 will be 4, R3 will be 5. R2 will be 4. So my what will be my R1? R1 will be 4 plus 5 equals to 9. And what will be my R4? R4 will be 9 minus R5. R5 is 6 equals to 3. And in cycle 3, my values will be what? R1 is equals to 7 plus 8. So it is equals to 15. R4 will be equals to R4 will be equals to this 15 minus 9. Okay, 15 minus 9. So that is the case over here, right? Now what you should understand is that this is the correct scenario that should happen. The result that I am expecting 3, I am expecting 0, I am expecting 3, and I am expecting 9. But what is actually happening? Actual scenario. What is actually happening is very different than what should I get. So for that, right, I will actually take this picture with me so that you will understand this better, and obviously the cycle as well. Okay, this I will reduce. And the table as well. So I'm assuming this cycle 1 represents the cycle when the operands are fetched. So here I have fetched my operand of the first instruction, right? First instruction should do this R2, R3, and R5. This should fetch this operands. So the instruction I1 has fetched all this, right? So in the cycle 1, okay, or in the instruction I1, what will happen is it will fetch R2 equals to 1, R3 equals to 2, and R5 equals to 3, and obviously store in its own general inside register, right? Own registers. It has fetched the operands. After fetching the operands, it will go into the execution phase, correct? And it will execute what? It will execute R1 equals to R2 plus R3, and R5 will be equals to this is the first instruction, right, that it will do. Okay, this is only the instruction that it will follow. Okay, because what we assumed I1 instruction to be, I1 instruction was supposed to be only adding R2 and R3, right? So it will add R2 and R3. Okay, but the problem is simultaneously as I am doing this execution, I am fetching the operands, right, for the second instruction, that is for the subtraction. That should not happen. Actually, I only should fetch the second operands after finishing this addition, because this R1 actually is dependent, right? After only the value gets updated, I should use in the second instruction. I should not use the old value. So what will actually happen is that in the instruction I2, it will fetch the operands. It will fetch what? It will fetch, like, it doesn't need R2, it only, okay, this also doesn't need R5. It only needs R1. So what operands it will fetch? It will fetch R1 equals to 0. Why it will fetch R1 equals to 0? Because initially, if nothing is mentioned, I have assumed all the initial values of the registers to be 0. So it will not update the value here, right? R1 was supposed to be R2 plus R3, but it will not fetch R2 plus R3 because this operation hasn't been completed. ALU needs some time to complete the addition, right? Simultaneously, we are executing and fetching the R1 operand, okay? So R1 hasn't been updated yet. So what I do is I fetch R1 equals to 0, and obviously R5 was initially 3 only, correct? R5 was initially 3 only. So we fetch R5. So now what it will perform in its instruction to execution cycle, it is supposed to perform R4 equals to R1 minus R5. So we will get answer minus 3. Was I supposed to get minus 3? No. I was supposed to get 0. I was supposed to get 0, right? But I got minus 3. So it will go on like this. Why is there any problem? Because before updating the value, I am taking the operand, right? I have to update the R1 value, then only I should take the operand. If I update the value later and I take the operand before, obviously I am not using the latest value. I am using the old value. That calculation is wrong because I was supposed to get 0, but I'm not. So that's the advantages of sequential processing, right? Sequentially, if something is dependent on the previous instruction, right, it only finishes the previous instruction, then only comes to the current instruction. It doesn't do everything simultaneously, like stages of everything currently, because this stage execution or operand fetch is dependent on the previous stage execution, just like branch type instruction, right? So there is a data dependency of the previous instruction. So what is happening? There is data dependency of previous instruction. Okay, so that is the problem for this. Okay, so one more thing I am able to explain you, and it is taking you so much time to understand, right? So pipeline itself doesn't have any intelligence. It is very dumb, like computer is very dumb, right? So pipeline is not that intelligent to understand where is their data dependency. Okay, so pipeline or the architecture itself cannot understand if there is some data dependency or not. It is very difficult for us to find out data dependency. Okay, if I find out, okay, I got to know that there is data dependency here. So what I will do, I will just give a stall cycle here, right? After the execution phase, only after this I will do the operand fetch, correct? So that is the problem. Pipeline itself doesn't understand if there is a data dependency or not. Okay, so pipeline I will write here. Pipeline by itself won't be able to understand won't be able to identify data dependency on its own. Okay, so obviously someone has to identify this. Who identifies this? Okay, so the compiler helps in this. Compiler helps. Okay, the compiler understands the instruction, so it adds stall cycles or NOP. NOP means no operation, or it performs, or some instruction. which are not interrelated. So what do I mean by that? So what happens is, if I have a C code, right? Let's just say this is the C code. Int I equals to 5, I plus plus, then while I not equals to 7, do something, right? Like x equals to y plus z, and initially there were some values, right? X equals to y equals to z equals to 0. Okay, something like that. You do something like this. So what we do is, compiler breaks it down into smaller micro operations, right? That is the task of the compiler. It breaks it down. Then what it does is, it understands if there is a data dependency between the previous micro instruction and the current micro instruction. So if there is, compiler is a smart person. Compiler is smart, not like us. He is a very smart person, he or she. So it actually gives a stall cycle between these two micro operations. Okay, and sometimes what it can do is, in this particular cycle, right? If we want to utilize this cycle, because this cycle is just idle, what we can do? We can do this instruction, check this instruction. If like there is a data dependency here, so we can just check this instruction, right? Or something like that. It will do, but most cases it will do no operation. No operation means just idle. It is sitting idle. It is not doing anything. So here, just understand this. Data hazards are very, very dangerous. First thing is hazard, but we will also be able to not know if there is a hazard or not, because our results were getting wrong results, but only after me doing manual calculations and comparing with the actual values, I'm understanding, okay, I'm getting wrong results. But this, if you are in the CPU and just doing some computations, right, you assume that computer always gives the right answer. So how will you know that you are actually getting the wrong answer due to the data dependency or hazards? So obviously we have to add stall cycles. Compiler adds the stall cycles. So here, like that is only written. A standard instruction pipeline cannot detect data dependency on its own. The detection and resolution of this dependency often require additional mechanism. So first one I have explained, that is a software mechanism, that is like compiler. Okay, so software solutions, delayed load. The compiler rearranges the instructions to introduce NOPs, no operations, or non-dependent instructions between the dependent ones. So here, what we do, we add a, between the instruction 2, right, we add a no operation. No operation, right? It also has all the 5 stages: instruction fetch, decode, operand fetch, execution, write back. But it is not doing anything. Literally, it is not doing anything. Okay, just there is a dummy operation. We can also say it is a dummy operation which has no use except just giving a stall cycle. That is the only thing. Dummy. Okay, this allows sufficient time for the previous instruction to complete and avoid stalls. Okay, so that is the case over here. So there can be hardware solutions as well. What is the hardware solutions? Hardware solution is, what we can do is, we have a opportunity. What is the opportunity? As soon as the execution phase is done, right, here, as soon as I execute the value, I instantly send it to the next instruction. Okay, I don't wait for the write back. Because after execution, right, I store it into a register. Remember, we have a buffer register to store between the stages. So I instantly give it to the buffer register, and buffer register instantly give it to the operand fetch. Okay, we don't wait for the write back. So that is what we do, because for currently what we have to do, we have to wait for the write back, then only I can do the operand fetch. This is also wrong. Operand fetch should be here actually. Okay, so currently what we're doing is, I have to wait for the write back. This will be again stall. This will be operand fetch. This will be execution. Currently, I have to wait for the write back. It writes back to the register R1, and then only I will do my operand fetch after this. But we have a hack for this. What is the hack? So this also is wrong, right? Actually, operand fetch, execution, and write back. So what we do is we bypass the write back stage. So what are the telling in team? Let's take the analogy. Person A can share the data as soon as it's available, even before completing the task 1 fully. So person B can begin with task 2 without waiting. So I have a project, right? And in the project I have to do some simulations and some things. Okay, so what I have to do, I have a manager, so I have to show my manager my work. Okay, just hold on. This charge is not happening. Okay, this plug got out. That is the problem. Just 1 second. Oh, it's fine. So what I was saying is, just hold on, I will check if everything is fine. Recording, yeah. I have to tell my manager, show my manager that this is the design. I have to create a PPT, then show him. One thing I can do, as soon as I design my, let's say I am designing a amplifier. As soon as I design the amplifier, I don't wait for any documentation or just PPT creation something to show my manager. I instantly send it to the person B, okay, for him to start the task. I don't wait for approval, right? I know this is okay, this is correct, so I will send it to directly to person B, and he can start his work, and in between I will create my PPT and all those things. So parallelly we can do all these things, right? So that is what this means by forwarding, operand forwarding. So in the team analogy, person A can share the data as soon as it's available. As soon as I complete my building of amplifier, I don't wait for PPT creation, I don't wait for documentation, I don't wait for approval. I send it to person B for him to start his task. He can begin his task without waiting. So this is the concept of operand forwarding or bypassing. Allows dependent instructions to use data directly from the previous stage without waiting for the write back. Okay, without waiting it for it to be written back to the write back stage. Directly from the execution stage, I can directly send it. Okay, so that is what we do. So what we do here is that we don't wait. Okay, even though we have done operand fetch here, this execution actually takes the data from this execution. We do some operand forwarding. Okay, so it is a internal hardware mechanism. What happens? Basically I have registers, right? After the execution finishes, I have registers in the stage 1, right? This was my stage 1, and here I had a register. So what we do, like stage 2 has 2 options. Stage 2 has 2 options. Either take the operands from the memory or take it from the registers. So what it will do, it will take the operands directly from the registers. So it is internal hardware mechanism, very difficult to build, but it is one way to avoid this data hazard. Okay, so we take the value from this execution, output of the execution, to the input of the next execution stage. Okay, so here we bypass the write back stage. So that is what operand forwarding is. We take the value from previous execution stage. Okay, forwarding from previous execution. So this is my operand forwarding. Operand forwarding is. So we take, like this is also known as the buffer register. We directly take from the buffer register. So here what I will say is we directly take the operand from the buffer register. We don't wait. Okay, we don't wait for it. So that is the important point that I wanted to talk about. Now there is an important thing. Okay, this is only possible when I am doing some ALU to ALU operation. Okay, no stalls will be introduced. But if I am doing some ALU to memory operation, operand forwarding, stalls will be introduced. What do I mean by ALU to ALU and ALU to memory? Okay, what do I mean by that? So I will explain that. Just hold on a second. Yeah. So what does ALU to ALU mean? Here, right? whatever like in the next stage, where do I need the data? Next instruction was the what? Next instruction was R4 equals to R3. R4 was stored with R1 minus R4. So all these, right, are present within the ALU because they are general purpose registers, and we know GRPs are within ALU. What if I told you to do this? Memory location like R3, like this. What if the instructions are this, right? First, my M1000 equals to R2 plus R3, and R4 equals to M1000 minus R5. Now, can I use ALU? Can I use operand forwarding here? Can I use operand forwarding here? The simple answer will be no. No. Why? Because actually I am not like storing this addition value in a register. Okay. Previously I was storing it in a register in the pipeline register somewhere, but now I am actually not storing it in a register. The instruction has said me it is not storing it in a register. It is storing it some memory location. Okay. We are storing it in a memory location. So I cannot instantly take from this memory location value, right? I cannot, because accessing memory location is very, very slow. It takes time to access the memory. So if I am doing some ALU to memory operation, operand forwarding is not possible. We have to introduce stalls only. So we don't have any other way. Okay. So operand forwarding here will not be possible. Don't worry. We'll understand this more with questions. Questions will come. There we'll understand this more better. Operand forwarding. Not possible. Okay. So that is the case. So sometimes what we do is we introduce hardware interlocks that actually has the capability to detect the hazards. It can detect the hazards and introduce stalls until data dependency have been cleared. So it will introduce stalls until data dependency has been cleared. So like it is just like software where the compiler understands that there is a data dependency and it gives some no operation or stalls. Here the hardware will give some no operation and stalls. Okay. So that is the thing. Like, why is it called hardware interlocks? Because each of the instructions, right, each of the stages, each stage has a log associated with it. So what happens as soon as I do the operand fetch, right, and I understand in the next instruction that I have to use the operands of the previous instruction, not instruction phase, sorry, in the decode phase, that I have to use the operands of the previous instruction. So I put a lock here. Lock. So this, like the next instruction, right, will not be able to use this operand fetch until the lock is unlocked. When will the lock be unlocked? Here, right? Here, that after the write back only, this will be unlocked. Okay. So actually this also should have been a stall only, because after write back only, like it depends, right? Sometimes in the question they tell you at write back the register actually is written, at execution sometimes also ratio is written. It depends how the question is framed. So you will solve according to the question. You don't know whether you have to provide one stall cycle. If I provided only one stall cycle and I'm doing operand fetch here, my assumption is that in the execution phase itself the data has been written to the register. That is my assumption. Okay, I can be wrong as well. Okay, it depends on the question. So like also you can understand with this analogy that we have blocked the pipe. The pipe is currently blocked. Okay, so you can understand this as well. Now there are many types of hazards. Okay, so one is read after write. Like there are many types of data hazards classification. So first one is read after write. So whatever this written, right, this actually what actually needs to happen but is not occurring. So this is the thing that actually needs to happen. Okay, that actually needs to happen, needs to be done, or needs to be done. What do I mean by this? Once we see the example, we will understand. This is also known as true dependency. Why this is known as true dependency? We'll understand this with when I compare it to the other types of hazards. In short, this is also known as raw. Okay, raw, like that. So definition: a raw hazard occurs when an instruction J reads the value from a register or memory location before the previous instruction I writes on it. The example that we have just used. So instruction J, that is this second instruction, gets the old value instead of the updated value from the instruction I. So I have instruction I, right, where my R1 is A plus B. Okay, R1 is A plus B, and my R2 is R1 into C. Correct. So if I am using pipeline instructions, it will take some time for me to execute, right, and update the value of R1. But before updating the value of R1, I am using this R1, right? Initially R1 was 0, so I am using this R1 here. So there is a dependency between this previous instruction and the current instruction. So I am reading the value of R1 before it gets updated. So read after write. What I should have actually done, after writing, I should have read the value of R1. Okay, but I am not doing it. So that is what it means. Read after write means I am reading it after write. That should actually would have happened, but I am not doing it. I'm not doing it. I'm not reading after writing. I'm reading it before writing. That is the problem. What should have actually happened? I should have read it after writing, but I'm not able to do it. Okay. So here, like the same example is given only. Assumption, just understand in the question it will be given that assumption is, just understand one thing, that assumption is that at execution phase, the GRPs, right, or the general purpose registers gets updated. Because general purpose registers are connected with ALU, so it will not take me much time. Here write back, right? Write back generally is write back to the memory. Okay. Execution, it executes the value and stores it in general purpose register or ALU. So it is internal to the ALU. So that's why assumption is my operands are ready for after this execution phase only. That is my assumption. Okay. In the question it will be given. We'll solve questions. You will see. Don't worry. We'll solve the questions. Okay. So here what happens? J needs the value of R1, but R1 is updated in the actually not in the write back stage, in the execution stage actually. Okay. In the execution stage. That is my assumption. Not in the write back, in the execution stage. If J reads R1 prematurely, if I read R1 here, right, even like before the execution stage has completed its operation, what will happen? My second instruction will get the previous value of R1, not the current updated value. So I am not doing read after write. I'm not doing read after write, right? So that is what is written. R1, it will get the old value. Old value of what? Old value of R1. Okay, so that is the one issue that you should know. Then is read after write. Read after write. So how we can negate this read after write problem? So we can use operand forwarding that I have just explained. What we do is, after this execution phase, right? After the execution phase, what happens? It is written to the registers. So as soon as it's written to the register, I send it to the next stage. Okay. Actually, this is I send it to the execution phase of the next stage. So here I send this to the execution phase of the next stage. So this execution stage, right, of the second instruction, it uses operands from the previous execution and not this. It does not use this. Okay, so this is just a waste. This is also like a stall cycle. This is just a waste, right? So we use the operands for this execution from the previous execution phase. After executing, operands are ready, right? Operands are ready here. Okay, so I instantly send this operand here. I instantly send as soon as the execution phase is done, right? So that is what we do in the operand forwarding. But remember, this is only possible because this is a ALU element, right? R1 is a general purpose register, that is a ALU element, and this is also a ALU element. R2 is also a ALU element. So I know ALU to ALU operation is very fast. I cannot do something if it is stored in memory. I cannot do that. Okay, I cannot do that. So just be careful about that. We'll do questions that will understand. Also, we can introduce interlocks, which stalls until the I completes, until the write back phase of the I we stall. That we can do. Okay, anything. Now there is another type of data dependency that is known as write after write. So this should have actually happened, and this is also known as false dependency or write dependency. Why is this false dependency? I will explain that. So in instruction I am writing on R1 A plus B, and in instruction J, that is the second instruction, I am writing on R1 R2 into C. So finally, what value I should get? Let's take an example. Let's take A equals to 2, B equals to 3, and C equals to 4, and R2 equals to 1. So actually what I should have gotten, I should have gotten my R1 equals to A plus B, that is 2 plus 3, it will be 5. Then I should have updated my R1 equals to R2 into C. R2 is 1 into C is 4, that is 4, correct? Now tell me, pause the video and comment below. Does this second instruction J, does it need to wait for the previous instruction? No. To calculate all this, right? Do I have any dependency previously? No, I don't have any dependency. It just overwrites whatever was previously written. Do I care about this value? If I would have cared about this value, I would have stored it somewhere else. If I would have cared about this previous R1 value, I would have stored it somewhere else. So if I really need this value, I will store. We can store. I will just write it here. We can store it in some other register if I really need this value. Okay, so that is a case over here. If I really need, I can store it in some other register, but actually I don't need. I don't like the user may have known, right? That's why he is overwriting it. Okay, so both instructions write to R1. If J completes first, then its results override the correct value computed by I. So do I care about this? No. Okay, I don't care about this. So that's why this is known as false dependency, because the previous instruction actually, like the current instruction is not depending on the previous instruction. Yes, there are like registers which are same, which are getting used, operands which are getting used in the previous and the current instruction, but there is no actual dependency per se, true dependency. This is false dependency because I don't care about this. So even if I do execution here, okay, this is a bit wrong. Operand fetch is here. Okay, this right. This is again wrong. This should be decode instruction, operand fetch. Execution and then so even if this has written back something, do I care? Do I have to wait for this execution phase? No, right? I can fetch the operands because these operands are totally independent. R2 and C are totally independent of the previous operands, right? So I can totally fetch R2 and C here and I can perform my execution and then I write back. I don't care whatever was written there previously R1, because finally I want this value only. So it doesn't matter. Okay, so I can show you an example as well. Okay, so like here I've shown you example only because at the end I want 4. Previously my R1 was supposed to be 5 here, but I don't care about this. Finally I care about this only. So R1 is 4 only. So I don't care about this. Okay, so that is the important point that I wanted to talk about. So here its analogy is given. Two people are editing the same shared document, and the second person saves changes before the first person completes the edits. Will it change anything? No, right? Obviously the second person can also save the edits. Okay, so it doesn't, there is no actual dependency. So what is the solution? Because if I want to really store this value, right, previous value, I will just store it in some other register. So we do register renaming, allocate separate registers to avoid conflict. If I'm writing after write, so I will allocate this separate register so that it doesn't override the previous value. Okay, that is just simple solution. Compiler can do these type of solutions. Okay, so this change has been changed to, from R1 this has been changed to R2. Okay, that is what we do. Next type of dependency, only there are 3 types of dependency, is write after read, war. We are going on a war. Okay, that is also known as anti-dependency. We'll understand this. So a war hazard occurs when an instruction J writes to a destination before a previous instruction I has read from it. So what should have happened? Write after read. Only after reading I will write to that register, but I have already written to the register. That is a problem. So here what is happening is, I have instruction I, that is R2 is equals to R1 plus B. R2 equals to R1 plus B, and R1 is equals to C minus D. Okay, so what I am supposed to do is, I am supposed to read from this R1, okay, first, and then add these two up and then store. Okay, store. So what was supposed to happen is, let's say R1, I will take the same example only. R1 is 1, B is 2, C is 3, D is 4. Okay, these are the things. So R1 is 1, B is 2, C is 3, D is 4. Now what if happens, like what should have happened is, R2 should be equals to R1, that is 1 plus 2 equals to 3, and R1 equals to C minus D, right? So C is how much? 3 minus 4, that is minus 1. This should have actually happened, but due to some glitch, some problem, first I should have happened and then J, right? But due to some problem, J is happening, then I is happening. Then what will be the problem? Then my R1 will be equals to 3 minus 4, that is minus 1, and my R2 will be equals to R1 plus B, right? R1 is what right now? R1 is minus 1 plus B. B is 2. So it will be 1. So actually I am not getting the correct answer here. I should have gotten 3. R2 is equal to 3. I am not getting the correct answer. So that is why I am writing, like I should have written after read. I should have read this register first, then I should have written, but I am not doing it due to some problem. Okay, so that is the problem, that is the hazard. But will it actually happen ever in a pipeline system? No, right? It will never happen. That's why this is known as anti-dependency or false dependency, because everything happens sequentially. This is also known as false dependency, because yes, this is correct. Dependency. Yes, it is correct. It is correct that there is relation between the previous instruction and current instruction, right? There is some shared memory between the previous instruction and current instruction, but that is actually a false dependency. That is not a problem to us, because obviously I'm reading that here first, then I'm writing it. That is totally allowable. So what we do is, this is actually R1 equals to A plus B and A equals to C minus D. They have given some other example. Okay, that is the problem. This should not, this is wrong actually. Lot of things are wrong. Okay, so R1 equals to C minus D. So here what is happening is it a problem? So I'm doing the instruction of fetch, then decoding, then doing the operand fetch. So I'm reading R1, and here I'm decoding the instruction, and this is actually wrong again. This is wrong, and this is also should not be execution. This should be operand fetch, and this should be execution. So here what is happening is I'm reading from R1, and operand fetch is fine. All these are independent. All operands are independent. Okay. And I'm doing execution. Execution will do what? It will write into R1. So obviously I'm reading before writing, right? Write after read. So every time A is there, so it will be always write after. It will always after. So I'm writing on R1 after reading. So it is totally fine, right? It is totally fine. It is totally fine. Okay, there is no problem with this. That's why this is known as false dependency. We don't need to add any stall cycles, nothing. We don't need to do anything. Okay, so like what happens is what is the analogy of real life? Someone starts erasing content from a shared notebook register before their friend finishes reading it. Okay, the problem would have been if we have both Ramesh and Suresh have a shared notebook. They go to class and they write on the notebook. Okay, so Ramesh will study that subject first, then Suresh. So what happens is Suresh first studies that from the notebook. Okay, we have only a notebook, single notebook. Okay, Suresh first studies from that notebook, and he studies, right? He has finished his study, Suresh. Then he gives it to Ramesh, and then Ramesh is a bit smarter than Suresh, so he writes, he edits the notebook, right? He writes the things that he have understood better or in his own language. So he writes on the notebook, Ramesh. Will it be a problem to Suresh? No, because Suresh already has completed his study, right? He has already completed his study. So it's okay if Ramesh does anything with the notebook, because Suresh has done his job. So he doesn't need to go back to the notebook. Ramesh can do anything. So that's why write after read is a false dependency. There is no problem of me writing after I have already read the register. But what would have been a problem? If Ramesh would have told Suresh, okay, just give me the notebook first, I will read first, okay? But he edits the content, he changes the content, he erases the content. Then he gives back to Suresh. So few content have been removed. So Suresh will not be able to completely study the subject because few topics have been removed by Ramesh. So then it's a problem. Okay, but the sequence should always be followed. Suresh will get first, then Ramesh. But due to some reason, sequence is not followed, then obviously you will have dependency, you will have a hazard. But generally there will not be an hazard, because if you follow sequence, everything is sorted. So that is what is written. If I don't follow sequence, this analogy is written according to the not following of the sequence. If I don't follow the sequence, then this will be a problem. Okay, provide each with their own copy. Again, what we can do is to have this, they should not share the same notebook. take a print out of the notebook and share it to both Ramesh and Suresh. They can do whatever they want. Okay, so we do register renaming, same as previous dependency. If this problem happens, if this hazard happens, okay, so we can use a temporary register to store the intermediate value. So R1 can be used as a temporary, temp1 plus b and temp2. Okay, all this we can do simple register renaming. Okay, so what we need to understand is how many cycles can data hazards affect. Okay, can I calculate that? So here I am giving you a question. I have In each cycle, I'm doing these type of operations, right? In each cycle, I'm doing these type of operations. Now, can you tell me how many cycles I need to wait here? How many cycles I need to wait? Can I find it out? It depends. Because here, where is data dependency? Where is the data dependency? All these are different registers. But here I am observing I need this value of register R1. And R1 previously getting used? Yes, R1 is previously getting used actually. So from here I am using R1. Correct? So I am using R1 previously. So there is a data dependency. Data dependency. Now can you tell me what type of data dependency is this? Data dependency. What type of data dependency is this? Can you tell me that? So this data dependency, right, is basically just see what is happening and just see it. Okay. So what I am doing, I am writing, not that, I am reading from this register after write. So after I have written it here and I am reading from it, right? I am reading and incrementing it. So I'm reading after write. I'm reading after write. So this is a raw type of data dependency. I'm reading after write, which is a true data dependency, which is a problem. Okay. So it depends, like how many cycles can it affect, how many stalls I need to give. It depends. Like I have this many number of instructions in each, after each cycle, this many number of instructions are happening. So to answer this, the simple answer will be it depends on the number of stages of a pipeline. Okay, because in between, right, this many instructions are happening. So if I have 3 instructions that are already happening and I have enough space between these 2 dependencies, then I don't need to provide any stall or no hazard will be caused. But if there is not enough space, right, if this instruction is directly here after the first T1 clock cycle, then I may need to provide clock cycle stalls. Okay, it depends. We'll see a few questions and from that we'll understand how many stalls we need to provide. We'll understand this, don't worry, we'll understand this. So this is a summary basically of different types of data hazards. Okay, summary of different types of data hazards. You can read this, go through this and like remember and put it in your short notes to quickly recall everything. So try to solve these 2 questions and then I will solve. Pause the video, try to solve this one and this one. Okay, these 2 questions and then I will obviously solve in front of you. So let's start with this one. Okay, so what is this question telling? It is a very big question, so we have to read this. A pipeline processor has 4-stage instruction pipeline with the following stages. Instruction fetch, so it is a 4-stage pipeline and it has the following stages. First one is instruction fetch, then we have instruction decode, then we have execute, and then we have write back. So we don't have any operand fetch, right? What does the operand fetch happens? Intuitively I can say operand fetch should happen here in the instruction decode, here only, or in the execution. They haven't told me, right? The arithmetic operations as load and store operations are carried out in the execution. They will tell you what happens. Okay, so ALE operations, arithmetic operations are happening in the execution phase. The sequence of instructions corresponding to the statement S equals to R into P plus Q by T is given below. So sequence is given here, right? Okay, the value of the variables P, Q, R, S are stored in these registers before the execution of the instruction sequence. So they are stored somewhere in this register, general purpose register. This is a ALU. All these are in ALU, right? The number of read after write, raw dependencies, write after read dependencies, and write after write dependency in the sequence of instructions are given us. So you have to just identify how many read after write, that is raw, that is a true dependency. Remember, this is the true dependency. That is the actual problem for which I have to give stall cycles. And all these write after read, also known as I'm writing not after write. So what is write after read? It is a anti-dependency. Why? I have already read from it and then I'm writing, so it is not a problem. So that's why it is anti. It is opposite of dependency. It is not dependent. Okay, and write after write is false dependency, because I'm like, there is no dependency. There is a dependency that I'm writing again. I'm writing, but I only want to see the updated value, right? So it doesn't matter. That's why it is a false dependency. So we have to identify the number of var, raw, and wow. Okay, wow dependencies. So let's start with the raw dependencies, read after write. So here I'm observing that I have to first see where am I like where are the dependencies. This is R5. Here I am writing and then I'm reading. So I am reading after writing. I am reading from R5 for this instruction multiplication. I'm reading from R5 after writing to it. So there is obviously a raw dependency here, right? So 1. Then again, if I observe here, again I'm reading from this register R6 to perform this operation after writing, right? Again there is a raw type operation. Okay, dependency, not operation, raw type dependency. Again if I observe this R4 is here, R5. Again this R5 is required, right, to perform this operation, and I am writing just before this instruction, right? So again I'm writing after, sorry, I'm reading after writing, so it is again a raw type dependency. Again here if I see, I'm reading directly, storing this value R6 in the X memory location. So obviously this value is written here and then I'm reading from it. So again there is another raw type dependencies. Total I have 4 raw type dependency. So obviously from the options you can see only in the one of the options there is present 4 raw dependencies. Option C will be correct, obviously, but we will obviously solve the other options as well. So this one was for the raw type dependency. Let's solve for the var dependency. Var, I'm going in a var. Okay, so write after read. So what you have to search, you have to search where I am writing after reading. So here if I observe, this is fine, this R2 is here. Okay, so okay, write after read, right? Write after read. So I'm searching for this. R4 is here. Okay, I'm writing after reading. So okay, just let me search few things here. If you see, I am reading from this R5 and then I'm writing after this instruction, right, which is not a problem. So I'm reading from R5 in the previous instruction and then I'm writing. So I'm writing after reading. Reading has been done, then I'm writing. So it is a var type dependency. Then here as well the same thing, right? Shortcut is, if arrow is like this, then it is a var type dependency. If arrow is like this, then it is a raw type dependency. Okay, but it is a var type. Sorry, if arrow is like this coming from right to left, it is a var type dependency. If arrow coming from left to right, it is a raw type dependency. But I don't want you to just mug up the shortcut. I don't want you to do that. I want you to understand conceptually what is happening. So I'm reading after, I'm writing after read, right? I'm writing after read. So I have already read this R5 value, then I'm writing on it. So it's a raw type it's a var type dependency. It's a tongue twister, sorry for that. Okay, here also same thing, right? I am writing on R6 after reading R6, right? After R6 read has been done. So again it is 1, so total 2. And here also if you see, for wow type dependency, right? Wow type dependency, what will happen? The arrow will be something like this. So I'm writing after write. So here I'm writing R5 and again here also I'm writing R5. So it is a wow type dependency. Again, if I see here I'm writing on R6, again here I'm writing on R6. So again it is a wow type dependency. Total I have 2. So 4 to 2, option B will be correct. Pretty simple. I hope you understand. Just whatever is written, right, that you need to identify in the instructions. That's it. You have to search for that particular thing in the instructions. They have mentioned exactly what is raw. You don't have to remember the full form as well. They have told you read after write. They told you write after read. Everything they will give you in the question. Don't worry. They will give you. In today's GATE questions, they mostly give everything in the question. Okay, itself. Few things that my students understand that they need to remember. They understand that pain, so they don't tell you to remember everything. Okay, they just want to see the conceptual knowledge, whatever you have gained. That is the important point. So here is another question. So we have this following opcode and things are there. 5 instructions are there, and we have to perform 5 instructions, right? So what they are telling me, consider the following 3 statements. There is an anti-dependence between instruction I2, I5. Like they're talking about instruction I2, I5, and then they're talking about instruction I2, I4, And then they're talking within an instruction pipeline, an anti-dependence always creates one or more stalls. So here, right, first let's see the relationship between I2 and I5. I see I2 is here, this is my I2 and this is my I5. So what I observe is this instruction I2 and I5, right, has a write after write dependency. And what is called a write after write dependency? Write after write dependency, if you remember, it is called as false dependency. It is called as false dependency because actually there is no dependency, because I am writing, I have already written, then I am again writing, so it doesn't matter, right? If I write after, before, I am not reading from it, so it doesn't matter. Final value only matters. Okay, that's it. So it doesn't matter. And the second statement says that there is an anti-dependence between instruction I2 and I4. So if I observe I2 and I4, right, this I2 has R1 register, R3 registers here, and it has R3 registers here in the I4, right? So what is actually happening? I am writing after reading. So it is a raw type dependency, right? Sorry, not reading after writing. I'm writing, not raw, sorry, after reading. It is a var type dependency. I'm writing after reading. So reading has been done. Only the problem lies when I fetch the operand, when I try to read the operand, right? So reading already has been done. I'm writing after reading. So it is not a problem. So what type of dependency it was? It was anti-dependency, if you remember, because there was no problem. I'm reading only, sorry, I'm writing only after reading. Reading has been done. I'm writing. So it is not actually a true dependency. I explained it is a anti-dependency, because if I swap the two, then there will be issue. Okay, if I swap the two, then there will be an issue. If I write after read, sorry, if I read after write, then there is a dependency, right? Then the write may not go through sometimes. So then there is a problem. But var is known as anti-dependence. So yeah, statement S2 is correct, that there is an anti-dependency between I2 and I4. But what about within an instruction pipeline, an anti-dependence always creates one or more stalls. Always is the important word, always. Anti-dependence actually can create stalls. I have not explained that, but it can create stalls, okay, anti-dependence. But not always. How it can create stalls? But let's say our instruction has many stages and we are not able to perform this read operation before this write operation, right? There can be a case, okay? So we have to provide stalls. But they're telling me we have to always provide stalls. In most cases, this read operation will be done before this write operation, right? In most cases, it will be done. So it is not necessarily true that I have to always provide stalls. Okay, so we'll see this with more questions. We'll solve those questions in the next lecture. We'll see this. Okay, so statement S3 is incorrect, statement S1 is incorrect, only statement S2 is the correct statement. Okay, so your option B will be correct. Okay, that I have an anti-dependence between instruction I4 and I2. So option B will be correct in this particular question. So that's it basically for this lecture. And in the next lecture, we'll learn about more types of hazards, that is branch hazards and control hazards. Okay, there are two types of hazards as well, branch and control hazards. So we will learn those hazards. Thank you for watching, and I will see you in the next lecture. Until then, happy learning. Hi everyone and welcome back to my channel. So today we'll start with the part 3 of our pipelining topic, instruction pipelining. So we have already learned about hazards. We have learned about control hazards in the starting of the introduction of the hazards. Then we learned about data hazards. So today we'll dive more deeper into the control hazards and also the structural hazards. So today we'll learn about two hazards. Mainly there are 3 types of hazards. So we learned about these two, and then we'll do questions on hazards, all the questions. Okay, so let's start with control hazards. What are they? I've already explained those previously in the starting of the hazards topic. What is it? Let me give you an analogy. Okay, so a driver is unsure whether to turn left or right at an intersection because the direction depends on the sign further down the road. Okay, what does it mean? where I have to turn, like you can take the help of Google Maps, okay, G Maps. You turn on your Google Maps, okay, and then you put the location of your home. So whether you need to turn to left of the road or to the right of the road, in which direction you need to turn, once you reach this point, right, then only you will be able to see, because you, like, let's assume that you are not able to observe the traffic. Only you are able to observe the traffic once you reach at that particular point. So from this point you are able to observe that the left turn has less traffic, so obviously you will take the right turn. Okay, so you have to wait for some condition to happen, then you decide at that point only that which turn you need to take. So this is like control hazard, because I cannot instantaneously, I am 5 kilometers before and tell that I will take the right turn. I cannot say that. I have to wait which turn I need to take. So that is what a control hazard is. Basically, the driver has to wait for the sign to make a decision. He has to wait for the traffic to make a decision, delaying the movement. In pipelines, a branch instruction causes the pipeline to wait until the branch condition is evaluated, generally in the execution phase or sometimes in the write back phase. It will be given in the question. Okay, so until the outcome of the pipeline of that this current instruction is clear, I will not be able to execute my next instructions, because I don't know if the next instruction is supposed to be executed or not, because I may have to take some other target instruction that is some other place. Okay, I7, I6, not I4. After I1, I2, I3, I may not need to fetch the instruction I4. I directly may need to go to I7 or something. Okay, so that is what your control hazard is. So it occurs when the pipeline encounters a branch instruction and must wait to resolve the branch, right? If this is, let's say this is a branch instruction, if I don't wait for the branch instruction to get resolved, what will be the problem? The problem will be that if I start my instruction fetch here and the condition of branch evaluates here, and after evaluating it is telling me target instruction, like I have to take the branch, so I have to go to instruction 6. So I was not supposed to fetch instruction I4. After this instruction I3, I was supposed to fetch instruction I6. So that's why I have to wait for these two instructions. I don't do anything in this, like in this whole operation, right? From this I will not fetch here, I will not fetch here as well. All this will be no operation. Basically all these cycles will be simply no operation. Okay, so only after this execution phase, right, finally the branch has been evaluated condition. So I will send the signal to the pipeline or something. Okay, so it will understand what is the next instruction to be fetched. So now I will fetch the next instruction. If the branch is taken, I will fetch I6. If the branch is not taken, so this will be fetched when branch is taken, and if branch is not taken, right, simply I4 will be executed, fetched. Branch is not taken. Okay, so that is the case over here that you have to understand. So next is what exactly is happening. That is, they have explained that pipeline stalls cycle 6. So this cycle, right, cycle, okay, 6 and okay 7 will not be stalled. Actually pipeline stalls during cycle 6 and 7. It not stalls during cycle 6 and 7. It actually stalls during cycle 4, 5 and 6 actually. Okay, instruction begins, yeah, 6 and 7. Why is it like it should begin fetching at 7 and okay. Pipeline stalls during cycles 4, 5 and 6 to resolve the branch. Once resolved, the instruction 6 begins fetching, thus in the cycle 7. If the branch is resolved, if we take the branch, if the branch is taken, then obviously I will go to the target instruction. The target instruction, not instruction 6, the target instruction will be fetched. It can be 4 or 6 depending on the result of the branch. Okay, begins fetching in the cycle 7. So we fetch the instruction, target instruction in the cycle 7. after these many stall cycles, right? We have to give this many stall cycles. So that is what is it telling. The pipeline is stalled and all stages after the branch instruction are emptied. Basically here, right? If let's say we would have done some instruction fetch here, we would have emptied it. We would have not done anything. We would have and then cancelled it. Basically deleted it. Okay. So that is known as pipeline flushing. If I would have simply done like you told me that don't wait. I will do my instruction fetch here. I will do my decode instruction here. I will do my operand fetch. I will again do my instruction fetch here in this instruction cycle 5, and I will do my decode instruction here. I will not wait. But actually, let's say I would have done all this, right? Then finally, after this execution, evaluation of the branch condition, I got to know that I have to actually go to instruction 6. Then whatever I have done, right, all those things I have to delete because those are of no use. Because actually those I shouldn't have taken the branch. I should not have not taken the branch. So I would have to delete all this. Okay. So deletion is also known as flushing. Deletion. Of flushing. Okay. So that is what it is telling me. It is known as pipelines are emptied or delete, also known as pipeline flushing. A general pipeline cannot inherently solve control hazards requiring software or hardware based solutions. That I have discussed in the starting of the hazards chapter, right? So how do we implement software solutions? The compiler provides the stalls or no operation. Okay. So like here, like same thing is written. If the branch condition is resolved during the ith stage of the instruction cycle, the number of stalls introduced by the branch instruction is given by I minus 1. That I have already derived in the starting of hazard, right? I have already explained why is this happening. Now, when will the branch condition be resolved? Will be given ith stage. This thing, right? When will the branch condition be resolved? Will be given in question. If nothing is mentioned, assume execution phase. Okay, you have to assume execution phase. The number of stalls, okay, this is has already been done. This represents the number of pipeline stages that must wait until the branch decision is finalized, delaying the fetching and execution of the subsequent instruction. So here, right, how many stall cycles I needed to provide? My execution was happening, my evaluation of the branch condition was happening in the 1, 2, 3, fourth stage. So how many stall cycles I need to provide? 3. 4 minus 1, 3. So exactly that is what I have told, right? 1, 2, 3. 3 stall cycles. Then again, after that, my next instruction gets fetched. So that is what I'm doing. So in this example, in our current example, I had to give my branch condition was getting evaluated in the 4th phase. So stall cycles and stalls will be 4 minus 1, that is 3. Okay, it is 3. So that is the case over there. Let's do few questions from this. We will understand this is a GATE 2000 question, which is a very, very lengthy question. An instruction pipeline has 5 stages. So K is equals to 5. I will write here K equals to 5, where each stage takes 2 nanoseconds and all instruction use all 5 stages. So like TP is basically 2 nanoseconds and all instructions use all 5 stages. So all instructions always use all 5 stages. What are they saying? Branch instructions are not overlapped. That is, the instruction after the branch is not fetched till the branch instruction is completed. So we have to complete the branch instruction, then only the next instruction will be fetched. Okay, here what does it mean? Branch instructions are not overlapped. That means they have provided as the explanation until the branch instruction is not fetched is not fetch. I will not fetch is not evaluated or completed, is not executed. I will not fetch the next instruction. Sorry, like I don't have space, that's why I had to write it like this. Okay, so that is the meaning of this. That is the meaning of the branch instruction are not overlap. Let's read the question further. Calculate the average instruction execution time assuming 20% of all the instructions executed are branch instructions. Ignore the fact that some branch instruction may be conditional. So we'll just ignore the some branch may be conditional. We'll ignore the fact. What we know is number of branch instruction, right? NB. If I have total n, if I have total n number of instructions, then out of this n not branch will be simply 80% of total number of instructions, and n branch will be total 20%. 20% of instructions are branch type instructions. They are asking me to find the average execution time. Average execution time assuming the 20% of all instructions are branch type instructions. Okay, so let's first solve the first one. Okay, so when does the branch condition gets evaluated? So here they have told me branch condition will be evaluated after the instruction gets completed. So at what stage? If I have for the option A, I have total 5 stages, right? S1, S2, S3, S4 and S5, and they're telling me only after the branch instruction is completed, then only I can start the next instruction fetch. So obviously stage 5 will be the time at which branch instruction is completed. So how many stall cycles and stalls I need to provide for every branch instructions? And stall will be what? It will be, this is the first, second, fifth phase, right? So 5 minus 1, 4 cycles. For 4 stall cycles for each branch instructions. Okay, so I will not write install. Install will be the total number of stalls that I need to provide for how many. So installs will be what? Total number of stalls that I need to provide for how many? For 20%, that is 0.2 n instructions. If one branch instruction causes 4 stall cycles, how many 100 branch instruction will cause? 400 stall cycles. If one branch instruction causes 4 stall cycles, how many will cause? Then 0.2 n branch instruction will cause how many stall cycles? 0.2 n into 4. So n stall will be 0.2 n into 4. Okay, so it will be 0.8 n. And what are they telling me? Average execution time. Okay, so basically they are asking me average execution time, that is CPI. They are asking me, so not CPI, actually average execution time. So what is average execution time of a single instruction? Like here they should have mentioned average execution time of a single instruction. So T execution average, right, will be what? It will be total execution time, that is T execution, total execution time, okay, of the pipeline system, then divide by the number of instructions, because I have to find out the average. On average, how many each instruction take how much time? On average, each instruction take how much time? Simple arithmetic mean, divide by n. Okay, let's just take 100. I have 100 instructions. So if I have 100 instructions, out of those 100 instructions, 20 instructions will be branch time instructions. Okay. So and those 20 branch time instructions will cause how many hazards? How many stall cycles? They will cause 0.8 into n. That is 80 stall cycles. So what I need to find out of 100, on an average, each instruction will take how much time? Okay. So that I need to find out. So T execution pipeline will be total number of cycles. What is the total number of cycles? It will be K plus N minus 1 plus N stall. The extra stall cycles that I needed to provide due to this happened due to what? Due to control hazard. Control hazard. Into obviously TP divided by the total number of instructions, that is N. That is my average, T execution average of a single instruction. Okay. So this will be K is simple 5, N is simple 100, not 100, like N is N only. Okay. N is N only, because they have not provided me how many instructions actually I am fetching, right? They have not provided me the value of N. Okay. So I will assume N to be very, very high. That is my assumption basically. So plus N minus 1 plus N stalls. N stalls will be how much? Now, you cannot simply replace this N with a number, right? So I will show you one example. Let's do an example, that is assume N to be 100. Okay. Let's first do example. Assume N to be 100. Then you will understand this better. If N is 100, so my branch instruction will be 20. So my number of stalls, total stalls will be how much? 20 into 4. Each branch instruction takes 4 cycles. So it will be 80 stalls, right? So now what will be my average execution time? Average execution time will be what? This will be like I have 5 stages plus 100 instructions minus 1 plus number of stall cycles, 80 stall cycles I have, into 2 nanoseconds, right? This is 2 nano, remember this is in nanoseconds. Okay, divide by the 100. So this will come out to be, I will calculate this. This will come out to be 105 minus 1 plus 80 divided by 100 into 2 is also there. So 3.68 nanoseconds. So if I have 100 instructions, then each instruction on an average will cause 3.68 nanoseconds. But actually, this is not the correct answer. Okay, I will explain why. So now we won't be able to assume any N because they have not given N. So my assumption will be N is very, very greater than K. That is my assumption. K minus 1. Okay. So what was the formula? Formula was this, right? Formula was this. So my T execution average, my K is 5, that is fixed, plus N minus 1. How much is N stall? It is 0.8 N, right? I have already computed it. It is 0.8 N into 2 nanoseconds divided by N. Now my assumption is that N is very, very large. If N is very, very large, right, overall what will this become? This will become 1.8 N minus 4 into 2 divided by N. So if N is very, very high, just assume N to be 1000, N to be 10,000. So this minus 4 I can ignore. So this will become 1.8 N divided by N into 2. So this will become 3.6 nanoseconds. Okay, if N is very, very large, right? So execution time will actually reduce. Average execution time will actually reduce. It will be 3.6, not 3.68. I just assume N to be 100. Okay, but this is how you solve, right? You use the concept of limits. I hope you understand the concept of limits. So this is the part A. Okay, this is a very, very good question, and this is the part A basically. Let's solve the part B. What is the part B telling us? So in part B, if a branch condition is a conditional branch, so it's a conditional branch. Okay, now they are telling me if it's a conditional branch instruction, the branch need not be taken. So if it is a conditional branch, it may happen that we don't take the branch. It depends, right, on the evaluation of the condition. If the condition is true, we take the branch. If the condition is false, we don't take the branch. So that is what they're telling. We already know this. So what it means is, if the condition is true, branch taken. If it is false, branch not taken. Okay. The following instructions can be overlapped. If the branch is not taken, the following instructions can be overlapped. Right? If the branch, let's say, if the branch is not taken, right, the instruction can be overlapped because I don't have to wait. Okay. So when 80% of all branch instructions are conditional instructions and 50% of the conditional branch instructions are such that the branch is taken, calculate the average execution time. So this is a tongue twister and bit difficult to understand. So actually, what is unconditional branch? Unconditional branch means I have to take the branch anyhow. If it is unconditional, then the condition is always true. Like, I will always follow the condition, right? So I will write here, if the branch is unconditional, I will take the branch always. I will always take the branch. So that means I have to wait, right, until the current instruction gets executed, because if I am branching, then I have to wait, because they told me, right, if I am branching, obviously current instruction needs to be executed first, then I will go to the target instruction. I cannot simply do sequential operation. I cannot do sequential operation. Need to wait for the current instruction. Okay, current instruction. So I will need to wait for the current instruction. So I have to actually wait if it is a unconditional branch. So point 1, if it is unconditional branch, I will wait. Now point 2, they have told me that out of 80%, when 80% of all branch instructions are conditional, so overall branch instruction I have NB, out of that 80% are conditional, 20% are unconditional. Okay, point 1. Then 50% of the conditional branch instructions are such that the branch is taken. So 50 out of those, 50% are such that branch will be taken. So simple thing is, whenever branch will be taken, stall cycles will be introduced. So second point is, whenever branch is taken, stall cycles will be introduced. Okay, if branch is not taken, right, if branch is not taken, then no stall cycles. Why no stall cycles? Why is that? Because I am doing sequential operation. Because after I3, I4 was supposed to come and it is coming. Branch is not taken, right? I am not going to I7. Sequential operation. Okay. So that is what happened. That is a point. These are the two important points that I need to understand. So let's first draw the tree diagram. So if I have n instructions, out of those n instructions, this information is already given. Okay. Out of those n instructions, right? In the first part, they have already told me that I have 20% are branch instruction. So, okay, 20% are branch instruction, that is already given in the part 1, right? So 20% are branch instructions. So here n not branch is 0.8 n and n branch is 0.2 n. I have 20% branch instruction. Now out of this, right, out of this 20% branch instruction, they are telling me something. What are they telling me? They're telling me that out of this 20% branch instruction, right, when 80% of all the branch instructions are conditional branch instruction. So 80% are conditional branch instruction. Out of all the branch instructions, 80% are conditional branch instruction. So I will do 80% of this. So what is 80% of this? I will simply multiply 0.8. So n conditional branch instruction will be simply 80% of this, right? So 0.8 into 0.2n. Okay. Also, remaining will be unconditional branch instructions. Unconditional branch instruction. What will be the remaining? Simply 0.2. You can either do 0.2 into this number, or you can simply subtract from this number as well. This number, you will get back the same result. Okay. So overall, this is what? This is basically 0.16n, and this will be 0.04n. Okay. And next, what they're telling me? They're telling me out of this conditional branch, right? Out of this conditional branch instruction, 50% of the conditional branch instructions are such that branch is taken. So I already know the result. So 80% are conditional branch instruction, and out of this 50%, so conditional branch taken, it will be, I have to multiply 0.5, right? 0.5 into 0.16n. And conditional branch not taken, it will be 0.5 into 0.68 only, 1.16 only, it will be 0.08n. Okay. So this is the basic tree diagram, right? This is the basic tree diagram. I hope you have understood this thing. So this is the actual happening, right? This is the actual thing. So calculate the average instruction execution time. So how do I find out the things here? So one thing I have to understand is that I have told you a point. Whenever the branch is taken, I will introduce stall cycles. If branch is not taken, I will not introduce any stall cycles. So how many total number of branch instructions where branch is taken? So it will be simply, I can give a notation, branch T, branch is taken. So it will be simply equals to, if I come back here, right, this many instructions, conditional branch instructions I have, where I know condition will be true and branch will be taken. Also, I have unconditional branch instructions. So those will be taken regardless. They don't have any condition associated with it. So those branch instructions will be taken. I don't care about those. So this plus this. Okay. So it will be NCBT plus N unconditional branch instructions. So how many NCBT I have? 0.08 n, basically both are same only. 0.08 n plus unconditional is 0.04, I think, yeah, 0.04 n. n. So what will be the total stall cycles introduced? The total stall cycles, right? N stalls. N stalls will be simply how many total branch I will take? 0.12, right? And for each of this taken branch, I have to introduce 4 stall cycles. That is 5 minus 1, 4 stall cycles. So it will become 0.48 n. So now finally I can write the average execution time for the part B. So this is right. This is for the part B actually. I will write from here. So this will be equals to K plus n minus 1 plus n stalls into TP divided by the total number of instructions, that is n. We started with n, right? So again, I can ignore K minus 1 as n. I will assume my n to be very larger. N to be very larger than K minus 1. So obviously I can ignore this. So this will be equals to 1.48 n into 2 nanoseconds divided by n. So it will be 2 into 1.48. So it will be almost equals to 2.96. Okay, this is C won't work. 1.4, just hold on. It is 2.96, I know that. Just I want to calculate. 1.48 into 2, yeah, 2.96. So average execution time is 2.96. Now you can see that if branch is like few branches were not taken, right? Previously what I was doing, I was actually giving time for all branch instructions. So now some way I got to know that few branch instructions are taken and few are not taken. So I can actually not give stall cycles where branch instruction is not taken. So I can save time. So this is how our current processors save the time, save the execution time. You can see the average execution time has reduced. It was previously 3.6. Now it has reduced to 2.96, right? Almost 0.6 nanoseconds has been reduced. So this is how we do branch prediction. Previous lecture I told you we use some branch prediction techniques. So this is how we save the time, execution time, by predicting the branch. Okay, so that is for some other topic. We will not go into that. Okay, so I hope you have understood the concept here. Okay, so let's solve the next question of this particular similar type of topic only. So this is again like whenever hazard question comes, right, it's a very big question and student gets scared by just seeing the length of the question. Okay, by just seeing the length of the question they get scared. So an instruction pipeline has 5 stages. So I have 5 stages. First is instruction fetch. I will write things. Instruction fetch, instruction decode, and register fetch. So operand register fetch happens here simultaneously. Okay, happens here simultaneously. And then I have instruction execution, EX. Then I have memory access, MEM. So they will mention what each thing does. Whatever is required, they will mention it. And then I have register write back. So WB. Okay. Each stage with latency is 1 nanosecond, 2.2, 2 nanoseconds, 0.75. So from here, can you find out the TP? TP will be what? TP will be maximum of 1, 2.2, 2, 1, 0.75. Okay, nanoseconds. So this will be equals to how much? This will be simply max of 1, 2.2, 2, 1.7. So TP will be 2.2 nanoseconds. Okay, and what else they're telling me? To gain in terms of frequency, the designers have decided to split the ID slash RF stage into three stages: ID, RF1, RF2. So this ID slash RF phase, right, has been split up into three phases: ID, RF1, ID, RF2, each with latency 2.2 by 3. So now this highest latency, right, of a stage has been reduced to 2.2 by 3. So now can you tell me what will be the pipeline time? This is TP1 actually. What will be the TP2? Now I will have 5 stages. K will be equals to 5, not 5, sorry. Previously I had K was equals to 5 only. Now K will be extra 2 stages has been added. ID, RF1, RF2, RF1, RF2 is extra. So it will be total 7 stages, and TP will be maximum of 1 divided by 2.2 by 3. What is 2.2 by 3? 2.2 by 3 is 0.73. 0.73. Okay, then everything else is same. 2, 1, 0.75 nanoseconds. Okay, so TP2 is maximum of this. So what is the maximum of this? Maximum of this will be, now maximum TP has reduced. It will be 2. It will not be 2.2 anymore. 2.2 anymore. It will be 2 nanoseconds. Now also the execution stage is split into, okay, also the execution stage is also, I should have written the read the question. Execution stage is also split into 2 stages, that is execution 1 and 2, each of latency 1 nanoseconds. Oh, so sorry, so this K also, this will become now 8 actually, because this, right, this is the execution stage, right, where it was previously taking 2 nanoseconds. Now it will only take 1 nanoseconds each. So I'm sorry, so this also has been splitted up into 2. 1, 1. So my TP will be 1 nanoseconds. Okay, because highest is 1 nanoseconds only. So I have reduced my TP cycle time, but the number of cycles has increased. Now what they are telling me? The new design has a total of 8 pipeline stages, as I have written here, 8 pipeline stages. A program has 20% branch instructions. So as I read the question, I will just draw the tree diagram. That will be very, very helpful to me. So a program has 20% branch instructions. Okay, so n branch is 0.2n and n not branch is 0.8n. okay, next, which execute in execution stage. A program has 20% branch instruction which execute, like it, what is telling, which execute in the execution stage and produce the next instruction pointer at the end of the execution stage in the old design. So what is this telling me? This is telling me when does the branch condition gets evaluated. So I told you, right, they will give you in the question when does the branch condition gets evaluated. So the branch condition for this type 1 of system, branch condition gets evaluated. For type 1 it gets evaluated after execution stage, and for the type 2 system they would tell me it gets evaluated after the execution 2 stage, at the end of the execution 2 stage. Okay, fine. If the instruction fetch stage stalls after fetching a branch instruction until the next instruction pointer is generated. So until the branch condition gets evaluated, then only the next instruction fetch will occur. It will start. Okay, restart. So all instructions other than branch instructions have an average CPI of 1. In both the designs, all the instructions other than branch instruction has an average CPI of 1. What does average CPI of 1 meaning? 1 means, I will explain. Just hold on. Average CPI average is 1 for non-branch instructions. What does it mean? What was the meaning of CPI? Meaning of CPI was cycles per instruction. So if I have n instructions, n number of non-branch instructions, each n number of non-branch instruction will take n cycles. So if I have nb, like this non-branch instruction, they will take nb amount of cycles, right? And what is nb? Not nb equals to 0.8 n. So I will take 0.8 n cycles to evaluate. Okay, all other instructions has this many cycles, so it will take them 0.8 n cycles to evaluate that particular instruction, non-branch instructions. The execution times of this program on the old and the new design are p and q nanoseconds. So they are not talking about the average execution time, they are talking about execution time. So in system 1, the execution time will be tx1 and it will be tx2. And what are they asking? They are just asking me, this will be tx2. They are just asking me what? They are asking me the ratio of tx1 over tx2. tx1 over tx2. So they are asking me this, right? They are asking me the ratio of tx1 over tx2. So for this, I need to find out the tx1 and tx2. Okay. So how do I find out? So first I will write for system 1 p, okay, and q, system 2. I will do side by side. So actually, how many stall cycles I need to provide? N stalls for system P, right? For system P, number of branch instructions is constant, right? 0.2 n. And if they have told me I have to wait until the branch only, then only I will be able to start my next instruction fetch. Correct. So I have 0.2 n number of branch instructions, and for each of these branch instructions, how many cycles I have to wait? Here comes the interesting part. How many cycles I have to wait? I have told you, if the branch instruction is evaluated in the ith phase, the number of stall cycles that I need to provide for a single branch instruction will be I minus 1. So it is getting evaluated in this phase, right? In the branch instruction is getting evaluated in the execution phase. And what is the execution phase? It is the 1 to 3rd phase. Third phase, right? So here it is the third phase. And in execution 2, it is the what phase? It is basically in execution 2. If I just, okay, I haven't written it down, so I will write it down. Okay. So this is for P and this is for Q. I will write down the stages actually. So first I have instruction fetch, then this IDRF has been divided into IDRF to RF1, then this execution, then execution also has been divided into 2 stages, execution 1, execution 2, then memory, then write back. So here, right, here my branch conditions gets evaluated in the second type of system. So what stage is this? 1, 2, 3, 4, 5, 6. In the 6th phase, right? In the 6th phase, my branch condition gets evaluated. So here, right, for one branch instruction, I have to provide 3 stall cycles. For 0.2 n branch instruction, I have to provide, 2 stall cycles. So it will be 0.2 n into 3 minus 1, that is 2 into 0.2. In Q system, for one branch instruction, I have to provide 6 minus 1, 5 stall cycles. Okay, but for 0.2 n branch instruction, I have to provide 0.2 n into 6 minus 1. So this will be 0.2 n into 6 minus 1. Why am I writing 6 minus 1? To show you the significance. Okay, to understand the significance that this 6, right, is the phase where the branch instruction gets evaluated. So this, like, I am stressing on this point because I know there will be doubt. So this is the phase where the branch instruction gets okay. So this will be how many stalls? This will be 0.4 n stalls, and this will be 1, like basically n stalls. Okay, now I need to find out the execution time. So how do I find out t execution time of p or 1? See this, right? I can write this as p as well, p over q, right? That is what they're asking me. So execution time of p will simply be equals to, if I didn't have any hazard, how many cycles I required. So how many remaining cycles are there? So if I didn't have any hazard, right, normally how many like cycles I needed to provide? Normally how many cycles I needed to provide? K plus n minus 1, correct? K plus n minus 1. This is the number of cycles that I needed to provide. This is Kp actually. This will be Kp. Plus the extra stall cycles. This is n stall p. This is n stall q. N stall p. Okay, this will be equals to how much? This will be, as n is very large, n is very large, so we can ignore the k. We can ignore the k. N is very large. My assumption is n is very large, so it will be 1.4 n into, obviously you forgot the tp, right? You have to write the tp of p. Okay, so it will be tp of p is 2 nanoseconds, so it will be 2.8 n nanoseconds. Now in this case everything will be similar only, but values will change obviously. So it will become tpq, this will be q, this will be q, and this, right, will be n plus how many stall cycles? N stall cycles, right? So this will be 2n actually, n plus n into 2 into what is the tpq actually? What is the tpq? Tpq, right now has become here, if you see, it is 1 nanoseconds only. So it is 1 nanoseconds only. So it will be 2n nanoseconds. And what are they asking? They are asking me the ratio of t execution p over t execution q. So obviously there has been some improvement, right? So it is 2.8 n divided by 2n, so it is 1.4. so this is, by this much approximately I have improved. Sorry, this is, was this 2 nanoseconds or 2.2? just hold on, this was actually 2.2. sorry, this is 2.2, right? So this will simply not be 2 nanoseconds, this will be 2.2 actually. It will be almost 3.08. so this will be 3.08 n. So obviously things will change a bit. This will become 3.08, then this becomes 1.54. okay, so the ratio becomes 1.54. so this will be the answer of the question. This is also, actually, if you don't know, indirectly they have asked the speed up basically. Speed up between what? Speed up between system 1 and system 2. This is not comparing with non-pipeline, this is comparing with system 1 and system 2. That's it. Okay, so that is what we are comparing for this pipeline. Answer will be 1.54. I hope you have understood this. Now I know many teachers, I have seen many educators just use the formula. CPI is given, right? They will use some formula and you will not be able to understand this. Okay. So I have tried to keep things as less formula intensive as possible, as conceptual as possible. Okay. So I have not written any formula anywhere, right? I have directly solved with concepts. Okay. Directly I have written the concepts here. This is a formula, yes, but I have explained what does each term mean here. So obviously my assumption here is n is very greater than k. That is my assumption. Okay. So that is the first thing that you need to understand and that you need to identify. Okay, this for some reason this gets opened. Fine. Okay. So yeah, I hope you understood this thing, that for n instructions, how many cycles I anyways would have required n cycles, but extra cycles I have to provide with install due to the extra branch instructions. Those branch instructions are also instruction only. So normally, if I didn't have to evaluate the branch condition, I would have taken n cycles, but I had to provide few extra stall cycles because few of them were branch instruction. And how much extra stall cycles I needed to provide? This number of branch instructions multiplied by the extra number of cycles per branch instruction. This is the extra amount of cycles that I needed to provide in addition with n instructions. Okay. So here CPI equals to 1 signifies what actually? If you want to understand what does CPI equals to 1 signify, CPI equals to 1 signifies that indirectly they have told you that n is very greater than k minus 1. Why? Because what is CPI? CPI is cycles per instructions, and in pipeline I know new execution of new instruction takes only single cycle when n is very large, right? If n is very large, at every cycle I am getting a new output. It is a pipe and pipe is fully filled, so at every cycle I am getting a new output. So that indirectly they are telling you that n is very larger than k minus 1. Okay. So this question is a very elegant and very good question and lengthy question as well. So I know students get scared from this question, and trust me, even the CS branch student won't be able to solve it using basic concept which I have taught you. Okay. You are EC, but you will be able to solve better than those guys. Okay. Trust me, you know COA better than those CS branch guys. Okay. So yeah, let's study the next question. So in the next question, a CPU has 5-stage pipeline and runs at 1 GHz frequency. So CPU has k equals to 5 and the frequency, clock frequency is 1 GHz. Instruction fetch happens in the first stage of the pipeline. Instruction fetch happens in the first stage of the pipeline. A conditional branch instruction computes the target instruction and evaluates the condition in the third stage. So here my I is equals to 3, right? At third stage, I am evaluating the condition of the branch. Okay. So this is very important thing. The processor stops fetching new instructions following a conditional branch until the branch outcome is known. So obviously the same thing only, we'll stop our instruction fetch if I currently am executing a branch instruction, and then I will execute the branch instruction. I will execute the next instruction after the evaluation of the condition of the branch instruction. So I have to wait till this third phase, right? So a program executes 10 raised to power 9 instructions. So my n, I will assume n equals to 10 raised to power 9. Out of which 20% are conditional branches. So again, I will draw the tree diagram. So n is here, and out of this n, 0.8 are actually non-branch instructions, and this is 0.8 in, and 20% are branch instructions actually. 20% are branch instructions. Okay. So next, what they are telling me, if each instruction takes 1 cycle to complete on an average. So basically they have given me CPI average. Okay. Each instruction that it is taking 1 cycle to complete. I already know this. In pipeline, each new instruction take only 1 cycle to complete, because it is pipeline, right? Pipeline is already filled and is very higher than 1. I already know this. Even though they are telling me, I already know this. The total execution time of the program will be, what will be the total execution time? So they have given me f clock, right? From this, I will be able to find out my cycle time, TP. TP will be 1 by f clock, or this will be 1 nanoseconds. Okay. So I know how many stalls I needed to provide. I have branch instructions. Point to n are branch instructions, right? And I know each branch instruction will cause how many stall cycles. It will be I minus 1. So 2 stall cycles, 2 extra stall cycles I have to provide for each branch instruction. So it will be again 0.4 n. Okay. And overall, how many number of, like, what will be the total execution time of the pipeline system? It will be simply total number of cycles, which is k plus n minus 1 plus the extra stall cycles that are needed to provide for the branch instruction into obviously each cycle time, TP. So k is actually 5, right? K is 5. N is, anyways, 5 will be ignored. N is very, very large. 10 to the power minus 9, 10 to the power 9, so it will be anyways ignored, but still. So I will not write this right now. I will keep it n as it is, because here also it is in terms of n only. So this is 0.4 n into TP is 1 nanoseconds. So like I can ignore this, right? I can ignore this 5, 4. This will be anyways ignored because it is 1.4 into 10 raised to power 9 into 1 into 10 raised to power minus 9 seconds. So this will come out to be 1.4 seconds simply. So your answer will be 1.4 seconds. This is a simple question, and these are a simple question you will be able to solve after solving this question. This was the highest difficulty level that they can ask. Okay, this is the highest difficulty level that they can ask. Previous question was also a very good question. Okay, so I hope you're enjoying the lecture. So obviously, what are the solutions to this branch hazards or control hazards? Basically we use delayed branch, right? We have the software solution. Basically compiler detects it is a branch instruction, so we introduce stall cycles that we have already been doing, that we have already learned, right? So our next instruction will be fetched only after this branch is evaluated. So we have our compiler does this. That's why it is known as a software solution. Compiler gives a delayed instruction, also known as dummy instruction, which is not related currently. It is some other instruction. If the compiler needs to evaluate this, compiler, it doesn't want to sit idle. So let's say you are on a factory, okay, and you are building manufacturing cars, right? And your previous stage has stopped due to some delay or some hazard, okay? So now what you will do? Will you sit idle? You can do some other task. Your manager will tell you, okay, currently project A is installed, you do project B. So I will do project B, which is completely independent of project A. So it can happen. Or sometimes what they do is they provide no operations. We don't do anything. We just sit idle, just like stalls. Same as stalls, nothing else, same as stalls. Understand, we are not doing anything. We're just sitting idle here. Okay, we're not doing anything, sitting idle. So we introduce stall cycles, and only after this execution of the branch instruction, then only I start my instruction fetch. I go to the target instruction and I fetch my target instruction fetch. Okay, so like this I have explained previously as well. Only after the execution of, only after the evaluation of branch instruction, I will evaluate I will fetch next instruction, also known as target instruction. Okay, so like this we already know. I have just written this thing here. So another way to do is branch prediction. Although like this is very difficult, but I have told you, right? If I know already beforehand that 50% will be 50% time I will take the branch, then I have shown you the example that execution time gets reduced. So we can do this. We can implement this hardware solution. If the driver anticipates the direction, like I'm giving you an analogy beforehand with experience, right? With experience, the driver knows whether I need to take the, you are inside your like a very busy road, right? And there is a left turn and right turn. And if the driver is situated in that location for years, right? He knows at 8 p.m. whether I need to take the left turn or right turn. By experience, he knows the congestion or the jam will be on the right turn, so he will not take the right turn, he will take the left turn. Okay, by experience. So I just given you an analogy, but actually there are many algorithms and those things go inside the computer. We don't want to get into that. But if we are able to predict the branch, right, then we can save the time. Okay, if we are not taking the branch, then obviously it will be sequential. So we are saving the time there. Okay, so if the guess is correct, no delay because I fetch the next instruction instantaneously. If wrong, the driver backtracks or flush the pipeline. So if our guess was wrong, right? So we have fetched the sequential instructions, but those are of no use because I will go to the target instruction. So I have to flush everything. I have to delete everything, right? That is the main thing. So if the pipeline prediction is correct, pipeline proceeds without any interruption. If the prediction goes wrong, pipeline rolls back the branch instruction, rolls back to the branch instruction. It goes back to the branch instruction and deletes whatever that pipeline has done till that point. Okay, it will delete all the other things and then it will fetch the correct target instruction. Okay, so now we'll study about the structural hazards. So what are structural hazards basically? So let's understand with a basic example. Imagine a busy grocery store with only one cash counter. Two customers arrive at the same time but can't check out simultaneously because the counter is already in use. There is a line, right? There is a cash counter here. Okay, and two people are coming to the cash counter, right? But I have only one cash counter, so this can only service one cash counter because someone has to pay. Then like he will give the bill to that person, right? He will take the his purchase items. So I can only resolve one customer at a time. But if two customers come, I cannot do that. So first I have to resolve this customer, then the next customer. So I've also given an example of like movie and friend. Okay, so then what we do, we create a queue. Basically we create stall cycles. We tell this person to wait until I finish with this person, with this customer. Then after finishing, this customer goes away and then this customer comes in. So what we do, we just provide a stall cycle. So let's understand with a computer example, right? This structural hazard also is known as resource conflict because two instructions are actually at the same cycle are actually applying for the same resource. Occurs when two instructions require the same hardware resource at the same time. Consider a pipeline with one memory unit shared for register fetch and data access. So I have only a single memory unit, right? Where I have told you, right? So data comes into the memory unit from any location. Okay, and then again data goes out of this memory unit to any memory location. So I have only a single memory unit. So if I have a single memory unit, what will happen? Instruction one is load R1000. So basically what it does is load the whatever content that is stored in memory location 1000 and load it to R1. Instruction 2 is store 2000 R2. So basically whatever is present in R2, I will store that value in memory location 2000. So assumption is we access the memory in the operand fetch stage. Okay. So what we can understand is that here I am doing instruction fetch, correct? So this is also accessing the memory, right? Because we have only a single bus. So instruction is getting fetched from the memory location that is address is pointed by the PC. So it gets fetched here. Then I am decoding, fine. And in this decode, I am also doing instruction fetch. So I can do the instruction fetch here, okay? Because there is no resource conflict here, okay? Here I am doing a operand fetch after this, okay? So if I am doing an operand fetch, this should be decode. Actually, this should be decode the instruction. Okay. So what we can assume is one assumption. What we can take. This is a bit wrong. My assumption is operand fetch, right? Operand fetch takes 2 cycles. So here it is a standard 5-stage pipeline only, but one of the assumption is operand fetch takes 2 cycles. Okay, it takes 2 cycles. So if operand fetch takes 2 cycles, then a third cycle I will do operand fetch, and in the next cycle as well I will do operand fetch. Everything will be shifted by a single cycle. So This cycle will also be a operand fetch because I need 2 cycles, and this cycle will be execution phase, and this cycle will be write back finally. Okay. So now here first instruction it is totally fine, so all the cycles are fine. In the next instruction, in second cycle, I am doing instruction fetch because I know first cycle I do instruction fetch of instruction I1, and in the second cycle I do instruction fetch of instruction I2. Next I can decode the instruction, no worries. So this will be decode only, this will not change. This will be decode the instruction. Next is where the things will change actually. Here I am supposed to do the operand fetch, but currently I can observe that operand fetch is getting used. So what does operand fetch do? It fetches the operand from the memory location to its own general purpose register. Correct? But memory unit, I have only a single memory unit, right? I only have a shared single memory unit. If I have a single memory unit, so memory unit is already getting used to execute this particular micro operation, right? So I cannot use operand fetch here. Same example as cache register. Already a memory unit is getting used. I cannot use that same memory unit here. So this will cause a stall cycle here. Stall. I have to provide a stall cycle here. Then after I provide a stall cycle, this instruction I1 is not using the operand fetch anymore. It's not using the memory. It is using the ALU. So now I can use the operand fetch here. Now I can use the operand fetch without any resource conflict, because here in this particular cycle, fourth cycle, they were asking for the same resource at the same time, but I cannot do 2 things at a single time. I can only do 1 thing at a time. So after this operand fetch will happen, no worries, and after that this will also be, this will take 2 cycles of operand fetch. So this will be operand fetch and this will be execution. Okay, and this will be write back. But here is the main concept that is lying underlying concept, right? We are having resource conflict. Okay, so here actually this should be in cycle 4. In cycle 4, both instructions try to access the memory, causing 1 stall cycle, because I cannot give access to both the instructions. So what I will do, first I will finish this, because I am in the middle of this. I will finish this, then I will come to this next instruction, right? Solution in real life, add more cache counter. So we can add more memory units. If I add more memory units, so I can handle multiple customers simultaneously. So in pipelines, what we do in real life, we do add more cache counters. In pipeline, we add separate memory units for instructions, fetch and data access. So we can do all these things. We can add separate units, right? But sometimes it is not possible. So we have to only provide stall cycles. Okay. So this is a comparison table between all the different types of hazards. So what is structural hazard? It is like the hazard that we studied now. It is a resource conflict, where if I have multiple instructions competing for the same hardware resource. Data hazard, an instruction depends on the result of the previous instruction still in pipeline. So remember, only raw dependency are the true. Raw, raw. What is raw? Raw agent or something like that, right? So raw dependency is the true dependency. Other dependencies are basically false or anti-dependency. What was the anti-dependency? Anti-dependency was WAR. You can write a short notes like this, right? This is anti-dependency and this is true dependency. And what was false dependency? False dependency was W, because we're just writing back. Okay, it doesn't matter. So this was the false dependency. Okay. And in control hazard, we have just studied, that is branch or jump instruction disrupt the sequential flow of the instruction. Okay, hence we have to provide stall. So everything, the solution is mainly providing stall cycles. Okay, now we will solve few questions on this particular hazards. Okay, for a pipeline CPU with a single ALU, consider the following situations. The J plus ith instruction uses the result of jth instruction as an operand. So let's say J is 3. So fourth instruction, okay, uses the third instruction. So result of third instruction is getting used in the fourth instruction. So I can do it like I have just taken an example that R1 equals to R2 plus R3, and I do R4 equals to R5 plus R6. Okay. The execution of a conditional jump. Okay, like these are following situations that it telling me the execution of a conditional jump instruction. So this is a branch type instruction, right? Branch control hazard can happen. The jth and j plus ith instruction require the ALU at the same time. This is basically resource conflict, right? Resource conflict. This is like a structural hazard. And this is data dependency. What are they telling? Which of the following can cause hazard? All of them can cause hazard. Like these are the three different types of hazards. So all of them obviously can cause hazards. So option D will be correct. So let's solve the next question. So in the next question, we have a code and it is run on a pipeline processor, and I have a extra branch delay slot. Like this were old questions, that's why the language is not clear. I will explain. I have an extra branch delay slot here. Okay. And what they're telling me, which of the instructions can actually occupy the delay slot? Where should I place the delay slot to properly for this code to function without any modification? So if I place a delay slot here, right? If you tell me I will place the delay slot here, I2, will that be beneficial for me or not? Okay. Now here, right, what I'm doing is, if I observe this R2, right, is getting used, like it first I'm writing, then I'm getting reading from it. So actually there is a raw dependency between I1 and I3. So obviously I cannot just simply add a branch delay slot because there is a raw dependency. So this instruction has to wait until this instruction gets evaluated. So I cannot modify anything between I3 and I1. In I2 and I4, if I see, I again have a raw dependency, right? This R4 is getting used here, right? And there is is there any raw dependency? Yes, there is a raw dependency because this R4 will read the value of R4, right? So there is a raw dependency here as well, and there is a raw dependency here as well. Read after write, right? All this is a raw dependency. So I cannot mess up with I2 as well. I3 as well I cannot mess up. So in I4, actually I will give the delay slot Y. Why I will give the delay slot in I4? Because I can give the delay slot in this, between this instruction, right? I can give it here. What I want to do is, even if this instruction gets delayed, right, it doesn't affect the previous instruction. Okay. Even if this instruction gets delayed, it won't affect the previous instruction. Okay, it won't basically. So that's why I can place a delay here, because what I'm doing, I'm branching to a label if R1 equal to 0. So it's not like these two instructions are related. R1, I'm not changing anything. I'm not changing R1. I'm just reading R1 here, right? So I can provide a delay here because I don't have any data dependency. So instructions I4 can be used to provide a delay slot. Now I know this question is confusing. If this is confusing, skip this question, because these types of questions will not be asked nowadays, because previously what used to happen was language was not clear. That's why understanding the question is very difficult. Now they will explain the question very well, because you get a paragraphs of question, right? So it's very big question. So don't worry, you'll understand it. So now let's come to few new terminologies like pipeline efficiency. What is pipeline efficiency? Pipeline efficiency is a measure of how effectively the pipeline is being utilized. Okay, how effectively I am able to utilize the pipeline. It is expressed as a ratio of achieved speed up to the ideal speed up, typically represented as a percentage. In an ideal pipeline with no hazard, the pipeline operates at 100% efficiency, because my install equals to 0, right? Install is 0. Now if install is 0, then if n is very, very large, right? If n is very, very large, this should be installs, not st. This is installs. What is this basically? This is S ideal. S ideal will be the highest because it talks about the highest speed up that can be ever achieved. So S ideal, S achieved will be this. Now if install is 0, right, and my n is tending to infinity, what will happen? This will be Tn by Tp, which is equals to S ideal. Then my efficiency is 100%. That's why it is written 100% if the install is 0. Okay. If install is 0, n is very, very high, this nn gets cancelled, it is Tn by Tp, S achieved is equals to S ideal, that hence my efficiency is 100%. Okay, so that is the, this should be installs, right? That is basically the definition of efficiency, pipeline efficiency. So sometimes if they will ask questions from pipeline efficiency, if they are asking questions from pipeline efficiency, you will understand that they are talking about the ratio of S ideal upon S achieved. Remember S ideal, sorry, not, I'm telling you the wrong thing. It will be S achieved upon the S ideal as written here, right? Because obviously S achieved will be lower than the ideal, the maximum speed up that I can achieve, right? It will be always lower than that. So there is a question, this came on ISRO, I think. So a pipeline P operating at 400 megahertz has a speed up factor of 6. So its speed up factor is 6 if it is operating at 400 megahertz, right? So S achieved is 6 if my F clock is 0.4 gigahertz. Okay, so and I'm operating at 70% efficiency, so my efficiency of the pipeline is 70%. From here, can I find out the ideal speed up? What will be S ideal? I know S ideal, S achieved upon S ideal is equals to efficiency, right? So S achieved is 6 upon S ideal equals to 0.7 basically. So S ideal will be what? Will be 6 by 0.7. 6 by 0.7. So it will be 8.571. Now this is equals to what? This is S ideal is equals to Tn upon Tp if n is very, very high, right? Now they have not mentioned anything. They have not mentioned anything. And what do I want to know? I want to know the number of stages. Okay, they have not mentioned the number of stages and I want to know the number of stages. They have not mentioned whether the stages are balanced or not. So what I will do is I will assume nothing is mentioned. So I will assume all stages are balanced. Okay. So if I assume all stages to be balanced, then my Tn will be what? Tn will be simply KTP. How this comes? Lecture 1 of pipelining. I have explained how this comes, right? So Tn by Tp will be K. So this will be equals to K. Now obviously K is an integer. It is a number of stages. So if it is number of stages, right? K has to be greater than equals to this number. Why? Why it has to be greater than equals to this number? Because only in the balanced case Tn is equals to KTP. For all other cases, if system, I will assume if system is unbalanced, right? If pipeline is unbalanced, my Tn will be less than equals to KTP. Why? If you remember, I shown you example as well. Let's take example of 4 stage 2, 2, 2 and 2 nanoseconds, right? So in case of balance, my Tn will be simply equals to 8 nanoseconds, basically sum, and which is equals to 4 times 2, which is 8, right? If I add and then multiply 4 times 2, that is same. But in this case, if it is unbalanced, right, 1, 2, 3, 4, Then what will be my Tn? Tn is sum, right? Sum of all the stage delays. Remember, Tn is the non-pipeline execution time for a single instruction. So it will be 1 plus 2 plus 3 plus 4. That is 8, 10 nanoseconds. But what will be KTP? KTP will not change, right? KTP will be what? KTP will be the maximum. Maximum is 4 nanoseconds. So it will be 4 times 4, that is 16 nanoseconds. So it will always be, KTP will always be greater than Tn. Okay. So I will just use this. I will not equate this directly with equals to K. I will just use this particular thing, right? So from here, what I can say? I can say that my K will always be greater than or equals to Tn over Tp. This will always be the case for balance, unbalance, all cases, right? And what is my Tn over Tp? Tn over Tp is here, right? Tn over Tp is 8.571. So K has to be greater than or equals to 8.571, and K is an integer. We know number of stages, it can't be a fractional number, it has to be integer. So from the options I can see only one option is telling me that K will be greater than 8.571. So obviously option D will be correct. All other options are rejected, right? K has to be greater than 8.571. All these options are saying otherwise. Okay. So I hope you have understood this conceptually. Okay, because many students, many students and educators also, they just mug you up this concept that this will be always true. This is not always true. Okay, if it is not balanced, unbalanced, it will not be always true. So you have to identify the relationship. What is the exact relationship? Okay, so now let's solve the next question. So we have a pipeline processor with the following 4 stages: instruction fetch, instruction decode, and operand fetch, execute, write back. So we have 4 stages, and in this only operand fetch happens. Okay, fine. The IF, ID, WB take 1 clock cycle each to complete the operation. So I will write the things down. Okay, I will write the things down. So IF, now this is a very, very good question. IF, ID, and WB take 1 clock cycle, and my execution stage depends on the instruction. How many cycles the execution stage will take, it actually depends on the instruction. The add and the sub instruction need 1 clock cycle. So in execution, if I have add and subtract, it will be 1 clock cycle, right? If I have add or subtract, it will be 1 clock cycle. Okay. And the multiplication instruction needs 3 clock cycle. Multiplication actually needs 3 clock cycle. Okay. Next, operand forwarding is used in pipeline processor. When can you use operand forwarding? If they are telling me operand forwarding is used, that means they are only talking about ALU to ALU operation. ALU to ALU operation. Else I will not be able to use operand forwarding. Okay. Only if I use ALU to ALU operation, then only I will be able to use operand forwarding. What is the number of clock cycles taken to complete the following sequence of instructions? So first I have add, then I have multiplication, then I have subtraction. Okay, how many clock cycles will I require? So first, what I notice is all these, right, are general purpose registers. All these are GRPs. So basically, I can use the concept of operand forwarding. Operand forwarding, because all of them are ALU to ALU operation. Okay. So now let's break it down. Let's solve it step by step to understand this better. Then I will tell you a method 2. Okay. First I will solve it using table method 1, which is the lengthy one. So this is instruction I1, right? And I1, everything is same, everything will take one clock, okay, everything will take only one clock cycle only, but except the multiplication, right? It is a addition instruction, so it will take one clock cycle. So it has 4 stages. So first I will do instruction fetch, then I will decode the instruction and fetch the operands, and then I will execute. It will take only one clock cycle because it is an addition operation, and then I will write back the result, so it has no issues. Okay, then in the second clock cycle I will start the instruction fetch of I2, then I will do instruction decode. As soon as I decoded the instruction, I got to know that it is a multiplication type instruction. So how many execution cycles will it take me? 3 execution cycles. So it will take me 3 execution cycles. 1, 2, 3. After that I will write back the result. Why 3? Because it is a multiplication type instruction. Okay, then in the instruction 3 I again fetch the instruction, that is fine. I fetch the instruction in the cycle 3, that is fine. Then I decode the instruction, right? ID. Then I got to know it is a subtraction type instruction, and then I will do the execution here because it is a subtraction type instruction, and you will be totally wrong. Why? I told you, right? There is a control hazard here. I cannot do execution because for execution I need ALU, right? To perform subtraction I need ALU, and already it is being occupied by the previous instruction. Okay, ALU is already occupied. Okay, it is already occupied in the previous instruction, so I cannot use execution here. I have to provide a stall. Here also I have to provide a stall. Then after this, finally my execution phase is over for the previous instruction. Finally I can do execution, right, of the third instruction. So execution will start here. It will only take one phase, one cycle, because it is a subtraction type instruction. Then I will write back the result. So how many clock cycles it took me? It took me total of 8 clock cycles to finally execute, right? If I didn't have provided the stall, I would have finished earlier as well, but I had to because the ALU was already occupied. So that's why I had to provide only provide a stall cycle, provide 2 stall cycles. Okay, I had to provide 2 stall cycles. So this is the method 1 to solve. Number of cycles will be 8. Option B will be correct. So 8 cycles. Now what is the other method? Method 2. First of all, I want to say only valid when a single type of hazard is occurring. Okay, only valid for a single type of hazard. For multiple types of hazard, I cannot use this. I simply cannot use this. Okay, so what I can say is that assume, or we know this, assume assume each take one cycle to execute a instruction in the pipeline, right? Because like after, if n is very larger than k, we take only one cycle to execute a new instruction. So assume each instruction take one cycle to execute the instruction, correct? Or like but we already, okay, one thing I know, no need to assume in this one. What we know, to execute without hazard, to execute n instructions without hazard, number of clock cycles. What was the number of clock cycles to execute n instructions without hazard? It was k plus n minus 1. Now, without hazard is this, right? But I have structural hazard. So how many stall cycles I have to give for a single structural hazard, right? So if I have a structural hazard, this is same like branch time instruction, right? So I have to give stall cycles. How many stall cycles I will give? So I have to wait till the resource is freed. So when will the resource be free? I can observe as soon as I finish the execution, right? For all this, we don't have any hazard. For addition, subtraction, it takes 1 second only. So we don't have any problem. But for multiplication, I have to give extra 2 stall cycles. Why? Because my execution finishes on which stage? 1, 2, 3, 4, 5. 5th stage. My execution finishes on the 5th stage. After this only I can start execution of the next instruction, right? So for multiplication, okay, for multiplication, how many extra cycles I am taking? Extra cycles. How many extra cycles I am taking? Anyway, execution anyway for all the instructions, it already takes 1 cycle only. For addition, it takes 1 cycle. For subtraction, it takes 1 cycle. That has been accounted here. That has already been accounted here. But how many addition cycles does the multiplication instruction take? How many addition? 2. So, extra cycles 2. Multiplication takes 2 extra cycles. So, what will be my total number of cycles? Total number of cycles to execute the program. It will be without hazard, whatever I get, and extra cycles due to hazard. So obviously every time you won't be able to draw the table on those things. This is how you calculate. Without hazard I calculate it is k plus n minus 1. So k is what? K is, it is a 4-stage pipeline. N is how, what? I have 3 instructions minus 1. So it will be 6 cycles. And extra cycles for multiplication I have to provide 2 extra cycles for multiplication. As I have only 1 multiplication instruction. If I had 2 multiplication instructions, I have to multiply it by 2. So it will be 6 plus 2 into 1. This 1 is due to what? As I had only a single multiplication instruction. So this will be simply 8 cycles. I got back the same answer that I solved in the previous, using the previous method, but you will not be able to use it always. This you will be able to use it only for a single type of hazard. Okay, so that is the important thing that I wanted to take away with this. This method is applicable if I have single types of hazard. Previously also we were doing the same thing, only we are adding the extra cycles, but it was stall cycles because we are waiting for the branch condition evaluation. Okay. So let's solve the next question. So here, right, another interesting thing, operand forwarding was present, right? So if operand forwarding was present here, right, if you observe that this R2, I was like, I ignored this, I was doing what? This is a RAR type dependency, right? If I see read after write type dependency. And this is also read after write type dependency. So as soon as I finish my execution here, I instantly give this value of R2. R2 is given to the second instruction, right? Second instruction. As soon as I finish, as there is a operand forwarding, okay? And here as well, the R4, as soon as I execute this R4, right? At the next stage only I start my execution, because I directly give the R4 into the next instruction. Okay, I don't take it from here, right? I don't take it from here. I don't take it from here. I directly, from this execution stage, I give it to the next instruction. Okay, that's why operand forwarding was present. Now, if operand forwarding is not present, how will you do? That is the question, right? If in the same question, provision, if in the same question, provision of operand forwarding, if in the same question provision of operand forwarding is not present, then how clock cycles, then how many clock cycles? Then how many clock cycles we would require to execute the same instructions? How many clock cycles would it require for us to execute the same number of instructions? Okay. So here operand forwarding is not there. So we don't have any shortcuts. We have only this method only. We cannot use any shortcuts. So actually I have to bring more space into this. So what we can do, right? So we can take a bit top. So this will be increased, this will be increased, this will be increased. Let me put this as T10, T11 and T12. Okay. So if operand forwarding is not present, what will happen is that here I will start with my instruction fetch of the instruction I1, then I will decode and do the operand fetch, then I will execute. As it is an addition operation, I will only take one cycle, then I will write back the result. In the next instruction I will do the instruction fetch from second cycle. I cannot instantly do instruction decode and operand fetch. I cannot do it. Why I cannot do it? Because I am still waiting, right? I am still waiting for it to provide me the result. Okay, actually it was ID. Yeah, ID is here. Previously what was happening was here, right? He was actually, yeah, previously what was happening is like, yeah, I can do ID here. That is fine, I can do ID here, but I cannot simply start my execution from here. Why? Because right now this connection is not there, operand forwarding is not present, right? So I cannot simply take the operands from the previous execution stage to current execution stage. I cannot simply do that. Okay, operand forwarding is not present, so this is not possible. So I cannot do execution. What I have to do, I have to provide stall cycles. I have to wait for this to be finished and this write back to happen, right? So I have to provide stall cycle here, and after this write back has happened, then only I will start my execution. Okay, then only I will start my execution and my instruction decode as well, because this will also be not correct. Previously there was operand forwarding, that's why my execution phase was directly getting its operands from the previous execution instruction. Okay, but now I don't have operand forwarding, so I will take the operands from the instruction decode stage only, and I cannot do instruction decode here because this instruction hasn't been done yet. So again I have to provide an extra stall cycle here as well. Okay, so finally after write back, now I am ready. Now I can start. Now I can do ID, instruction decode, then I can simply do execution. I know it is a multiplication type instruction, so it will take 3 clock cycles, and then finally after this I can write back the result. Now here, right, after this I can do the instruction fetch here. I can do the instruction fetch in the third clock cycle. But can I do ID? No, right? Because if you remember correctly, that your third instruction, right, was dependent on the second instruction. It has a raw dependency. So I cannot directly start the operand fetch here. I have to wait till the write back because there is no operand forwarding. So I have to provide stalls until here, right? So all this will be simply stalls. This will be stalls, right? And after the stalls only, I can start my instruction decode. This will be ID. Then I will have my execution of addition, not addition, this is subtraction. And then finally, I will write back the result. So after the 12th cycle, finally my instruction will be over. So how many cycles it took me? It took me 12 clock cycles. So this will be 12 clock cycles. Now you will say, sir, does this have any shortcuts? No, actually. This doesn't have any shortcuts, right? This doesn't have any shortcuts. You have to solve it like this only. If no operand forwarding is present, you have to solve using the tables. Okay, so that is very difficult. So let's solve this next question. Okay, so we have a 5-stage pipelined processor, and it has instruction fetch, instruction decode, operand fetch, perform operation, write operands. Okay, so 5 stages are there. Okay, so K is 5. And what it is telling, the perform operation stage takes 1 clock cycle. Sorry, the IF, ID, OF, WO take 1 clock cycle. So I have IF, ID, OF, WB are 1 clock cycle. Okay. And the PO of add a subtraction take 1 clock cycle. So PO, perform operation of add / subtract take 1 clock cycle, and the perform operation and the perform operation for multiplication instruction takes 3 clock cycles. For multiplication it takes 3 clock cycle, and for division it takes 6 clock cycle. Okay, so operand forwarding is used in the pipeline. So operand forwarding is used only for ALU to ALU operation. I can observe that everything is register. So it will, everything is ALU to ALU operation, right? Because we are using general purpose registers. What is the number of clock cycles needed to execute the following instructions? So will I draw the table again? No, I won't draw the table again. Okay, so we'll simply calculate. So without any hazard, because there is some hazard. What is the hazard? If I observe, if I just copy this thing, okay, and paste this here. Here, what can happen is there is a data dependency, right? Where is the data dependency? Here I have a data dependency, right? R2 and R2. I am writing, this is a raw type data dependency, and again here there is a data dependency. Now I have to check whether I have enough gap between instruction I0 and I2 so that there is no data dependency. If this instruction takes enough time, I have to actually check that. Okay, so how can I say is that, and okay, anyways, okay, no, this also has data dependency, right? So I don't have to check anything. This right here also I am reading back from R5 after updating it, and okay, so it's totally fine. Yeah, everything has a data dependency. This also has a data dependency, right? So like everything has a RAW data dependency. So how will I solve it? Simple. Without hazard, how many cycles it would take me? It will take me k plus n minus 1, which is equals to what? Is equals to k. It is a 5-stage pipeline. N, I have total 4 instructions. 4 minus 1. Okay. With hazard extra, how many extra I am requiring, right? Due to the data hazard, how many extra stall cycles I needed to provide. Okay. How many extra? This is 3, right? I have a multiplication instruction here. This is 3 clock cycle, and there is a data dependency. Just hold on. And not R2. Sure. Actually, there is no data dependency here. There is no raw data dependency here. From here to here, there is no data dependency, but there is what? There is hazard, right? There is control hazard actually. Control hazard. Not control, sorry. There is structural hazard. And this, there is a data dependency, but that I can ignore because here also there is a structural hazard. And why I can directly use? Because they have told me operand forwarding is used. So as operand forwarding is used, I can ignore raw or data hazards. Why? Because of operand forwarding. So I will only consider structural hazards because operand forwarding is present. I will not consider data hazards. Okay. Previously, also I ignored that. So how many extra cycles do I need to give for structural hazard? For multiplication, how many extra cycles it takes, including excluding the one cycle that anyways every instruction, every micro operation takes. It takes 2 extra. So this will be 2 extra. Multiplication and division will be 5 extra. So how many multiplication instruction I have? 1. How many division instruction I have? 1. So this will be extra cycles will be 2 into 1 multiplication plus 5 into 1. So this is 1 multiplication and this is 1 division. So total number of cycles will be what? 9, and this is 8 plus this is 2 plus 7, right? 2 plus 5, 7. This is 15. So total I will be requiring 15 cycles. So option B will be correct. Now you might say, sir, you ignored the data hazard. Yes, I ignored. Because why did I ignore the data hazard? Because the stall cycles provided due to structural hazards is more than enough to deal with the data hazards. I don't need to provide any extra stall cycles. Homework, you can make the table and see, observe yourself that I don't need to give any extra stall cycles for data hazard. Okay, because operand forwarding is there, data hazard won't be occurring. Okay, I hope you have understood this point. Let's solve this next question. So this question I took, I think, in the starting of lecture as well, but this question is a bit different. What we have to do? We have to say that what we have to find out. A pipeline processor uses 4 stages, and this like we have to evaluate, and everything is register to register. Everything is ALU to ALU, ALU to ALU. Okay, and they are telling me that the IF, ID, WB stage take 1 clock cycle each. So IF, ID and WB, it is a 4 stage, right? They take 1 clock cycle. And the other stage, execute stage, it depends on the instruction. Execute stage take 1 clock cycle for add, subtract and store. So EX takes for add, subtract and store, it takes only 1 clock cycle. Okay, for 3 clock cycles for multiplication and division operations. 3 clock cycles for multiplication and division operations. So it is 3 clock cycles. So how many extra I required? How many extra? Extra here for add is 0 only. For multiplication division I have to provide 2 extra clock cycles. Okay. Now what are they asking us? They are asking me operand forwarding is used in the execution stage to ID stage. Okay, operand forwarding, like operand is forwarded directly from the execution to the next ID stage, right? Directly it is forwarded. So I don't need to provide extra stall cycles. Okay, I don't need to provide extra stall cycles here. The number of clock cycles required to complete the sequence of instructions. So same question again, how many clock cycles I will require. So again I will find without hazard how many clock cycles I require. Without hazard it is k plus n minus 1, correct? K plus n minus 1, that is, it is a 4-stage pipeline. How many instructions I have? Total 1 2 3 4 5 instructions I have, minus 1, and extra, how many extra cycles I needed to provide, right? So for add, subtract, store I don't need to provide, but I have a multiplication, I have a division. So I have 2 instructions which take 2 extra cycles each. So this will be 2 times 2. So total number of cycles will be 8 plus 4, that is 12 cycles. Okay, so answer will be option B. I can show you using the diagram as well. Okay, so like this will be a bit lengthy. So what I can do, right? I can do one thing. First of all, I can delete this and I can take from here. So I have drawn exactly the table, instruction cycle table, for you guys to exactly explain what is actually happening. Okay, although I have done the computation, but I wanted to show you how it is happening. Here first instruction is a addition type instruction, and I can observe there is always a dependency. This is a dependency, this is a dependency, this is a dependency again, and this is again a dependency, right? So tell me in the comments below what is this dependency, question number, and tell me in the comments below what is this type of dependency. Okay, so we have a data dependency, right? And what is the type of the data dependency, you can tell me in the comments below. So but that data dependency will not be affecting us. So data dependency stalls will not be present due to data dependency. Okay, stalls will not be present due to data dependency. So what will be present basically? What will be the fault basically? So why will stalls be not present? I will explain in this table. I will explain. So first instruction is an addition type instruction. So it will have instruction fetch, it will have instruction decode and operand fetch, then execution, and then write back. Simple as. So I will start from next instruction. Next instruction is actually a multiplication type instruction, right? So I will just write in brackets what is the type of each instruction. This is add, this is multiplication, this is subtraction, this is division, and this is store. Okay, so what I can observe is I am doing the instruction fetch, I am doing the instruction decode and operand fetch. I can instantly start the execution of multiplication. Why? Although there is a data dependency here, but as there is operand forwarding, what will happen? The execution stage execution stage operands will go directly into the next instruction execution phase, because I have operand forwarding element. If operand forwarding was not enabled, I had to provide a stall cycle here, and my instruction decode and operand fetch would have started from here, right? But it is not. Operand forwarding is present. That's why there is no hazard due to data dependency. So we will see the hazard will come only due to structural dependency or resource conflict. Okay, so I know execution phase for multiplication will take 3 cycles and then write back will happen. Now for the next instruction, the instruction fetch will happen in cycle 3. The instruction decode and operand fetch also will happen in cycle 4. But the problem is I cannot exactly start here execution phase. Why? Because the previous instruction is actually using the ALU. It is using for to compute the multiplication, right? I cannot start execution phase here as well. Simultaneously in the same clock cycle, 2 execution phase cannot work. I have a single person for a single stage, right? A single person cannot do 2 tasks at a time. So I have to provide a stall cycle. These stall cycles are provided due to what? These stall cycles are provided due to structural hazards. Stall cycles due to structural hazards. Okay, these are not due to data dependency. So here I have 2 extra stall cycles. So how did it came here, right? Already I have shown you using the method what we do, but here we can visually see actually where the 2 extra stall cycles are present. Again, what will happen then after this stall cycles, my execution will start for the subtraction instruction, then write back will happen. Again, instruction fetch can happen after this, right? At the 4th clock cycle. Instruction decode can also happen. But also you can observe that the execution after the execution of this multiplication, I am directly feeding this result into the execution of the next instruction, right? Because there is a data dependency between multiplication and subtraction. If you observe, R6 is being read back here in the sub instruction, right? After being writing. So obviously I can directly forward this here, right? If let's say operand forwarding was not there, I had to wait till this write back. So I had to provide a stall here, then execution, or then the instruction decode would have happened, right? So I had to provide extra stall cycle. So that is the issue that I had to face. Okay, so I hope you understood this point. So yeah, again same thing will happen here as well, and same thing will happen here as well. You can visualize and see. I will not explain this further, but I hope you are understanding the point. The point being that if I have operand forwarding and like there are some structure like the hazard will be done due to only either structural hazard or branch. Okay, there it won't be due to 2 things if operand forwarding is present, and this method is only valid for a single type of hazard, right? If I have 2 types of hazard, then I have to do visually. That's why I have explained 2 methods, visually and both like just writing, right? Method like writing method, shortcut method. Okay, so I hope you understood this point. Let's solve the next question. An instruction pipeline consists of 4 stages: fetch, decode, field, execute, and result write. The 5 instructions in a certain instruction sequence need these stages for different number of clock cycles. So now actually different instructions has different number of clock cycles in different number of stages. Okay, so things are more and more difficult. So I have seen many educators teach you like you have to visualize, you don't have any method, but I will tell you one single method with the help of which you will be able to solve these type of questions, right? So they are asking me find the number of clock cycles needed to perform the 5 instructions. Different stages has different number of clock cycles. How will I solve this question? Now first of all, you have to actually draw the table here as well. If you don't draw the table, you won't be able to solve it. So this, right, this can be solved with a shortcut as well. If the cycles are given, this can be used with a shortcut. So the thing is, you have to draw these type of table, like exactly same table, but everything will be empty. Okay, so this much hard work you have to do, and this will not take you much time. This table will not take you much time to draw than this table, right? Drawing this table is very difficult, but this table will not take you much time. Okay, you have drawn the table, you have written the stages, and you have written the instructions. Now what you will do, you will write the addition. So you will write the, like, what does this box represent? This box represents the current clock cycle. Okay, so let's assume I have started with the instruction I1, I have fetched the instruction I1, right? So this is the current clock cycle. Then I went on to the decode. So after what clock cycle this decode instruction will be over? After third clock cycle, right? Because first clock cycle has gone for instruction fetch, then I have to take another 2 clock cycles for decode to happen. Second and third. First clock cycle instruction fetch, second and third for decode. Then how many clock cycles will I require to execute? Only 1 clock cycle, right? So I am at third clock cycle currently. I will require 1 extra clock cycle to execute. So it will be 4, the current clock cycle. So after this is done, how many clock cycles will I require to write back? I will require 1 clock cycle to write back. So currently I am at 4. So current clock cycle number will be 5. So after 5 clock cycles, my first input will be ready. I1 will be processed, basically will come out of the pipeline. Now what about here? When I will start my instruction fetch. So I will start my instruction fetch after before it was 0 clock cycle. I took 1 clock cycle, right? Now I am at first clock cycle. I need 1 extra clock cycle to do the instruction fetch of I2, right? So I will be at current clock cycle number will be 2. After this instruction fetch has happened, current clock cycle number will be 2. Now comes the interesting point. Here, how many clock cycles will I require to decode instruction I2? They have told me it will require me 2 clock cycles to decode the instruction I2. Now, this represents what? This represents the current clock cycle number. It is telling me that the instruction I1 decode will finish after 3 clock cycles. So from this 2 observations, right? These 2 observations, what I can deduce from these 2 observations, that decode of I1 will finish after third clock cycle. And what this particular thing is telling me, this is the first point that I can deduce. Second point is what? Second point is IF, that is instruction fetch of I2 will finish after second clock cycle. Now tell me one thing. Can I instantly start my decode of instruction I2 from third clock cycle onwards? No, I cannot, because after the third clock cycle only the decode stage is getting freed, right? This stage is getting freed only after the third clock cycle due to instruction I1. So I cannot start my decode from second clock cycle onwards. So from this I can deduce I have to start my decode from fourth clock cycle onwards. I cannot start from third clock cycle onwards because third clock cycle is busy. Already that stage is busy. Due to what? Due to which hazard? Due to structural hazard, or what do we call it? We call it resource conflict. Okay. So in short, what we do is, here what will be written? Here actually what thing will be written? That is the most important point. If I have some other color, yes, this is the other color. What will be written here is, like I can tell you logically what should be written is, mathematically what should be written is maximum of top and left plus its own clock cycles plus how many cycles it takes on, this is my own language, own cycles. What do I mean by maximum of this? So whichever one will be maximum, right? From that cycle onwards I will start, because I cannot start from second clock cycle because it is telling me that the decode stage is being used now. Okay, decode stage is being used until third clock cycle. I cannot start, let's say if this was 4, I cannot also start from 3 as well now, because the instruction fetch hasn't happened, right? The previous stage hasn't even finished and I am decoding the current instruction, which is not possible. What I am telling, let's say if this is 4, let's assume that this is 4. Now you tell me, if this is 4, then this first line will be, then the second line will be instruction fetch of I2 will finish after 4th clock cycle, right? Okay, after 4th clock cycle. And decode of instruction I1 will finish after 3rd clock cycle. You will say that decode stage is free now, so I can do my decode after 3rd clock cycle. No. The instruction fetch of I2 hasn't even been completed. How can I decode? Instruction haven't been fetched yet. How can you decode the instruction? Instruction itself hasn't been fetched yet. How can you decode the instruction? You cannot decode the instruction, right? So you have to wait. You have to put a stall cycle again. Okay. So obviously I will choose the maximum of these two. I will always choose a maximum of these two. If the instruction hasn't been fetched yet, how can I decode the instruction? If the current stage is busy, there is resource conflict, how can I use the decode stage? I have to give stall cycles. So that's why I told here maximum of top plus left plus my own number of cycles. So what will be this value equals to? Maximum of top plus left, maximum of top and left is what? Maximum is 3. 3 plus its own number of clock cycles that it takes to complete that particular stage is 2. So 3 plus 2, this will be, I will write this better. This will be, just hold on. This will be 3 plus 2. Okay. So this will be 5 actually. Can write this. Three plus 2 will be 5. Okay. Now in the next stage also I will do the same thing only. I will not explain again. I have already explained. If you couldn't understand this, please go and rewind. I will apply the same procedure here. I will check for the maximum of left and maximum of top. Like I will check from the maximum of left and top. So what is the maximum of left and top? It is 5, right? After 5 clock cycles, this I2 decode stage is getting finished. Although my execution stage is free from the previous instruction, but I cannot use it because the decode stage hasn't finished yet. So I will wait for 5 clock cycles, then I will add with my own clock cycle delay. What is it? 5 plus 2, that will be 7, right? So this will be 5 plus 2, it will be equals to 7. Now this also will be same only. So next ones I will write directly. So this again I will choose the maximum. What is the maximum? Maximum is 7, and what is its own delay? 1. So it will be 8. So here again, left I don't have anything, top I have 2. So what is the maximum of left and top? It is 2 only, and its own delay, that is 2. So it will be 2 plus 2, so that is 4. Then again the same thing, maximum of left and top, it is 5 plus its own delay. 5 plus 1 is, sorry, not 5, yeah, 5 plus 1 is simply 6, correct? This will be 6. Okay, then the maximum of these two, that is maximum is 7. 7 plus its own delay. 7 plus its own delay is 3. 10. Then again I will check the maximum. Maximum is this 10. 10 plus its own delay is 2. 12. Again I will check the maximum of top and left. Left I don't have anything. Top I have 4. So 4 plus its own delay 1, that is 5. Same thing. Maximum 6 plus its own delay, that is 9. Maximum plus its own delay, that is 12. Maximum, both are same only, so it will be 12 plus its own delay, that is 13. Again maximum, that is 5 plus its own delay, that is 6. Maximum 9 plus its own delay, that is 11. Maximum 12 plus its own delay, 13, and 15 finally. Okay, so after 15 clock cycles, I will be able to perform my 5 instructions. My 5 instructions will be processed. Okay, so this question is very very elegant. If you couldn't understand, please rewind that portion again. That is the most understanding like point of this particular question. So these type of question can also be asked. This topic is for different type of branch delays, right? If I have different types of, not branch delays, if I have different types of delays of each stage, then how will I solve? This is for the case of what? Actually, this comes under the topic of non-synchronized pipeline. Okay, I haven't explained this, but actually what happens is this comes under the topic of non-synchronized pipeline, right? Because every stage is not taking the same amount of delay, and you can observe that what a hassle this is to compute the total number of clock cycles that the instructions will take, right? What a hassle. That's why we don't use non-synchronous pipeline. So this is also the same type of question only. I have 4 instructions and each of them take different number of cycles so in each stage. So what will be the number of cycles needed to execute the following loop for I equals to 1 to 2. So 4 stage pipeline instruction. Okay, the number of clock cycles required by the 4 instructions is given. S1, S2 are stages S1. What is the number of clock cycles needed to execute the following loop for I equals to 1 to 2? So for I equals to 1 to 2, basically I have a loop here for I equals to 0, I equals to I'm starting from I equals to 1, I less than equals to 2, I plus plus, right? So like there is some code. This I1 instruction is there, then this I2 instruction is there, then this I3 instruction is there, then this I4 instruction is there. This is running, and after that what we do, we simply execute. So they are telling me how much time it will take me to execute this particular loop. So how many times the loop is running? So here I observe the loop is only running once, right? Loop is only running once. Okay, or yeah, loop is only running once, because I am starting from I equals to 1, then I reach the second stage. Okay, it should go from for I equals to 1 to 2, for I equals to 1 to, okay, this is not actually less than equals to, this should be less than 2. Okay, the loop is only running only once. Loop is running only once. It is only running once. It is not running more than that. If it would have run number of times, I will tell you how to solve. Okay, so if it is running only once, I can calculate for once how much time this whole cycle, right, it will take. I1, I2, I3, I4. So again I will do for the first I will simply write back the values. This will be 2, then I will add 2 plus 1, that is 3, then I will add 1 again, this will be 4, this will be 5, then again I will use the formula. Maximum of top and left, maximum of top and left is 2 plus its own delay, that is 1, so it will be 2 plus 1, 3. Again maximum is 3 plus its own delay, 6, maximum plus its own delay, 8, maximum plus its own delay, 10. Okay, then again, okay, everything is correct here, right? This 2, yeah, this is correct only. Then maximum plus its own delay, that is 5. Okay, this is only, I have only 4 instructions, right? Okay, this anyways can be gone. Maximum plus its own delay, that is 7, maximum plus its own delay, that is 9, maximum plus its own delay, that is 13, maximum plus its own delay, that is 6, maximum plus its own delay 9, maximum plus its own delay, that is, yeah, that is what, that is actually this will be 11, maximum plus its own delay, that will be 15. Okay, so one thing is wrong. Actually this should be I less than equals to 2 only. I made a mistake. It is going from I equals to 2 to 1. How many times it will run? Actually, my mistake, it will not run twice. It will run, loop is running twice. Why? Like at the start only I was right, but at the end I got it wrong. So why it will run twice? So it will start from 1. So for once it will execute, then for I equals to 2 again it will execute, right? Again it will execute. So if it executes again, it will be just twice, right? For once the loop is taking 15 cycles. So for once one loop 15 cycles, 2 loops, it will be 15 times 2, 30 cycles. So your option D will be correct. So it will take total of 30 cycles because the loop is running twice. Why? Because if you know a bit of C coding, you will know that if the loop is something like this, for I equals to 1 to I less than equals to 2, then for I equals to 1 it runs, then again I increment my I, it goes to 2, then again I check the condition for I less than equals to 2, 2 is equals to 2, the condition is 2, so I will run the loop once again and then it will end. Or if you want to know, I told you a shortcut, right? If you ever want to understand how many numbers are there between two numbers within a range, you can simply do what? You can simply apply this formula. Max minus min plus 1. So 2 minus 1 plus 1. So it is 2 times. So that's why the loop will run twice. Okay. So I hope you understood this point. So let's do this last question. Okay. Let's do this last question. So what is this question? We have a instruction pipeline of a RISC processor has the following stages. IF, ID, operand fetch, perform operation and write back. 5 stage I have. Okay. The IF, ID, OF, W all take 1 clock cycle. So except the perform operation, right? Everything takes 1 clock cycle only. 1 clock cycle. Okay. For every instruction. Consider a sequence of 100 instructions. In perform operation, 40 instructions take 3 clock cycles. So in perform operation, I have take 3 clock cycle. Okay. Then I have 35 instructions that take 2 clock cycle, and I have remaining 25 instructions which only take 1 clock cycle. Okay, so assume that there are no data hazards, no control hazards. There is no data hazard, no control hazard. What kind of hazard can happen? Only structural hazard. The number of clock cycles required for the completion of execution of the sequence of instructions. So how many clock cycles it will require me? So again I can use that formula, right? Simple. It will be what? It will be without hazard. How many clock cycles I will require for 100 instructions? K plus n minus 1. I have 5 stage, 5 plus 100 minus 1, and extra stall cycles I have to provide. Why? Due to structural hazard, right? Because obviously this takes more time. So obviously this instruction will use the perform operation stage more number of times. So the next instruction cannot use that. So how many extra cycles it has? Extra cycles. This will be 3 minus 1 extra cycles. Anyways, 1 cycle we anyways allowed to everything. This will be 2 minus 1 and this will be 1 minus 1. That is 0 extra cycle. So how many total number of extra cycles? Okay. So this will be this plus for 40 of this instruction I take 3 minus 1 extra cycle, right? So 40, each instruction takes 3 minus 1 extra cycles. How many of these instructions I have? 40. That's why this is 40 plus again 35 instructions take 2 minus 1 extra cycles. So total extra cycles will be 35 times 2 minus 1 plus 25 instructions take 1 minus 1, that is no extra cycle. That's why a 0 is there. So why am I writing this? Because like I think you will find this pointless. Why am I writing this? But there is a point to it. To understand this conceptually, why these terms are coming. That's why I'm writing this. Okay. So total number of cycles will be 104 plus this will be 80 plus 35. Correct? 80 plus 35. So this will be 115. So 115. So 219 clock cycles. So total number of clock cycles that I will need to finish this instruction will be 219. Okay. Please do keep in mind that this method is only valid for when only one hazard occurs throughout the pipeline, else this will be not valid. So this is a very important point, key point that I wanted to tell you at the end of today's lecture and at the end of our YouTube journey. So I hope you have enjoyed. Like we have covered most things on pipelining. Few things will be left that will be covered later on. Okay, you can check in the comments for more information about regarding that. Okay, so few things are left for pipeline. Most things gate syllabus is covered for EC domain and for placements as well. Most things are covered. Few things are left that will be, you can get the information from the comments below. Okay, so I hope you have enjoyed. If you did, please go in the comments below, tell your review, how you liked, what you hated. Okay, what you liked, what you hated, all those things you can tell. Please do. Don't forget to press the like button. Don't forget to subscribe to my channel for more content, okay, related to digital VLSI and analog VLSI. I hope you have enjoyed this journey of COA, and I hope I have kept you engaged and you have developed an interest in the subject if you already didn't had any interest in the subject previously. So yeah, that's it about our journey of COA on YouTube. Thank you for watching, and I will see you in the next video. Until then, happy learning.